hair underwater to help me breathe. And I'll spend 100 years until life's over with you, my dear. losing faith. Don't wanna talk about it today, but sometimes we go missing. In our thoughts we sink down low, but you know you can always call. Now I only wanna see that you're better, and smiling like you're on a show. I wanna know what's in your head. Take a pen and write me a letter. If words are too hard to say, now we can try to find a way. Now, just let me in. Time is moving.
All right, good morning, everyone. My name is Gloria Cambrala. I'm sorry for all the extra energy I have, but I have it all the time, so hope you guys get used to that. My name is Gloria Cambrala. I do developer relations for BiddleBox, which is under Supermodular. I'm formerly of GetCoin. If I've known you, like, come say hi, of course. I'll be your MC for this morning, and we'll get started right now. So I would like to bring up our first speaker. Our first speaker is Jeff Lampert. Jeff is the project lead for privacy and scaling exploration solutions for the Ethereum Foundation. And for Jeff's talk this morning, they'll be talking about Interep. And Interep is a bridging solution from Web 2 to Web 3. So with that, I'll go ahead and hand it over to Jeff.
Hey, thanks, Gloria. Hello, Devcon. Good morning. So, I'm Jeff Lampert. I'm from the Privacy and Scaling's Explorations team in the Ethereum Foundation. And I'm going to talk today about Interep, which is a project we've been working on. It's in the identity space. So, a brief introduction to what we do. There's lots of projects in the trying to bring identity into Ethereum. And they tend to be have some identity source and build it up from the ground. Our approach is a pragmatic approach where we build on the identity that we already have in our digital lives, and we bring that across to Ethereum so we can have an established pool of, or established identity pool, and we can integrate that into our Ethereum applications. So yeah, very much a pragmatic approach, building on the identity sources we already have. So what we aim to do is build a bridge from existing digital identity sources to Ethereum, integrate with providers of those identity sources, and then privacy is very important to us. So we build on the semaphore framework. Those building blocks all come together to form the basis of an application. So, identity. We spent a lot of time in our social networks. Some people more than others, but people spend a lot of time on their Twitter accounts and building up, putting out a bit of our personality into those accounts. So we spend, every tweet you write is a bit of humanity that goes into that tweet that represents you. And we build those up in our social network accounts. And some people spend a lot of time on that kind of thing. Even if you're not into social networks big time, we still have digital identity in the non-Web3 world. We have things like government IDs and driver's licenses and all that kind of stuff. So, yeah, it's our real-world human identity is reflected in those digital sources. So that's what we try and build on. But we need to recognize that those digital sources also are vulnerable to Sybil attacks. So we need to, filter out the bots and kick them out. So they're the kinds of things we're trying to do with Interep. Now, let's take a look at what the Interep Lego block looks like in an application. We have everything rooted in the blockchain. Interep is the Lego block on top of that provides the identity module. And the Lego block on top of that is Semaphore, and your application hooks into Semaphore, and with all of that we get the identity layer in Interep, we get the privacy layer in Semaphore, and we get the blockchain providing all the guarantees. Interep will integrate with those identity sources, like our social media accounts and those kinds of things. Now, Semaphore relies on the idea of groups. You form pre-existing groups, and the Semaphore application will use those identities in those groups to verify the kinds of things that your application is doing. So Semaphore is a privacy layer. So those groups, the group membership is guaranteed, but never revealed. It's never revealed what the underlying Ethereum account is. So, so we'll talk a bit more about the details of that a bit later, but that's an idea of what your application stack is. It's really just a bunch of Lego bricks all plugged together. The kinds of identity providers we've been linking with so far are these examples, Twitter and Reddit and GitHub. So what we'll do is an OAuth verification on your Twitter account, for instance, and using that we'll link it with an Ethereum account and never reveal that link, but we maintain that link, that Twitter handle is always reflected in that Ethereum account. And it's easy for us to add new providers. It's really it's an OAuth verification and some rules about what's a qualified account, or what does it look like a bot, does it not? Does it look like a human? We can also integrate with other providers. We could use email as an identity source. And this is useful in some cases, not in others. Maybe it's not so useful for Gmail accounts, but even Gmail has some barriers to entry. So, but if you've got like a .edu account, email account, then that's a fairly good guarantee that there's a human behind that account, and a reasonably good guarantee of uniqueness. So we can use those kinds of sources and integrate with those. Government authorities are good in that, the government makes sure you only have one driver's license, for instance, and there's a strong guarantee that there's a human behind that driver's license. So if we can integrate with those kinds of sources, and it also includes the people who don't use social media. So that's another approach we have. We can do things like curating groups of users, so that might rely on personal knowledge of the individuals involved. So that's also a strong way to guarantee humanity. Other ID projects, we can integrate with those, and we can integrate with on-chain sources, like use things like NFT ownership, that kind of thing. Now, a bit about Semaphore. So with those identity sources, we create a group. We put someone into a group. Now, Semaphore relies on these groups. Semaphore groups are membership sets, so there are guarantees of, once you're in that set, you're expected to be, anyone can expect that that identity to have a human behind it. And with Semaphore, it's a generic framework in which members in that membership set can signal on a topic, and that can be applied in multiple ways, but an easy to grasp example would be a DAO that has votes on proposals. In that situation, a signal is a vote, and the topic is a proposal, and Semaphore will guarantee that anyone who votes is a member of that group, and they can only vote once. And all of that is done with privacy, so you don't know who is voting on a particular, voting in a particular direction. So it can support secret votes, but it still maintains strong guarantees of membership in that set. So the Semaphore framework gets used in lots of ways, but the group membership part of Semaphore, plain vanilla Semaphore has its own group management, but what we do with Interep is Semaphore outsources the group management to Interep. And then that's Interep itself is basing its identity groups on, for instance, on Twitter membership and GitHub membership and so on. So the way that works is users will prove their membership on that in that social network identity source. So that will form a Twitter group, but we subdivide that into tiers, which basically represent a level of confidence that there is a human behind that ID. And as we know, Twitter is riddled with bots. So we will just apply rules to filter out those bots as best we can. We're not going to say it's perfect, but we'll get pretty close. Good enough for most applications. The way we do that, for instance, with Twitter, is we have some criteria that we apply ourselves. With Twitter, it's a fairly high bar to get in gold status. You'd need 7,000 followers. With 2,000 followers, you'd be silver. With less than that, you'd be bronze. But we also link to Botometer, and that will do an assessment of your Twitter account. And for most people, that's going to give us a score on how much Botometer, how confident they are that you are not a bot. So most people with a bit of history in their Twitter account and a few followers will be able to get in silver or gold just using that Botometer score. You can try, you can join a group and on our website and assess your own status there and see if you can get into one of those groups. The link will be in a later slide. But yeah, so the way we do it is we'll do that evaluation, give someone a score, and then assign them to that level, that tier, bronze, silver, or gold. So applications will be able to choose what level of confidence they require. Some applications will insist on a strong guarantee of humanity, but they're going to be working with a smaller pool of people who can qualify for that. So some applications will want a large pool of people to draw on, and they're not so concerned that we strongly guarantee humanity, as long as we do some filtering to kick out the bots. So that would be a bronze level. With Interep groups, because Interep is managing those groups, if you join a group, that group can be used across multiple applications. So you can join once and use it in many applications, and effectively you've got a sign-in that will be workable across multiple applications. And the advantage of doing that in a privacy setting is that we have a large privacy pool. So the nitty-gritty process of joining a group, the user will come to a sign-on screen. Sometimes it'll be a step just before they go in to use the application. Sometimes it can be done well beforehand. Someone can join a group and then they'll keep their identity and use that to kind of log in to work with the application. So whichever way that's done, first step is to prove the identity with the provider. That might be like Twitter OAuth or GitHub OAuth. Having done that, our application will do that assessment, assign the user to a tier, gold, silver, bronze, and then invite them to join that group. So the user will do their Twitter sign-on, say, okay, you're in Twitter Gold, would you like to join this group? They click that button, and then the next step is they link that with an Ethereum account. So the user will sign a message with their Ethereum account, which guarantees that they own that Ethereum account. It also prevents that account from being used again, so they can only join once, and the Twitter account likewise can only join once. So having made that link, we return a semaphore ID. The semaphore ID provides that guarantee that that Twitter handle is represented in that semaphore ID, and that can be used from there on in the application without revealing that link of who the actual Twitter user is behind that account. And neither is the Ethereum account revealed in the actual application because we're using semaphore IDs and it conceals that. We can also work with on-chain sources of proof of humanity, if you like. Some of those are pretty strong guarantees of humanity. And I'm thinking there of like Solburn tokens or POAPs, like the POAP you get from your Devcon 6, with your Devcon 6 ticket. That can only be owned by a human, right? Because they're only giving out tickets for humans. So that's a pretty good indication that that account has a human behind it. It's certainly very hard to, very resistant to Sybil attacks. So we take a slightly different approach with on-chain groups behind the scenes, but they end up as a semaphore ID and work the same way in your application. So, the kind of applications we work with that we have in mind for Interep are private voting. I talked a bit about this before. Membership of DAO, for instance, and we can guarantee membership, guarantee that there's a human behind that a human in that group, but never reveal who that human is. Social networking, we think, is a promising way to apply this. And some of our sister projects in privacy and scaling group are working on this. You'll hear some talks in Devcon about that. But yeah, that's another place where privacy is important, but also humanity. Proof of humanity is very important. We have anti-spam applications like the rate limiting nullifier, another one of our sister projects. We can do things like fair airdrops and Sybil resistant faucets. So if you want to put some anti-Sybil properties into an airdrop or a faucet, Interep can do that kind of thing. So to close, we think a pragmatic approach to identity, building on our history that we all work on in our existing digital lives, taking a pragmatic approach to use that, bring it across to Ethereum. We can build up, we have an existing source of identity that we can build on. We don't need to build it from the ground up. We don't need to discard those relationships we have in our social networks. But we don't want to bring along the surveillance opportunities, the opportunities for misuse and abuse, and we can build applications that respect personal privacy. So our Ethereum accounts can be used for more than just financial transactions. We can start to extend it into the social realm, bring along our social relationships, give them a human context, and make our accounts more credibly human, and our applications in the Web3 world. So the links, that QR code is to our Discord. You're welcome to come there and ask questions and find out more. You're also welcome to come and hit me up. I'll be hanging around a lot at the temporary autonomous zone down on the ground floor, which is the PSE's little hub. You're welcome to visit the application, interep.link, and you can sign on there, get yourself signed up with a semaphore ID, see what your Twitter status is. Maybe you have to work on that. We've got documentation links. We've got our code open source. You'll find all that on the on those links. But yeah, please come to the Discord and ask questions or come and ask me in person. So thanks for all that. The QR code on this slide is the Discord for privacy and scaling. We do lots of cool applications in the zero knowledge space. So you can join that Discord and ask questions. Check out our job openings if you like building cool applications for privacy and scaling, and check that out. And on that note, thank you.
Hold me here. Don't let go. Hold me here.
Thank you so much, Jeff. I think anything that makes a more civil resistant network and is probably something that I really appreciate after spending so much time at GetCoin and working with GetCoin grants. One piece of information, if you are ever asked for a grant or are looking for a grant, the EF is having Grantee Day downstairs on the first floor, I believe, in workshop room 2, or actually second floor in workshop room 1. So if you're interested in getting a grant from the EF, it's going to be all day down there. You might want to go ahead and check it out. All right. Next up, we have Andrew. And Andrew works at Give Directly on part of their innovation team. And he will be talking about lessons from the field, threats modeling for everyday use of digital currency.
High above, got me so in love for us to get around the sun. Oh, high above, got me so in love for us to get around the sun. Oh,
All right, everyone, please welcome to the stage Andrew Vaziri. Andrew works at Give Directly's innovation team. His presentation today will be Lessons from the Field, Threat Modeling for Everyday Use of Digital Currency. Welcome, Andrew.
All right. Thank you for that great introduction. Good morning, Bogotá. Okay, we got a couple. I think we can do better than that. I mean, we are at a really high elevation, and this is the highest conference room. So as an excuse, you are the participants at the conference with the least oxygen right now. Good morning, Bogotá. Awesome, but that's a little too much. Okay, don't get too excited. I wasn't kidding about the oxygen. There is a sensor there that's literally measuring the CO2 in this room. If you get too excited, we might suffocate. I'm Andrew Vaziri. I work at Give Directly. I'm on the innovation team. And this is the presentation Lessons from the Field, Threat Modeling for the Everyday Use of Digital Currency. Before we talk about the presentation, though, I want to take a step back and ask, why are we here at DevCon? This was the topic that was first brought up yesterday at the kickoff on this stage. Why South America? Why Bogotá? Because Ethereum is for everyone. It's not just for financial capitals. It's not just for the most comfortable, developed places. It's for people who are still in places where they might not have financial inclusion. There might be more corruption. There might be more censorship. And those are the people who really have the most to gain from using Ethereum. Give Directly sends cash directly to people in poverty, the kind of people who are in those settings. We've reached over 1 million recipients. We've raised nearly $1 billion. We work in more than a dozen countries. And we've had some of the greatest partnerships that you can in the development and aid space. And that has really been made possible by our approach. Giving people cash is really simple, right? If you want to financially include someone, financially include them. I think this really brings me back to yesterday's talk about subtraction, about keeping things, working very hard to keep things simple and effective. It's really easy in charity to say, we're going to get the best experts, we're going to decide exactly what people need. And I think it's a little bit more respectful, and in fact, it's been proven to be more effective to give them cash because they know what they actually need. So let's talk a little bit about our approach. And at Give Directly, our approach always starts with recipients first. So what does a recipient look like? This is Liz Auma. She's from Kibera, Kenya, and that's her house on the left. So this house, you can see it's very modest. It's made out of a whole bunch of different materials, whatever she had on hand. It probably doesn't have a door that locks. It probably doesn't have windows that close. But Liz does have some access to technology. Specifically, she might have what's called a feature phone. If you're old enough, you might have had one. Maybe you skipped that. You went right to smartphones. But this is a very simple phone. You can make calls. You can send SMS. And you can use USSD. Now, that third one might be less familiar. This is when you can go through a series of menus where the app is being served on the other end by your telco. So you could go through those menus and you could see how much airtime you have left, top up, basic things. So in her setting, she might not have reliable access to electricity. It truly does make sense for her to have a phone like a feature phone that can last for many days without being recharged. And we want to meet people where they are when we're trying to help them. And so when we look at our process, we have 4 steps, and each one of them is designed to meet the recipient in their environment. Target, enroll, transfer, monitor. So what is target? Targeting is, of course, to figure out who is in extreme poverty, who could benefit from this, or in some cases, if we're doing humanitarian work, who's been affected by the most recent flood, or what area needs some help to achieve equal rates of gender participation in education. So there are all sorts of criteria we could use to try to figure out where to send money, and that's the targeting step. The next step is enrollment. So this is very relevant for the talk that we've just heard. We need to verify people's identities. We need to make sure that they're real people, that we're not just sending money to some account somewhere which was set up for the purposes of fraud. And we need to be in person. There's no such thing as a free lunch. I think everybody is skeptical if somebody came to you and said, I'm going to give you what is more than a year's worth of your salary tomorrow for free. You wouldn't believe them. It has to be a scam. There has to be a catch. And so it's really important, actually, that we go there and we can talk with people, we can build rapport with them, and they can hear about other villages nearby, other people who've already gone through this process, and they can know that this is truly unconditional cash. It will be theirs. They can do whatever they want with it. The next step is transfer. Presently, these transfers use centralized digital currency systems. These are mobile money systems that are operated by telcos. These are very popular in Africa and Kenya. Over 90% of households use M-Pesa, which is Safaricom's mobile money. These sorts of systems truly are the best systems that we have at the present day. It would not be sensible to give somebody literal cash, although it would be more private and more decentralized. Their house doesn't have locks. You know, that would expose them to a lot of risk and danger. And finally, we have monitor. So we follow up, we make sure everybody was able to receive their cash, that they were not threatened, they weren't bribed, nothing bad happened to them because of it, and that they continue to understand how to use their phone, how to use it safely, securely, to protect their PIN code, etc. So let's talk a little bit in more detail about fraud prevention, and then we can talk about how we might reimagine the system with Web3. So GiveDirectly lost $241,000 in 2021, and that's about what we would expect. Now that's a lot of money, but at the same time, because GiveDirectly operates at such a large scale, that's only 0.2% of the funds. And you can see on this chart here that 2021 and 2020 were relatively similar. And you can see that we have a breakdown of the types of fraud that we discovered. The first is theft. Makes sense. Somebody coerced a person to give them their money, or perhaps tricked them, lied to them, tricked them into revealing their PIN code. The next is imposters. This would be people who should not be eligible for a program. Perhaps they are assuming a false identity, or they've pretended to move into a place where they don't actually live. And the final are bribes, people who have asked for payment for some sort of favor, which is not appropriate, which is an abuse of their power. So the rest of the presentation, I'll talk more about theft and bribes. While imposters are important, I think theft and bribes affect individual people directly, and that's, of course, makes them even more important. So some of our measures that we take. We have our standard approach, which we've already talked about. We're going to give them training when we first meet with them. There's a hotline where they can call us. We do follow-ups to make sure everything went well. Additionally, there's a recipient advocacy team. So this is an entire team that's firewalled from the day-to-day work, the people who are doing targeting, operations, etc. Those people don't even know who the recipient advocacy team are, and that allows us to do audits. We audit that nobody on our team asked somebody for a favor in order to be included with a program. And finally, we'll do risk assessments. So sometimes in a certain setting, it's actually quite sensitive, and so we'll take additional actions. We'll randomize when we send people to the field. If we know that our field officers are being tailed by scammers or people who are trying to take advantage, we'll make it as hard as possible for them to figure out who was in our program. Additionally, we'll conceal who's being enrolled, and we'll stagger payments. If we pay everybody at once, they all go to the market at once. It's very obvious that XYZ village was the village that most recently received their payments from GiveDirectly. So that was an interesting system, but I think we can make it a lot better. And to that end, let's talk about what GiveDirectly currently does. Splitting that into two categories, funds in. We've received crypto donations since 2014. We've been very happy to receive more than $50 million in direct crypto donations, and I think that speaks to how well our visions are aligned. GiveDirectly and Ethereum are both focused on financial inclusion. They both are focused on empowering and respecting individual people and their privacy. And for that reason, I'm very happy to be able to speak here today. In terms of funds out, we're still working on piloting these programs, but it's been surprisingly an interesting learning for me this year that I always assumed it would be really painful to use cryptocurrency. You know, it's so much easier if you have a smartphone. If you're in a setting where you don't have a lot of technical expertise, you only have a feature phone, I would have expected it to be quite difficult. But in our initial pilots, it's second nature. If you can make the product feel like what they've used before, feel like mobile money, then suddenly everything makes sense by analogy. And in fact, there were very few questions about how it worked and more questions about what are the fees, what are the exact details of the financial incentives here. So in the interest of time, I won't go through the centralized versus decentralized. I think people in this audience probably know that there's a lot of value to be had by a more decentralized system. What are the privacy threats that we see? And specifically, what would be happening in a naive implementation with a public ledger? Contrast, presently, we're using centralized systems, so they have some degree of privacy as long as nobody leaks the information. It's not published anywhere. And we would imagine in a public ledger, some of these types of adverse events might become more common. Maybe the first thing to say is that while in a naive implementation, people are anonymized, they just have a wallet address, that's probably not going to be enough. The first time you transact with somebody in an everyday setting, you've paid them for a good or service, they've gone to a store that has a known wallet address, it's very easy to quickly de-anonymize everybody in your local community. So thinking about that, theft becomes very easy. If you're sitting outside of a store and you wait for somebody to walk in and you're refreshing the blockchain on that store's address, you could see the most recent transaction, you could see the balance of that person, and you could say, it's worth it for me to take the risk to mug this person because I know that they have enough money that I will potentially benefit. Bribery, similarly, people pay legitimate fees all the time. Once they've paid that fee, if you can look at their balance, you can know exactly how much you can extort them, or they'll be able to pay. Phishing. You'll see I'm not wearing any Give Directly clothing. In fact, there doesn't exist any. We're very serious about preventing phishing, and just showing up in a village wearing Give Directly clothing is enough to let you social engineer much more than would be safe for our recipients. And if you imagine what somebody could do with a public ledger, they would be calling somebody who had been in a Give Directly program. That person has already been sensitized to expect a call because Give Directly follows up. They would speak to that person and say, hey, I know that we've given you a transfer in exactly this amount at exactly this date. I see you bought a sandwich yesterday that was $1.50. Was that you? Great. Let me secure your account. Please open up your app. I will need your seed phrase. And suddenly, they've lost all their money. The next category is scams. Of course, scammers are always trying to find the people who are the most vulnerable, who don't have people who can intervene and say, wait, this doesn't sound right. So they're looking for people who are elderly, people who are illiterate, people who are going to be more likely to be scammed. And we don't want to make that any easier for them. We don't want them to be able to cross-reference. These are all the elderly people, and these are their account balances in this village, and therefore we'll target so-and-so. And finally, maybe the most hard to pin down is social pressure. It's supposed to be unconditional cash. It's supposed to allow people to make decisions for themselves. And if that decision is, for example, to send your daughter to school, that might not be the norm in the place that you live. And it's very important for that person to be able to make that decision for themselves and for their family without people giving them undue scrutiny. So of course there are mitigations for this. That was all assuming a naive implementation. You might have heard of Aztec, that's layer 2 focused on privacy, and they have many of these features. Balance and transaction privacy. It's enabled by default. For example, if I told somebody, hey, there's a way to be private, you're going to go use this smart contract called a tumbler. You're going to add to that tumbler in one amount, and when you subtract, you'll subtract in a different amount, and each time you subtract, you're going to make a new wallet address. Now, if you understood that, you are probably afflicted with a terrible disease. You're probably a developer. And I'm sorry to say it's terminal. Okay, maybe that joke wasn't that good. Okay. But for normal people, that's like way too much. Okay, they're not going to be able to do that. You need something that's more akin to Venmo. You can easily swap between private and public, and you can be given a little warning that prompts you, hey, this is public, people will read it in the future, do you understand those implications? And finally, the fees need to be reasonable. In a setting where you spend in your entire day less than $2.15 to feed and house and everything, even a fee that's 5 cents kind of precludes you from doing stuff on an everyday basis. You know, you buy 3 meals, you've spent 15 cents, you're getting close to spending 10 or 20% of your daily budget just on fees. So going to extremely, extremely low fees can be important. And given that privacy features generally require more gas, more transaction fees, you know, this is a challenge, and luckily there are a lot of solutions on the roadmap to help with those scaling issues. Okay. So if we assume that we exist in this private L2 in a future state, maybe post-surge, where the fees are low, we still need to think about how do we actualize this? How do we bring it into the real world and have people comfortable with it existing in their country? And I think it's important to think about in this hybrid model where there are real world activities, but there's also blockchain underlying the mechanisms, that we can have censorship resistance as a feature, but we can't have it as a strategy. And what do I mean by that? I often hear proposals of people who may not be thinking about the recipients or people in extreme poverty, and they say something like, oh, okay, if people don't like this, we'll go the permissionless route. Just try to ban us. Just try to stop us. You can't really, it's decentralized. So that works if you're only making a financial product and you're okay with operating in a hidden manner. But the moment that you think about a hybrid method where you actually need to go out and meet people and build rapport and you need to follow up with them, all those activities become impossible with that approach. Now, what's a good example of censorship resistance? You might be in a refugee camp, and refugees are, of course, in a very precarious situation. They may be rehoused, moved somewhere else. Depending on political changes, they might be supported in one regime and not the next. And so it is really important in those cases that we have something which is really owned by the people themselves. So if they're changed, if they move somewhere else, if they go to a place where a different telco operates, all their funds and their livelihood isn't tied up in mobile money. It's something that they can continue to have access to. So if we assume that we have cryptography and we are going to try to work with governments and have this be a force for good government, we are going to need a couple more features. So selective disclosure would allow us to continue to have the kinds of systems and institutions in place that democratic societies often create. So I'm talking about having legal recourse, having regulations, even taxation. And I know that's not a really popular subject, but I just want to imagine for a moment, if somebody was interacting with you in a truly fully private system, and they claim they pay you, and you claim they never paid you, and you sue each other, and you go to court, and you're in discovery. Ideally, you should be able to say to the person who said that they paid, prove that I paid, and they should be able to do that without exposing their public key, or their private key rather, without giving you access to their funds. They should just show you that one transaction. So that would be an example of how I think presently we have some solutions where there's a viewing key. You can see everything that ever happened associated with that account. That's probably a little bit invasive of privacy. And so I look forward to better ZK proofs where we can answer the specific legal question that's at hand for only as much information as needs to be communicated to resolve the issue. So takeaways from this talk. I hope you agree that Ethereum is for every person. And if we think about every person, the people who have the most to gain are the people in extreme poverty or in places where their institutions are really not functioning very well today. We have to think about each person as existing in their own ecosystem, right? They exist in a house that doesn't have locks. What does that mean for them? They exist in a place where their government is going to need to be a partner if we're going to help educate them and bring them services in real life. And finally, I would like to thank everybody for their work and remind you that today's EIP is tomorrow's family tree. That's kind of a lame rhyme, but it's the case that some of these really, I don't know, bland or seemingly at first glance, not very intriguing improvements actually fundamentally change how usable this technology is. So if you read the text of EIP 4844, You might not get it at first. If somebody explains it to you, it makes roll-ups less expensive. But thank you to Proto for providing me with this chart. How much less expensive? If you look at gas fees on Optimism, for example, the L1 data fees are like 97, 98% of the expense of each block. So if you can imagine that we create this EIP, we're going to suddenly be in a case where instead of paying 5 cents for every transaction, you're paying a fraction of a cent, and you can actually use it every day. And it's a 0-to-1 change. It's a step change that I'm very excited to see happen, hopefully in just a few months. So thank you again. I would encourage you to support all the relevant EIPs and, of course, the Surge. Reach out if you think we should work together. My Twitter is also just at my name. And if you're interested in donating to Give Directly, that QR code will direct you to all of our addresses. Thank you. We do have a few minutes. Yeah.
If you have questions, feel free to raise your hand, and one of the volunteers will hand you a mic, so we can go ahead and take some questions. There's a question right here in the front row. There's a question over there. Yeah, go ahead.
Thank you very much for this. I'm kind of impressed that you raised $50 million from philanthropists that are sort of handing over the decision-making of where the money goes. That's impressive. Do you have any kind of idea of who are the sorts of people that do this?
I think that a few of them are giving their donations under an anonymous circumstance. I mean, it's just a crypto wallet address. Anybody can send to it. But I know that Vitalik has been one of our top donors, and thank you to him.
Awesome. I know there's a question in the back.
Yeah.
And there's also a question over there.
Hi, man. Great job what you're doing, man. I just heard about your project and what you're doing. What's the landscape in Latin America like? What do you think about Latin America? Here we have so many problems that you describe, like crime, corruption, bravery, worst governments. It's really bad. And I see that you support a lot of African countries. So can you tell us about Latin America? If it's in your roadmap or not, or when?
Yeah, absolutely. Thank you. Great question. So we've done projects in many places throughout the world. Africa tends to be the primary source because many of our funders are looking for where's the place where the poverty is the most extreme, the most widespread, and so their dollar will go the furthest. Now, I don't think that precludes us from being other places, but it's a question of finding the funding of people who are specifically interested in seeing change in Latin America. And luckily, there are a lot of things on the horizon. I know that there are some US government and other international organizations that have recently proposed some more aid. So hopefully, Give Directly will be able to bring some of that to Latin America soon.
Awesome. I believe there's a question over there, too, with the gentleman in the black shirt.
Thank you. Hey, GM, amazing presentation. Thank you for that. I'm Russ, founder of 40 Acres DAO and Chief Vibe Officer. And we kind of echo a lot of the same sentiments that you talked about today, really through trying to create self-sustaining communities of color utilizing blockchain technology. As we've seen, the biggest hurdle has been just this convoluted language and vernacular in which we use every day that makes sense to us, but for other people just goes over their head. Liquidity pools, yield farming, AMMs. So we've been trying to aggregate all that information through education, empowerment, and engagement. And so the question you guys have been doing beautiful work raising $50 million. And so as far as allocation goes, do you guys focus on protocols? Is that something you've been thinking through, helping aggregate it to certain communities versus just individuals themselves?
Thank you, great question. So right now we're at the prototyping stage. So our funds presently are used to test delivering cryptocurrency directly to recipients. And I think that we obviously want to have that kind of killer app. that says, why did it make more sense to do this on a general purpose blockchain? And that goes back to, I think, at the beginning of this event, they spoke a little bit about the overemphasis on financialization, right? That there should be non-financial apps. And I think that that's an incredibly important point to show that this isn't just an alternative to mobile money, but this is actually something new and different. This is infrastructure. This is part of a functional society. So I don't have a particular protocol that I can say today. We're kind of proving that first step, which is it's at least as good as mobile money. And once we have that information, hopefully the ecosystem will have a lot of great partners that we can start proving why it's beyond present day solutions. I know that we have just run out of time, but thank you again. I'll be off to the side after the talk, and I'll be with you at dinner once you invite me there.
Thank you so much, Andrew, for your talk. I think it was so important to remember the human aspect behind blockchain. Up next, we're going to have Guillaume Ballet, but you have 5 minutes between that and this next transition. I do want to give you all a reminder that if you're a grantee or a grant person who's looking for a grant, the EF is having Grantee Day, and it's going to be down on the workshop room number 1 on the 2nd floor, and it'll be all day today. We'll conclude with our next talk in about 5 minutes.
Keep me by your side. We're running through the fire. Save me from my mind when I can't sleep at night. Keep me by your side. We're running through the fire.
Oh yeah, oh yeah. It's been interesting. Yeah. It's been an interesting time. That's the only safety I've had is like that everybody has been having the same type of conversations. Yes. Yeah, what else do you
I'll be falling down, you'll be watching by my side, by my side. I just need a helping hand, I just need you in my life, in my life. Clouds keep driving by, baby, please just call me back. You keep moving my mind, feeling so inside, yeah, inside. Falling into pieces, I'm so alone. Falling into pieces, I'm so alone.
All right, good morning, everybody. Again, my name is Gloria Kambwala. I'm part of the BuildAbox team under Supermodular. I'll be your MC for this morning, and I apologize, not really, for being super high energy. That's just how I am. I'm going to go ahead and introduce to you Guillaume. Guillaume is going to be our next presenter. It's Guillaume Baillet from the Geth team. And Guillaume is talking about stateless Ethereum, how Verkle Trees make Ethereum lean and mean. Guillaume is on the Geth team. He's interfacing between research and engineering, and he's interested in the evolution of the Ethereum protocol. I'll go ahead and hand it over to you, Guillaume. Yeah, you're welcome.
Hi. Yeah, excellent. So, I'm going to talk about Verkle Trees. I've been making a few presentations about those already, but they tended to be a bit too deep, technically speaking. So, because this is Devcon and we're trying to onboard more people, this one is going to be a bit more high level, so hopefully enough to raise your interest in Verkle Trees. Why are we considering Verkle Trees? It's basically a big change in the way Ethereum functions. So why do we want to risk this? Well, there are several reasons. The first one is we want to be able to build blocks as self-contained execution units. So at the moment, Ethereum has a bit of a problem. That when you want to join the network, or if you haven't followed the network for a while, you need to go through a process that's called a synchronization. You cannot access the state directly. It's like you cannot just download the state. I mean, you can download the state, but it's a fairly convoluted process. So the idea is that if you include in the block everything that you need, you can just download the block and execute it and see if you're interested. Like even before you execute the block, you can even know if it's going to be of interest to you or not. And if it's of interest to you, you can execute it. Otherwise, you don't even have to care. So it's something that it's to build something that is in between a full client and like a full node and a light client, in the sense that you are still supposed to follow blocks, but you don't have to hold the entire state. And it's nice because it paves the way for other upgrades, or it makes other upgrades a bit simpler. For example, if you want to shuffle committees between shards in the future. You don't want shards to shard validators to keep following the chain at all times, like several chains at all time. So it's something that's going to help them get up to speed a bit faster. And of course, there's the idea of state expiry. Like the state of Ethereum is quite large. So we want to be able to delete some of the state, but we don't want to delete and forget forever. If your state has been deleted, but you want to use it again, you need to provide a proof to resurrect your state. And the idea is that Verkle Trees make your proofs smaller, so it will be cheaper for you to resurrect the state. So because it's a fairly like deeply technical topic, I have tried to make a simpler explanation with pirates. So imagine you have 4 pirates, and they bury a treasure somewhere, and they plot the directions to get to the treasure on the map, and then they want to go their separate ways. So if they adopt the method, like the metaphorical method that we currently use in the Ethereum to store the Ethereum state, what they would do is they would split the map in 4 bits, and then each of the pirates would get their own bit. And when they want to access the treasure, they need to put all the pieces of the map together. The problem is inheritance. If one of the pirates wants to retire and, for example, wants to sell you his bit of the map, how do you know he's not selling you a fake map, a fake piece of the map? He's a pirate after all, so you should be careful. Well, the problem with this, the method that was chosen, is that to figure that out, you need at least the other two pirates to check that the pattern matches. So the proof size is quite involved. It requires you to take the siblings, the sibling pieces. Now, if we use the proving technique that is suggested by Verkle Trees, which is called it's based on something called vector commitments, hence the name Verkle. What you do is you cut out something at the center, some little stub, and you make this little stub as hard to reproduce as possible, ideally cryptographically impossible to fake. And then everybody goes their separate ways. And when you want to buy your part of the map, all you have to do is make sure that your piece fits into that proof, that little stub. So of course we don't use pieces of paper. We use cryptography, stronger cryptography than this. And now this is your proof size. And so how do you transpose this to Verkle Trees? Well, the current Ethereum state is stored in a tree where all the data of Ethereum is at the bottom of the tree. And then you group them. The parent is a commitment. The parent node is a commitment. And then the parent of that parent is also a commitment all the way to the top. And the root of the tree is ending up in the block. So if you want to prove in the tree, for example, the purple square here, if you use the current method, it's the same thing as with the pirates. For each level, you have to pass the siblings. And here, this is a very simple representation. But in Ethereum, each parent node has 16 children. And the consequence of this is that you need to pass 15 other values for each value at each level for each value you want to prove. So there are thousands of values that get touched per block. That's 1,000 times 15 values per level. And if I remember correctly, the average depth of the MPT is between 10 and 15. I don't remember exactly. So that's a lot of data. That's roughly, if you want to pass that data in a block, that's 3 megabytes. We are in Bitcoin territory. So yeah, it's a bit too big to pass around the network in a reasonable time. If you use the Verkle commitment, so you have the equivalent, like you still have the, oops, that doesn't, yes. You have the little cryptographic proof, but all you have to pass as your proof is the nodes along the way to your value. And that is much smaller, first of all, because you don't pass the siblings. But on top of that, because you don't pass the siblings, there's a virtual cycle that allows you to widen the tree. You can have more children per tree and per node. And as a result, the tree gets shallower. So your path is even smaller, even shorter. And as a result, your proof is that much smaller. So unfortunately, it's not that simple. There's quite a few changes to introduce at the same time. Like the first one is putting the proofs in the block. That's the whole point. But we also need to change the tree structure. And I'm not going to get too deep into the details because, once again, it's quite involved. There's an EIP. There are other talks about it. Look them up if you're interested. But the idea is that all the data ends up in a single tree. So currently, accounts have their own tree, and for each account, you have another tree that encodes the storage for this account. Well, here, everything is kind of hashed or mixed together and spread over the tree. Each item, like each account item, for example, the balance, the nonce, the code, any slot, like for example, if you're thinking of CryptoKitty, each cat is accessed independently because we don't want to add more to the proof that is required. So if I'm sending funds to a new address, well, I just need the address, the target address balance. I don't need to know how much code they have. I'm only interested in the funds. Right, and like I was saying, the data is spread all over the tree, but we are trying to group things that belong together a little bit so that you don't spend your time jumping all over the tree all the time. So it's grouped in batches of 256, and I'm going to go over that in just a bit. So this is a picture that comes from the EIP itself. I'm going to describe. On the left side, you've got what's called the stem tree, and it's basically the top of the tree, so the tree is flipped to the side, is rotated 90 degrees to the left. And the root, the stem tree only has branch nodes, so that means every node in that tree has at least 2 children. When you take your key and you follow the path traced by the key, at some point you will reach a moment where there's only one group, that is a group of 256, that is pointed at by this key. So there's this intermediate, like what's called an extension. Yeah, I don't quite see the pointer here, sorry. But the blue box, that extension says this is the prefix, the 31-byte prefix that every key below me are keyed by. So that means that when you go through the tree and you have to compare the key that you're using with the encoding, the key encoded in that blue box, and if it's the same, that means your data is in the group below it. Otherwise, your data is not present in the tree. And then there's the suffix tree, so that corresponds to the 256 values. And there's a fourth column that we're not going to cover. It's not really important for this talk. So, like I said, every piece of data is broken into chunks. That means, for example, the code is broken into bits, into 31-byte pieces that are fitted in a 32-byte piece. The storage slots also have their own data. The balance has its own value. And each of these values, each of these chunks is given an offset. And for example, the balance is always at offset 1, the nonce at offset 2. And then a bit further, you have the beginning of where the code is supposed to start. And then even further, you have the bit where all the data slots are supposed to be. And the way you find them in the tree is you take the address of, so you have a key that is made of two parts. The 31st bytes are called the stem, and the suffix, it's just a byte that indexes in the group that we saw before. I'm talking about the third column here. So the last byte is the index in there. Oops, sorry. And so to build the stem, what you do is you take the address of the account and you take the first 31 bytes of the offset of that chunk, and you hash them using what's called a Petersen hash. So it's like Ketchak, but it's much more friendly for ZK applications, and it's also much slower. But you get a 32-byte values. You take the 31st bytes of this value, and that gives you the stem. And the way you use it, when you compare it to the tree, the stem will give you the path through the stem tree and the extension. And when you found that, you use the suffix to select the value in the group. So, like I said, just a recap. Verkle trees are nice because you can make the tree much larger, much smaller, much more shallow, sorry. You can also experiment with ideas, like you could think, so I know that this is very interesting to dApp developers. You can just download the blockchain, not care about the state, and when you look at the proof in the block at the witness, you can figure out if if that block is accessing something you're interested in. So, for example, if you're CryptoKitty, you want to see if the CryptoKitty contract is accessed. If so, you just execute that block to update your internal state. If not, you don't care. And that was just a recap for the rest of the slide. So, what is the current state of Verkle Tree implementations? We have 1.5 running testnets. We have one testnet that is fully working. It's a proof of work testnet called Condrieu. I'll give the address at the end. And so, proof in blocks. It works. It's been working for a while. And then there's a proof of stake testnet that is currently in bring up phase. So unfortunately, I wasn't able to get it to work for Devcon, but it's going to happen shortly. When we do performance, we currently have performance testing. We see that it's currently 5 times slower than regular mainnet. So when we replay blocks from mainnet on a translated Verkle tree layer, it's 5 times slower. We took it down. It used to be 40x, so it's a bit faster already. We have another avenue to make it faster, but I mean, in my opinion, it's always going to be a bit slower than the current method, but it offers some opportunities to build interesting applications. So I think it's worth it. And there are like 3 implementations. And there's a 4th one ongoing with Besu. So I don't know if it's quite readable, but I wanted to give an example of what you can do with Verkle Trees. So there's a block explorer on that testnet, on the running testnet. And there's a piece of software that is able to read the block and reconstruct a view of the network, of the tree, that is everything you know to re-execute the block on top of it. So I don't know if it's quite visible. I still don't see the pointer, but basically you can see that the leftmost branch here is an account. The next branch, the right of it is another account. I mean, I can tell because of the way the last level looks like. And you have the other 2 branches from the root. These do not have a very deep tree, and that's because this is a proof of absence. So that means this is the way you signal that those branches, those locations did not exist before the execution of the block. And what definitely happened here is that those 2 accounts on the left probably sent funds to those 2 accounts on the right that did not exist yet, and that they will exist after the execution of the block. So it's quite interesting because you can see what's going on, you can visualize it this way without loading the whole tree. Right, so this is the current state. What are the challenges we still have to overcome? One of them is the transition. Converting a Merkle tree to a Verkle tree is no walk in the park. It requires a lot of RAM, it requires a lot of disk space, it's quite difficult. So there are 2 methods, really 2 avenues to do this translation. Either you entrust the conversion to very powerful machines. I have a test machine that is a Xeon. It takes 6 days. I know Erigan is able to do it in like less than a day, but even for Erigan, it's not instant. Where was I? Yes. So that's the first avenue. The second avenue we have to do the translation is simply to pace it to the slowest machine on the network. So that would be to do a translation of, let's say, 5, 10, 100 values per block. But this would last for a month. But then every node on the network would theoretically be able to follow. So these methods have names. The one where like you follow the pace of the network, it's called the overlay tree. The other one was called offline conversion. There's a third one that is known as the roll-up appreciation week, where you just do nothing for a week or a month, and you wait for everybody to be done translating. That's, it's just here because it's a cool name. No one's really considering that. Yeah, one last thing I wanted to say about this slide is pre-images. So most clients, including Geth, do not encode the addresses directly. They just write the hash of those addresses. So to do the translation, and because we use a different hash system, we need the pre-images. It turns out that most clients do not store that. Well, Erigon does, but the rest of them don't. So pre-image availability is another problem that needs to be addressed, and it's not an easy one. Another thing is the slower cryptographic primitives. It's not as fast as Ketchak. So this is one of the latest runs. And you can see that roughly 30%, 33%, 35% is spent just doing elliptic curve operations. So cryptographic primitives is really where the effort needs to be, the optimization effort needs to be made. So either by writing faster crypto or by not calling those functions as much. So caching, for example, is a technique that has worked well. Yeah, there's a slide on database design. So basically the idea is that most clients have optimized their database layout and their database access layer for the current MPT. A lot of those assumptions are no longer valid, let alone helpful with Verkle Trees. So there will be some need to adapt to something that is a bit close to what Erigon is doing, but that will take time, unfortunately. And I wanted to finish on on what you can do if you want to help. The first thing would be, there are test nets. So the first thing you can do is just try to deploy your contracts on the test net and see if that works. You can also try to run your own client, like hashtag testing the Verge. You can also modify a CL client to figure out how to propagate the proofs, because currently it hasn't been defined. So it would be interesting to run a fact-finding mission, finding out where and how the proofs need to be propagated in a proof-of-stake world. Like I said, crypto is the bottleneck. So if you can find a better cryptographic primitive than what we have, that would be also quite helpful. It's also going to affect layer 2 solutions. Like presumably, layer 2 groups don't really want to diverge too much from the main net. So they will need to adapt as well. There's not a clear path for that yet. Like I said, pre-images are also a problem. So if you have a way to make pre-images available to everyone, that's a very good test, very useful. And then you can go crazy. You can try to prototype the interaction of Verkle Tree with the Portal network, try to implement state expiry using Verkle Trees, all of that. All of that is greenfield, but it's also quite interesting to get some information, some ideas of what is to come. And with this, that's pretty much it. I have put the addresses of the 2 test nets, knowing that the second one is still in a bring-up phase, so it will probably not work today. But the other one is the landing page for the proof of work testnet, and this one works, or should work. You can look at the Explorer. You can send transaction. You can try everything, and that's it. Thank you.
Thank you so much, Guillaume. Guillaume, do you mind taking a minute to answer our questions? Sure. If you do have any questions for Guillaume, go ahead and raise your hand, and one of the volunteers will actually come towards you. There's a question right there. Let's see. In the 4th row or 5th row with the black sweatshirt.
You mentioned accessing data is going to be a little bit different. Does this imply that tooling teams and wallets and such now are going to have to like enforce access lists now moving forward?
No, it doesn't mean that, but it means that the gas model is going to change to follow this new model, which is why I was like, if you've got a contract, please deploy it on the testnet. But you do not need, access lists are going to disappear. They're replaced by something else that is not really exposed to the user. So for the end user, in theory, apart from the gas cost, everything will be transparent.
I think that answers the question. Thank you so much, Guillaume.
Okay. Thank you.
Appreciate it.
Yeah.
I'm going to take your mic.
Yep.
Oh, there's one more question. Do you mind answering one more? Sure. Sorry. There's a question right here. Can I repeat the question real quick?
Oh, sure.
I'm just going to paraphrase it real quick. And they said that they wanted to know if there's any drawbacks to the Verkle Trees.
Yes, there's plenty of drawbacks. Like I said, there's the transition, the slow crypto. Otherwise, yes, like the biggest drawback I only alluded to in the previous answer, it's that the gas model changes. And that means that a lot of code, some contracts tend to be very optimized for gas. Those optimization can turn out to be completely obsolete and counterproductive. So that, I would say that's the biggest drawback I can think of.
Awesome. If you have any other questions for Guillaume, I'm sure you'll be over to the side.
Yep,
Feel free to ask
absolutely.
him after the talk, too.
Thank you.
Awesome. Thank you. We're going to take a couple minutes to transition to our next speaker, but I have a few questions for the crowd. So while we transition, I would love to know is this anyone's first time at Devcon? Have anyone? Yeah? Okay, welcome, enjoy. I hope you enjoy it. As an OG and someone who's gone to a couple of these events, I will just say pace yourself. Try to go to as many things as you enjoy, but try to make as many connections as possible too. That's what is always the best. And you can always rewatch these talks afterwards as well. Perfect. Let's get set up. All right, everyone. All right, next up we're going to have David Theodore. David Theodore is a security researcher at the Ethereum Foundation, and his talk is going to be Noisy Neighbor, an automated fuzz harness generation for Golang projects. I'll go ahead and give it to you, David.
Test. All right, the room cleared out, so I'm gonna have an easy audience right now. Yeah, so I'm David. Last time I saw you guys, I was in better shape. I'm surprised I made it here. More on that later. I'm gonna talk about Nosy Neighbor. Nosy Neighbor is a tool I've been working on open sourcing for everyone to use, hoping it makes some waves in the Golang community. Talk a little bit about the challenge, finding bugs in open source Go projects, and a little bit of the motivation. So Ethereum really loves Go. Some stats here. Geth accounts for 82% of execution clients. 42% of the consensus layer clients are running Prism, and this is as of like last week. These metrics actually used to be higher, like 90 plus on the execution side and like 60, 70 plus on the CL. Mev Boost is also written in Go. It's the only production open source Mev client for Flashbots right now. As of like, I think last week, 48% of blocks on mainnet were Flash blocks. So I won't go into Mev and all that fun stuff, but what I'm trying to kind of hit home here is that Go is like critical in the Ethereum stack. So somewhere I would say like maybe 3/4 of nodes or more are using Go at some point. So it's super important. Let's see, lots of code. Got to run 2 chains, the execution chain, the consensus chain. We've got the entire EVM, all kinds of stuff. So there's like a huge amount of code here. How big is it exactly? The pure Go Ethereum stack is 583,000 lines of code. So as a security researcher, like a deer in headlights, I'm not going to manual review all of that, right? We do manual reviews here. All of these things have been reviewed at least once, most likely, if not twice or more times. But they're moving targets. We've got every 6 months or so, we've got hard forks on both the EL and the CL. So it's just kind of something that if we can automate anything, we should automate finding issues here. So my task, there's a few of us at the Ethereum Foundation working on the consensus layer security research team. My task is to kind of like look right now and focus on the Go stuff. This is kind of a daunting thing. So a few months ago, I guess about a year ago, started looking at this and trying to understand the problems that we have. So I'll talk a little bit about it. First of all, Go is memory safe, which is awesome. We don't have remote code execution issues, stuff like that very often. The memory safety stuff helps also a lot in the, I'll talk more about it in this talk, but making it possible for me to make a tool like this. A lot of common mistakes in Go though. There's some that are queryable, right? There's a lot of these like little issues like the colon equals sign, this like quick variable assignment. It makes writing Go really easy and human friendly, but it also means like you can have these shadow variables where if you like declare a variable in a loop, you overwrite it and you might reference it later thinking you're talking about the first version of the variable. If you call a Go routine and you kick off like, which is basically like for non-Go people, it's like a pthread create under the hood. The variables that are passed to that are not the same variable that you might think they are. So if you have like racy type things later, you don't really know and Go doesn't complain. So we can query for certain things like this. This is a good example of like one query GoSec that just says like, hey, you need to manual review all these uses of unsafe. Probably not the best example, but we have CodeQL, SimGrep, and GoSec are like just major tools you can look up for like automating querying static analysis, right? Another big one is race conditions. So Go's, I think the reason it was designed and the design decisions they made was to make parallelization very easy. So they have like this concept of channels and they have this concept of Go routine. So it's very simple to be like, hey, just go on another thread, go do something, and then come back. And Google made it to be memory safe, but also efficient and human readable, but to process massively large data sets. And so we can do a lot of parallelization very easily, but the problem here is that it's so easy that it's really easy to introduce race conditions. So like one thing we have been doing is running these thread sanitizers. This little terminal prompt right here is an example of actually a mainnet geth bug, a race condition that was causing some memory corruption, which if you see memory corruption in Go, it's usually something race related, or you're using like CGO or some native library, because Go is relatively like almost 99, I would say, % safe if you're not in one of those conditions as far as memory goes. There's also some other sanitizers. There's ASAN, MSAN, UBSAN, things like this. We're running nodes on Robson, Sepolia, the Prater-Gurley testnet, and also on mainnet that have all these sanitizers running. So we're like, we've kind of automated, you know, this querying. We've automated like sanitizers running stuff, like using dynamic analysis. So we've kind of checked both of those boxes. But you know, what else can we do? And that is where Nosy Neighbor comes in. So how else can we cover these 583,000 lines of code? The solution. Let's talk a little bit about the problem. I'll rewind just a bit. Obviously, I already mentioned the huge attack surface. One thing I do want to point out here is that denial services are like critical for us, not just like for other Go repos necessarily, but a blockchain cannot have a denial of service. So usually a denial of service on the common vulnerability severity scale is like a 3. It's not like a 9. It's not considered critical. There's no information disclosure, there's no remote code execution, and thus there's not usually privilege escalation. So people aren't like lifting keys. But if you have, you know, more than 35% of the network running some kind of Go under the hood, and there's denial of services in those Go routines or these repos, then you end up in a problem where the Ethereum network could like be brought to its knees. We obviously have a multi-client architecture, so these other clients would be kind of like carrying the network during that time. But it's not something we want. We wouldn't have finality. For those of you that are like really familiar with proof of stake, it would be pretty big deal. So we kind of have this like weird issue where the worst kind of bugs we don't really see, but like we care a lot about these smaller bugs. The good, I mentioned RCE is rare. We have the source. This is really great. I've been a security researcher for a long time, and I've not had this source very often in my career. So this is like a whole new ball game. Go is strongly typed. All of the panics and stack traces and failure reporting is like excellent. So if you write a fuzzer and it finds a crash, it doesn't bring down your fuzzer and your fuzzer doesn't commit suicide. So that's really helpful. And I'm gonna talk a little bit about the tooling. This is a big deal. So Go 1.18, I guess like maybe 6 months ago, they released native fuzzing support. So this is an example of like in the testing library, I can fuzz this function. So the function on a test on the right side, and I lifted this straight from like the Go fuzzing, like native fuzzing design doc. Foo is the function under test here. So we can fuzz foo. We can say, hey, f.fuzz, give it a function interface. I say, I want an int and I want a string, which are the 2 argument types to foo. We can add a test corpus of like, right here it says 5 and hello. Anytime you want to like prevent like regression, you can add like previous bugs into your test corpus this way, and it will automatically tell you if the bug is reintroduced. So that's really cool. It's automatically coverage guided. All the test cases, when there is coverage, they get added to the test corpora and they get mutated on. Errors are super descriptive. Don't need health checkers because all this stuff is built in natively. It's awesome. This is kind of the next piece of the puzzle. Discovering this kind of like opened my eyes to the possibilities of what we could do here. The AST is exposed. The parser library and the Go types library expose everything about the source. So when the compiler reads your code and then compiles it, everything that it sees, you can see right here. So like this is an example of the AST. It kind of is pretty printed. You can see like there's a variable, you can see at the top it says like AST if statement. That's saying there's an if statement here. The first directive is X. The value is 2. There's all this information here. There's more information than you'll ever want here. So that's really cool. So what can we do here? We can parse all the Go code in a repo. We can basically collect all the dependencies for the packages and the types. We can collect all the function declarations, the package declarations, the type declarations, all the interfaces. We can see what every function looks like. Like does it take like, you know, arrays, slices, bytes, strings, complex structs? Also, if it takes a complex struct, what is that struct made of? And recursively down the whole thing. So you can basically go all the way down to all the built-in types in Go, and you can see all the information you want about something. So using this, we can generate valid fuzz harnesses for all of these functions that we have typed. and we can fuzz them. We can round robin them. We can fuzz them while the target's running, and I can talk a little bit about that more later. But then, yep, find their bugs, profit. I know this isn't like a security-specific conference, so this is a reference to an old frack magazine, smashing the stack for fun and profit. I'm not profiting off these, I promise. I want to clean up all of these bugs. That's what I'm paid to do. That's how I profit. Oh, and then you can repeat on every commit, which is kind of why Nosy got its name. It's the nosy neighbor. You can integrate it into your CI. Hopefully, people will do this. And then when bugs are introduced, like the moment they're introduced, we can just like automatically fuzz a function before even the tests are written for the function, and we can find these bugs. So it's like really annoying and really nosy to developers because there's like this old granny across the street that's like always looking in your business. That's where the name comes from. I just call it Nosy. Nosy neighbor's way too much, so I'll refer to it as Nosy from now on. So, Nosy in action. It basically has three main stages. There's an initialization, there's the harness generation, and the fuzzing. You can put this all into like one seamless, action if you're integrating into your CI. But for the purposes of like the tool as I made it, you might want to debug stuff in the harness generation. You might want to add test corpora. There's all kinds of like interesting things you can do in between these steps. So I have it broken up into these three steps just for like kind of sanity reasons. This is the input. Every time you run Nosy, no matter which of the three like actions you tell it to do, you're going to give it this YAML file. And this YAML file contains a bunch of stuff. The most important thing, though, is the URL to the repo. So it'll pull down this repo. You can say, I want this particular branch. You can specify different Go versions. Like Prism, for instance, is like one of the big repos that I always look at. And it won't build with Go 1.19 right now. This is really easy. As long as it's like 1.18 and above, because that's what supports native fuzzing, you can kind of use older versions and that sort of stuff. There's also these like ignore declarations I put in there. Like maybe you have a bunch of test functions. Maybe you have things that use networking, stuff that writes to the file system that you don't want to fuzz because you don't want to pulverize your file system. You can declare at the package, the function, and the object level to ignore these kinds of things. It also has substitutions. What this will do, if you're familiar with Go, if you put a substitution in here, you just put both packages in there, and it will put a little replace directive in the go.mod file. And this is really nice if you like want to knock out all of your like signature checks. You get a lot more coverage this way. Like obviously your fuzzer's not going to be like signing ECDSA signatures correctly. That would be a whole nother talk, and we'd be having bigger problems if that was the case. The initialization, it uses Docker. It basically makes this little fuzzing environment and building environment all in Docker. And there's kind of a lot of reasons for that. One is that we don't want to pulverize our host file system. We have a lot of ease with dependency. If you're like looking through and you're trying to dynamically write code, writing all these fuzzing harnesses, then it's a lot easier to not use your own Go root. So this makes a valid Go root inside of a Docker container. It makes it adds all the dependencies for Nosy for doing the source parsing and the harness generation and all the fuzzing and all this stuff. Throws it in this little Docker container and initializes it inside this repo, or initializes the repo inside this container. It has a shared like host file that you'll see like in a little bit. It's an asset directory that keeps everything that the host needs to get. So you do all your fuzzing inside this like protected environment. If you're a security researcher and you're familiar with like jailing a target, this is just like a cheroot under the hood, except that we get to stand on the shoulders of Docker, and we get to like potentially neuter all of the networking. We can like control things and like really jail stuff. It also makes it where you could like run this on your host computer and like only give it a few cores, and you could still like work, and maybe you're kind of like dual purpose using a fuzzer that's also like your desktop for research. Let's see, generate harness. Generate harness will copy all the assets in, and then it will spit out this one-liner. And if you double click this one-liner and run it, it'll start generating all of the harnesses. And so you can kind of see like the lower half of this terminal. It's spitting out all of these fuzz nosy test.go files. All of those files are placed into the respective package under test directory. The reason I do that instead of having them all in one is that one bug doesn't prevent the whole thing from compiling and having Go complain. The other thing is that we can fuzz internal functions. You might not want to fuzz internal functions, so Nosy has a flag for that. But if you do want to fuzz everything and get like this serious breadth first coverage of your target, this is the best way to do it that I found. So this gets to the fuzzing. Same thing, spits out a one-liner, it adds all the assets to this asset directory, and then you start fuzzing. So you can see on the right side here, it started fuzzing, it found a crash like right off the rip. It minimizes the test case that produces the crash, and then it spits out the like panic output. So kind of funny that one found one like right off the rip. This is an example repo that I have that comes with Nosy so that you guys can all test this. I don't provide YAML files for all of the targets I'm testing because I don't want to give you guys free bugs, and Nosy's still kind of like a work in progress. So I will release other stuff further down the line as I've like hammered out all the bugs that are there. I think what I'll probably do is kind of like have this like private repo that's maybe like 3 months ahead, and then as we've kind of like shaken out all the bugs that this fuzzer can find, I'll open source the other parts of it. But you can copy the example YAML file for this target repo that I've made, and you can point it at the Go standard library. I haven't had time to do that. I'm sure there's tons of bugs out there. Like I have, one thing Nosy does do is it causes like a decent amount of false positives, but it does find bugs. So I have like a ton of crashes to look through before I'll release all this other stuff. This is an example of like the round robining. So when there's not a crash found, this was what the output will look like. So it'll fuzz for like 10 seconds on each thing. The YAML file has a little variable there where you can say like how many seconds do you want to fuzz for. As you generate like larger test corpora that are getting better coverage, you might want to bump this up to like 6 minutes per function or something like that. This is just a little shot of like what the script looked like. Like what does the round robining? This is a shell script that's just like kicked out into the asset file that's run on the target. So there's some reasons that this is not the best way to do it, so I don't think I'll be doing this way forever. But if you can see right here, it basically calls the go test fuzz on the function you want. If there is test data fuzz inside of that package now, that means that we found a crash. Copy that into the asset directory so that it's available on the host. If the fuzzer either commits suicide or if you're done fuzzing, you don't lose this. A lot of people like know that use Docker, your container might not be persistent if you don't have some like asset directory where you save stuff off to. So this prevents you from kind of losing work that you've done. All right, example findings. I made this little repo so that everybody can kind of like see Nosy in action and have an example so they can point it at their own repos. These are all the root cause of all of these bugs are copied from real bugs that Nosy did find. And I'll talk a little bit about like the type of bugs it finds because it doesn't find everything, and it's really good at finding a few things. And I'll talk about that looking at these here. So this is just showing like the panic line. Like this is identifying the type of issues that we have. It looks like there's 2 index out of range. The second one actually has another bug. There's 2 bugs in that function, so I included the wrong screenshot. It should be like a divide by 0. So these 4 functions on the right show the vulnerable functions. So these are the kind of things that Nosy, like if you say like spend 3 seconds on a function, Nosy will find these things like immediately. And if you notice what these are, they're panics, they're not like remote code executions, they're panics where things stop. So if you have some blockchain software, it's highly social, it's listening to all these peers, every time it receives a packet, if you have like a gRPC handler and it's meant to like panic gracefully and it just panics in that go routine, you're fine. But if you have this in like core code, this panic can like make the panic go all the way up the stack and just completely bring down your node. So these like true like packet of deaths, they're a big deal, and this is kind of the thing that like keeps me up at night because panics are not always handled gracefully, especially in like these huge systems. So like the EVM, for example, if you found a panic in it, you might actually crash that part of the process, and then Geth would just be like completely worthless, right? So let's talk a little bit. I've only got 5 more minutes left, so I'm going to talk really quickly about like what these functions look like. So this is the most basic, right? So if you look at this, this is the same native supported testing. The input to the top it's actually a test function. It takes in the testing object from Go. You hand it a function interface, right? So this function here, all I'm saying is, hey, I want to fuzz this log validator webauth, right? I just picked some random function. It takes a string, and a string, right? So, this is the kind of thing I need to tell GoFuzz, hey, I want strings. When you mutate, like I need a valid type string. Super simple. This is something that Go testing does not support, complex structures. So if you see the second line there, what it accepts is actually a byte array. What this does is I use, right now, Nosy ships with the open source version. We'll ship with GoFuzz utils from Trail of Bits. There's some reasons that, and I won't go through them unless I have time at the end, why that's when it ships with. The biggest one, though, is that you see all of these fill errors. It will return if you don't have enough data. So if I have, like, you know, a bunch of nested structures, and like you can imagine my function under test like needs basically like 2,000 bytes to fill all the data correctly, it'll say, hey, return, there's no issue or anything, give me something larger. It doesn't really say give me something larger, but it keeps letting the fuzzer mutate until it finds, you know, further paths. And this is coverage guided, so the fuzzer will very quickly make it all the way to that last line. So what happens here, that last line is ACM import. It takes a context variable. I need a valid context variable. I want to basically test import, but I need ACM. This is an actual like object. So it doesn't just fuzz functions. It fuzzes methods on receivers, which is Go's version of an object. So methods on objects, we need a valid object created. We need the argument there, that kind of stuff. Yet more complicated. Here we actually have a constructor. So why make like an object and fill it with random data when there's custom constructors made? So like, you know, these large blobs for the EVM, maybe like different peer structures, maybe like beacon blocks, things like this. We've already got constructors for them. So like, why make them ourselves? We're going to get a bunch of like no pointer derefs and false positives. So what Nosy will do, and this is hugely inspired and borrowed from FCGen, even like probably like 60% of the code for this type of interface is borrowed from that. But what we do here is we go look and say, hey, is there a function that returns this object and only this object that doesn't take that object as an input? And you know, it can either just be that object or that object in an error. And if that's the case, we say, oh, that is a constructor. Sometimes you see false positives for this, but in reality, they're actually really good at still generating valid objects. So in this case, I need a new key manager. I didn't have to write new key manager. Some developer that made the new key the key manager object wrote this constructor. That's what he uses. It takes, you know, this configuration deal and then whatever C1 is, a context variable. So what happens here is Nosy recognizes this, builds not only its own version, but a second function to fuzz this that relies on the constructor, and whichever one gets, you know, more coverage can find the bugs. So right here, we basically find the constructor, and we know how to see a function interface. So we build everything we need for that constructor, and then we make the constructor hand us the object, and then we also provide everything for the function under test, which in this case is fetch, validate, something priv key. I can't really read from here, but this is just like a random example. There's plenty to choose from. One thing I forgot to mention, out of the 583,000 lines of code, there's over 15,000 functions in those 5 repos, which is basically all of the dependencies for Mev Boost, Geth, and Prism that are supported. So that's 15,000 functions that I can get coverage in, that's coverage guided fuzzing that I don't have to write the harness for. That's kind of like the value out of this tool here. And yeah, notice here that like Nosy didn't only like create the valid arguments to fuzz here, it created the object, and by doing that, the way that it did that was it created the valid arguments for the constructor. So everything that needs to happen here to try to get like as close to like a real test case as possible, we have. All right, mistakes learning. I'm gonna go really fast, I got a minute and a half. Version 1, actually there's like a version 0.5. Shout out to Tyler Holmes, one of my teammates. He did a big code QL query for various things, and we found like a bunch of stuff that just accepts byte arrays. So we wrote some Python that would like basically generate harnesses to fuzz those. That was version 0.5. Then version 1 was in Python. This is just like to show you my pain. I'm grepping for regex here in Python. All that gibberish, I felt like JR Token, like basically like writing Elvish or something. This was no good. Trying to do this for complex structures and stuff was like a total pain. So I moved on to the AST objects that you get from the Go parser library. But you guys have seen this. This is kind of cool. Looks sort of pretty printed. It still sucks. All that stuff is like, you don't really know like this AST ident on the fifth line that X is. You got to like do a type check on all of those. So you end up with like this massive parsing thing that's got like, you know, a gazillion nested case statements. Still better than Python, but still really ugly. Then I ran into FCGen uses the Go type libraries to write that like more complex function interface that I showed. It blew my mind. I can't believe I wasted all my time for 6 months on these other things. So I basically grabbed all of the code that works from there, threw it in here. It was a minimal rewrite for me. Cool. Talked about why we use Docker. These fuzzers will find the Go binary and delete it. They will write all kinds of crazy stuff to your file system. If that happens, you can just restart Nosy and your host isn't screwed. Let's see, various fill libraries. I talked a little bit about Trail of Bits. I have a proprietary version that I'll talk a little bit more about here. Last slide that really matters, I know I'm out of time. Things that we want to do, AutoCorp or Bootstrap. So you can imagine here, we already know how to dynamically write code. We can dynamically rewrite code. So if I point it towards a repo and I say, hey, I want to run Go Ethereum, you know, let's say I support 7,500 functions in it, then what I can do here is I can say, all of those 7,500 functions, instrument them, run Go normally, run it on mainnet if you want, save off every valid call to all of those functions and receivers, and then mutate on those. So I can bootstrap a corpora that way. I can automatically fuzz in a separate Go routine in a Docker image or something in real time. You can be like continuously fuzzing, mutating on real valid test cases. Let's see. Auto object fuzzing, you can find race conditions this way. You could say, hey, I know I support this constructor. It's got 10 methods on it. Write a fuzzing function that will kind of round robin those. There's some work like this in FCGen that I'd like to copy as well. I think if you run that with the thread sanitization, you'll find a ton of race conditions that way. Lockdown networking. You can do AST walk to say like, hey, I want to like look at all the reachability from this function. If it writes to the file system, exclude it because I'm tired of something's pulverizing my file system and it's destroying my fuzzer, that kind of stuff. Final task, test case minimization at the end of a run and all the coverage analysis. This would be really great if I had this done today because then I could say, hey, look, you know, Prism's testing library has this much coverage and I added this much coverage automatically with Nosy Neighbor. That would be really cool. Maybe I'll have that in 6 months for you guys. All right, I will open source this in the next 24 hours. That's my promise to you. My creative excuse, as of all procrastinating engineers, has a creative excuse. I got bit by one of these snakes like 4 or 5 days ago. I wouldn't be here if my wife didn't like do so much to get me here. I spent a lot of time in the hospital. I've been elevating this foot, hence why I came up on crutches. I'm starting to be able to put weight on it, but yeah, I actually have like a real excuse this time. The doc didn't eat my homework. One of those guys like legit bit me. It was a whole thing. Follow InfoSecUL on GitHub or Twitter. I'll drop the repo links probably later tonight, latest like this time tomorrow, depending on how the rest of the day goes. Real quick, I do want to thank FCGen, Trail of Bits for that fill repo, Zen Chada and Justin Traglia for various things that they added to this repo and to this project. The GoFuzz folks, and then everyone in the Gopher Slack that's been like super helpful. Any questions?
Yeah, with that, David, I'm going to say you can go ahead and take questions over to the side, but thank you so much for, making it here through all of those different hurdles and for giving us your great presentation. So thank you so much. If you do have any questions for David, please feel free. I am sure he'll be answering questions over there on the side. We'll make sure you get all set up over there too as well. Next up, we're going to have Bartek in about 2 minutes. While we transition the stage, feel free to talk or transition yourself as well. right, next up to the stage, we're going to have Bartek K. Puseshki. He's an architect at MakerDAO, and he's also the founder of L2 Beats. Bartek is going to be discussing roll-ups in the most secure bridges. With that, I will go ahead and hand it over to Bartek. You all set? Beautiful.
Thank you.
You're welcome.
Thank you very much. That's a big stage. Thanks so much for showing up. My special thanks is to MakerDAO fam, obviously. I'm going to talk a little bit about bridges. You might have heard a lot of talks about bridges. This one might be slightly different because the subject of the talk is actually quite serious. I mean, we had a lot of problems with bridges recently. So before I actually go into the crux of the matter, let's just go back and look at a bit of a history. So how come I'm here? 2 years ago, more or less, we started to work at the multi-chain strategy for the MakerDAO, and we asked ourselves a question: how do we actually move DAI to different chains? So it was actually quite hard, and for us, it took, sorry. Let me go back. So 2 years ago, we started to work on the multi-chain strategy. And we had to look at all the other chains, and we had to find out how secure they are to actually be able to move DAI in a very secure manner. And to do that, I had to look at the security of all the other chains. So basically, I created the spreadsheet, and I posted the spreadsheet on the forum. And frankly, after a while, not a lot of people looked at the data and looked at what we had to say. So I figured that we need to make this information more broadly available to the broader audience. And we basically created a website called L2 Beat. And the reason for us to actually do that was to make people aware that the security of DAI on all the other chains is very, very different. If you hold DAI on, let's say, Polygon, if you hold DAI on Phantom, you'll be looking at a very, very different DAI. And the security properties of the DAI will be very different. For MakerDAO, it is of the utmost importance that DAI is censorship resistant. And if you hold DAI on all these other chains, you should really ask yourself a question: is this really a DAI that you hold on Ethereum? Does it have the same properties, or is it actually different, right? And can you make all these different DAIs fungible? And what is it really needed to be able to mint DAI on all these other chains? So these are actually quite hard questions, and that's why it took us so long to get all of us to where we are here. And once we looked at all the other chains, we want to publish all the results, and this is how L2 Beat was born. L2 Beat was essentially initially created as a website to disclose all the risks for all the different chains. And it took us really by surprise how important this thing was. Everyone was like really looking at the risks and the value locked, and at all the information that we actually uncovered in a way. So let's have a very quick look at the state of the bridges and where we are today. So essentially, when we look back at the last year, it was a bad year, right? We had a hack at the Poly network, we had a hack at the ChainSwap, We had a hack at the ENS swap. So last year was really, really bad. But that doesn't really compare to what we witnessed this year. And it's really shaping up to be much, much worse. So it all started with the wormhole hack. Then we had Ronin network. It was like huge. $600 million was taken from that bridge. Then we had the Harmony, Nomad. This one was particularly bad. I personally really liked Nomad architecture. I was actually trying to convince my peers at Maker to have a very much closer look. And unfortunately, to a bug in a smart contract, it was hacked literally 2 weeks after I pitched Nomad. So that was really, really intense. And then probably a week before Devcon, you might have heard about Binance. And I even had to correct my presentation because of what happened literally yesterday, right? And it's not just the bridge. Some other DeFi protocols were hacked as well, but yet we had another bridge hack. So bridges are scary. And bridges seem to be really weak point in all of this. And we had to take a closer look at all of them. So far, we spent the last 2 years looking mostly at the rollups. And now it was time for our team to have a look at the other bridges as well. And how we publish this information, like I said before, we basically looked at all the escrows, we looked at all the values that was locked in all the bridges. But looking at other, not just the rollups, looking at other bridges was essentially requested by the community. And if Josh Stark from Ethereum Foundation asks you to actually do something, you should seriously consider. So without further ado, I mean, this is actually my pleasure to announce that at L2 Beat, we also are covering all the bridges. You can check it out. It's actually up and running and live since yesterday. And I'm going to tell you a little bit how we look at these bridges and what are the findings that we uncovered by looking at these bridges. So to put it simply, we obviously track total value locked in these bridges. So we can see more or less the same type of list as for layer 2s. We track total value locked, and you can see how much value is at stake. This is all that value that potentially can be hacked, and the bridges are like these huge pinatas for potential hackers, right? So we really need to understand what are the risks and what are the security assumptions behind all these bridges. And then you can look at the bridges to rollups as a type of a canonical bridge. So you can combine this information and you can see the total value logged in all of these systems and all of these bridges. But as you know, L2 Beat is primarily about the risks. We want to disclose the risks. Like you can see on this particular example, most of you probably know that Optimism does not have fraud proofs right now deployed. And this information should be known and available to everybody. So you know when you move your funds to Optimism, what are the security assumptions. I mean, we are in a close contact with Optimism team. We know that they're working on the fraud-proof system. But as it stands right now, you have to trust them, right? You have to trust the team and you have to trust the sequencer. So I guess we thought that we need a proper risk framework for bridges that would work more or less the same way as we did that before for rollups. We believe that risks should be disclosed. We believe that we should make everybody aware of the underlying security assumptions. We should constantly monitor infrastructure for upgrades, and we should really monitor the security parameters. And this is tough. This is hard because some of these constructs are actually quite complex, and you need proper automation, you need proper tooling. You actually need to be able to read from storage diffs. which if you have ever tried to do that, it's not particularly easy. And thankfully, right now, there are some tools that actually allow you to do it much easier, but generally, what you need to do is you need to replay all the potential Ethereum transactions that change the particular slot. So that's tough, but this is our task, and we believe that once we do that, we'll actually make multi-chain infrastructure more transparent and secure while keeping teams honest. And it is all about honesty, right? It is all about proper disclosures. It is all about making sure that users do understand the risks. So what are the risks when you're actually using bridges? And you would be surprised how few people actually do understand. Most people kind of think that when funds are in transit and once they arrive to the destination, they should be safe, right? So it's almost like, you know, crossing the bridge across the water, and once you made it to the other side, you know, you're safe. But you're not. You're definitely not safe, and I will try to explain why. But before I do that, you know, I will actually show you a few interesting findings that you might actually also find surprising. So the first one, and I think it's actually quite a big one, is the multi-chain. Multi-chain is one of the biggest bridges with the biggest TVL. Turns out that last year, they actually removed from escrow quite a lot of funds, like literally millions of dollars. So normally, for that type of bridge, you expect that you put your funds into escrow, and on the other side of the bridge, some funds will be minted, right? And when you go back, the funds from the destination, they will be burned, and the validators will release the funds from the escrow. Turns out that, you know, in this particular case, validators actually took funds out of the escrow without actually burning them from the destination. So that was odd, and the amount was very significant. And it seems like no one cared. Like, people were not really aware that that was happening, and just the fact that it is possible for the validators to take funds out of the escrow, this is the risk assumption that, you know, you should be all aware of. Right? If you're using the bridge that's externally validated, that's the thing. You know, they can all take your funds. So in this particular instance, apparently the funds were used to provide liquidity to any tokens on a lot of different chains. And to make sure that this is exactly what happened, you would have to like go to all the other chains and check it out. But, you know, my question to the multi-chain team is, was this part of the contract, right? Were users aware, and what is the consequence? Can actually users withdraw all their funds? And more importantly, what is this additional trust assumption? Because if the validators can remove funds from the escrow, they can do all sorts of things as well, right? And how do you actually monitor what they're doing? So that's one. Then you have something called Plasma Bridge. Some of you, again, might be aware of, because this is one of the two bridges that you normally use to move tokens to Polygon. And this particular one has a very interesting documentation. It says in the documentation that it provides increased security guarantees because there's a 7-day withdrawal period, and during that period you can challenge validators from Polygon. So it's kind of like a Plasma exit mechanism. However, to the best of my knowledge, this was actually implemented and deployed on a testnet, but it was never deployed on a mainnet, right? So if you look at the mainnet code, and by the way, who's looking at the mainnet code of the bridge, you know, of the contract? Probably very, very few of you. You'll see that the method that allows you to actually challenge the validators is empty, right? You can't do that. So frankly, the Plasma Bridge right now has the same security assumptions as the POS bridge, the main bridge that you normally use to the Polygon, and it's got this user nuisance of 7-day withdrawal period. And the last one that I wanted to mention, which in the documentation, the risks were properly disclosed, but again, I think that the user should be aware of that if you use the Omni Bridge to move your funds to the XDAI chain, they might invest some of these funds. They might actually put the funds that you normally expect to be in the escrow into Aave, into Compound, or wherever they like, actually, right? So normally it's called rehypothecation. This is the practice where, you know, banks are using your funds to actually invest them, and you're running into liquidity risk, potentially. If you were to withdraw all the funds, they may not be available. They might be like locked somewhere in say, Aave or whatnot, right? So the whole process is very transparent, but the power of validators to actually do that may be surprising to some of you. Because again, it's a question, what are the security assumptions, right? And what do you normally expect when you put the funds into the bridge? So, so now, with all these examples, you may wonder, you know, how do you actually collate all this information and how do you actually make it available to the users? And this is a challenge. We've got hundreds of bridges, we've got hundreds of different destinations, we've got hundreds of tokens, and every single transfer may be actually different, right? And this is a challenge for us as well, because we really wanted to make it very transparent to everybody, and we wanted to make sure that users are actually aware what exactly is happening behind the scenes. So we try to kind of, you know, make it the whole framework user-friendly, and I will quickly summarize what you will be seeing on the L2 beat bridges section. So first of all, we kind of differentiate primarily two different bridge types. And the first one is a token bridge, and that's the bridge that mints tokens on the destination. And then, so this is something that, you know, normally you should be like intuitively expecting, right? You put tokens into the escrow, the bridge mints tokens on the destination. However, a lot of bridges cannot mint tokens, right? Like, take DAI as an example. I mean, most bridges won't have access to DAI minting facility, so they have to do something different. They have to, on the destination, they have to create a liquidity pool. They have to mint something, or maybe, you know, through some other mechanism, and they will like swap whatever they minted for the DAI that is like sitting and waiting for you on the destination. And we call these types of bridges liquidity networks. And I think what is the most confusing for end users is that if you go to UI of almost any bridge, you will not know if you're actually using token bridge or a liquidity network. In fact, some of the bridges are hybrid. Sometimes, for some tokens, they may actually mint you tokens. Sometimes they may use liquidity pools, and it, like as is the case for the multi-chain, you can have like some mixed results. Some of the tokens may be minted for you, and some of the tokens may be actually coming from the liquidity pool. So these types of bridges we will call hybrid. And again, if you compare token bridges to liquidity networks, they have a very different risk profiles. So for the end users, I think it's very useful to actually understand the difference between the two, right? You have unlimited liquidity for the token bridge. You have tokens that if you keep the token at the destination, you will face the risk of the validators of that bridge. And generally, token bridges can be quite slow and expensive, while the liquidity network is almost like the opposite, right? It has limited liquidity typically, so you may end up with your tokens being stuck. But tokens held on a destination are not at risk of this network. They're actually at risk of the token bridge that was used initially to move tokens to the liquidity pool. So again, this is the risk that's actually quite difficult to disclose. And finally, they can be fast and they can be cheap, right? So this is the column on the L2 beat, which you can check very quickly, and this is something that should be essentially easy to read for all of you. And if you use any particular type of a bridge, you know, I do encourage you to check it out and understand the consequences. More importantly, from the risk perspective, and this is like maybe a little bit more technical, is the question how the messages are actually relayed between the source chain and the destination chain. So technically we use all sorts of terms for this, like arbitrary messaging bridge or some other terminology, but because we wanted to make the framework sort of user-friendly, we just want you to understand what are the four in our opinion, primary mechanisms that are actually used to relay the messages. And again, these messages are important because when you lock your token at the source, the destination somehow has to be informed how do you mint the token at the destination, right? So what are the 4 different categories? Well, first of all, you've got the third party, meaning that you have to trust someone to relay this message, and that particular party can essentially break you, right? So you put full trust on that party. Then you've got what we call the optimistic scheme. We relay the message, we trust that the message is correct, unless someone actually proves that the message is incorrect. So your intuition should be like, who's watching the relayers, right? Who are the watchers, and what is the length of the fraud-proof window? Because optimistic message bridges, they always have watchers, and they always have the fraud-proof window. Then we've got bridges that we normally call as secured by light clients. And essentially what it means is that we trust the destination chain to tell us what happened, right? So when, let's say, Polygon validators say that something happened on Polygon, I don't check that this is exactly what happens, I just trust the Polygon validators. And on Ethereum, I just need to build software that will check the signatures, essentially, right? So you're putting your trust on the validators on the destination chain. And the most secure bridges, in our opinion, are the trustless bridges that use Ethereum as the ultimate source of truth. So we don't trust anybody. We build smart contracts on Ethereum that will validate if the destination chain is not lying to us. Obviously, there are 2 techniques right now. You can use ZK proofs, or you can use fraud proofs. That's why we've got ZK rollups and optimistic rollups. And if implemented correctly, these are by far the most secure bridges, provided that there are no bugs in the implementation, right? So what can go wrong? I mean, if you've got external validators, everything can go wrong, right? They've got full access to the escrow. They can mint whatever they want to mint. If there's a bug, you know, you can have billions of tokens minted out of thin air, and validators can censor, they can steal, they can freeze funds, they can do whatever, right? You have to fully trust validators. For optimistic validation, as I said before, you need to make sure that watchers are actually active, because if no one's watching, the fraudulent message can be relayed. For the light client validation, if you're transferring your tokens to a chain that's weak, that has very, I don't know, it's a low value chain, and validators can be potentially 51% attacked, then your tokens again can be stolen from escrow. So you have to really understand how strong is the chain that you're moving your tokens to. And finally, for rollups, for full client Ethereum validation, in theory, nothing can go wrong, right? So funds cannot be censored, funds cannot be stolen, as long as there are no bugs in the implementation. And this is how we actually show who is validating all these bridges. And I think this is the most important column that you should all focus if you want to understand how a particular bridge operates. Then we have upgradability. So this is essentially the information whether the bridge can be upgraded and who have got the upgrade power. And again, we kind of have to assume that whoever's got this power is honest. So this is a very important security assumption. If you can upgrade the bridge, you can steal all the funds. That's as simple as that. And finally, and I think this is the most interesting aspect, which is often overlooked, is who's got the minting power on the destination, right? So take again DAI as an example. If you move DAI via 3 different bridges, let's say you use the MakerDAO bridge and move your DAI to Arbitrum Optimus Starknet, your DAI will be essentially minted by MakerDAO contracts, right? And it will have exactly the same properties as your DAI on the mainnet. But if you move DAI through the Polygon bridge, then your DAI on Polygon will be minted by Polygon validators, and they might actually have the upgrade power of the DAI. And finally, if you move DAI on Phantom, it will be minted by multi-chain, multi-sig. Right? So again, it's a question to you, I mean, how secure you feel with your DAI in your wallet. So this is the last column that we show on our framework. And as I said before, I guess, you know, the end game for all of us should be to build trustless bridges. Because everything else, we need to put our trust on some other parties. And these bridges are very, very hard to build. We had some problems with Arbitrum Bridge. There was a bug. It was essentially, fortunately, uncovered, and the bridge wasn't hacked. But as you can see, you know, the roll-up bridges can be buggy. Same situation happened in Optimism, and this is one of the reasons why these bridges are right now not fully yet permissionless, and I hope they will be very, very soon. But even more importantly, as you can see from this transaction, that's actually moving, how much is it? This is actually over 700,000 Ether from one version of the bridge to another version of a bridge, and that power has Arbitrum multisig, right? So even though you may think that Arbitrum has fraud proofs and whatnot, they still have a multisig that can move all the funds from the bridge, and they did in this very transaction, and it doesn't really raise any alarm. So that was kind of interesting. We saw this transaction, and we analyzed this transaction. It was an upgrade, and everyone knew that Arbitrum was about to upgrade, but seeing such a transaction moving essentially billions of funds in one move, it's kind of scary. So to sum up, we kind of think that we have no choice. We have to put engineering effort into building those roll-up bridges. I don't think it makes a lot of sense moving forward to rely on third parties in the long term. In the short term, they might be quite useful because we need that functionality, but in the long term, eventually we need to find a way to actually make sure that the code behind all these roll-ups is actually secure. And as I said before, I mean, the code is very, very complex, right? These bridges are actually very hard to analyze. I guess for a while, none of these roll-ups have shed the training wheels, so you should really also understand what are the current assumptions. But every single team that we talk to, they have promised us that eventually these training wheels will be shed. So there's some hope for the future. But how do we make sure that such complex software is bug-free, and how do we make sure that these roll-ups will not be hacked in ensuing months? And I think this is probably one of the hardest questions from the engineering perspective and from the perspective of the whole community. We don't seem to have a solution for dealing with discovery of potentially critical bugs without actually relying on some honest actor, right? If the bug is found, we all want some good guys to shut down the bridge, fix the bug, and restart the bridge without the bug. That's quite obvious, right? No one wants really the bridge to be drained by malicious actor. However, right now it just seems that the best we can do is to sort of create a multisig of some trusted security engineers, I guess, or a security council of sorts, and these guys can perform these sudden upgrades. And to make it permissionless and to make it immutable, that also means that we are exposed to potential problems. So thank you so much for listening, and I do hope that the future is bright and hack-free.
Thank you so much, Bartek. I'm sure if you have questions, Bartek, I'd ask you to go on the side, and then if people have questions for Bartek, you can go ahead and go over there. Next up, we're going to have Brewster Cahill. And Brewster Cahill is a founder and a digital librarian of the Internet Archive. Brewster will be talking about publishers' denial of digital ownership versus decentralization. I'll go ahead and turn it over to you, Brewster.
Thank you very much. So thank you very much once again. I bet this isn't a talk you were expecting. So I hope to at least, maybe a bit of a downer, but at least you'll learn something from it. In the Devcon in Japan, I suggested that the issues, once we start to have currencies with interest, that we could have debt with interest, that you get runaway wealth inequality. And historically, according to David Graeber and Michael Hudson, it leads to civil wars. So we needed some mechanism to have jubilees or other mechanisms of doing debt relief, or things can go very wrong. Okay, so I'm going to give another kind of thing to worry about that I hope is going to be at least useful to you on a going forward basis. And it revolves around the term digital ownership, of what is digital ownership, how it's being manipulated, what are the risks, what are the large corporations trying to do about it, and the like. But before I get on a downer, let's just, I want to just say thank you all for moving Ethereum to proof of stake. I mean, what an enormous achievement, and thank you very much. And I actually moved all of my personal Bitcoin to Ethereum because of this just in the last while. So thank you all. It's really wonderful to see this whole ecosystem take steps forward in the way that you guys have brought it forward. Okay, publishers' denial of digital ownership versus the decentralized web, which is the work the Internet Archive has been doing. So what does it mean when the mega publishers, 4 mega publishers, sued the Internet Archive about trying to have digital ownership of scanned books? And this is, I'd say, a widespread precursor of things you'll see in other areas. So in The Nation, they wrote it up as actually above just the Internet Archive, it's taking the internet to court. That the concept of what it means to have files, be able to archive them, be able to have use of them, be able to have them on your hard drives, is coming under attack from these extremely large organizations, and they're doing it in the guise of a lawsuit against the Internet Archive. So who are these people? It's orchestrated by the AAP, but it's the 4 of the very largest publishers in the world, one owned by Rupert Murdoch. There's other large monopolies, multi-billion-dollar corporations that are coming after the Internet Archive for fundamentally what we've been trying to do is buy electronic books in the same sense we used to buy books in the past. So we'd buy an electric book, and then we'd be able to preserve it and lend it out to one reader at a time, right? That's kind of what it used to be in the physical world. Why not in the digital world? They would not allow us or any library to buy an electric book. They're not available at all, so you can't own them. So that's a puzzle. So we said, okay, let's go back and scan the books that we do physically own, have one copy, and lend it one reader at a time. Been doing this for 10 years. It's been going great. Hundreds of libraries do it. And in the beginning of the pandemic, these publishers sued us to try to stop this practice across the board. So it's a bigger issue than just a little library sort of little lawsuit, as I will try to suggest. Like, for instance, if you want to get into the mind of what these big publishers are doing, Pearson, which is a major textbook company, is starting to invest in NFTs as a mechanism of killing off the secondary textbook market. So that even though if you've paid them for a textbook in the electronic world, you can't go and sell it to somebody else or give it to somebody else or actually own it in any real sense. So where the wonder of the blockchain was to have an artificial scarcity in the digital world, we've now allowed also mechanisms of holding on to things past when it was normally released based on being paid. in the world of books, and we're starting to see that in movies, for instance, or music. If you think about the music you've probably listened to in the last week, you probably don't actually have the MP3s of those. You're just listening to them off of some streaming service that can change at any time. So what does that world look like? It's really problematic, and at least we have some friends. So there was a recent letter signed by over 300 authors. It's now up to 850 authors. Neil Gaiman, a bunch of other very famous authors, to basically say that this lawsuit against the Internet Archive and libraries in general is a problem. But this is not, again, restricted to just a library issue. So digital ownership is what's at issue, and it's what's being formed now, and this community could really help if we work together to try to understand, what does this mean? How much role can people have on an ever-going basis forever to be able to say what it is you can do and how much can they retract at the end of the day. So let me just say a little bit about the Internet Archive. I'm going to just flash through a bunch of big numbers to just say, gosh, isn't it impressive? But to give you kind of an idea of what the Internet Archive is, which you may only know as the Wayback Machine, but it's a bunch of other things too. We have 790,000 software titles, many of which are emulatable, so you can go and do your old Oregon Trail days or whatever it is, your favorite video games on old platforms out there. We have over 5 million moving images that people have uploaded. This isn't even counting television, that are available, lectures and the like, on archive.org, a nonprofit library. Audio recordings, 14 million of them, including 280,000 concert recordings from bands that agree to share, sort of in that non-commercial kind of Creative Commons ways. So the Internet Archive has lots of these, and people are uploading more all the time. We have about 2 million hours of television news, so you can search what people said, which has been very important. It's not just United States television news. We also now have Russian, Ukrainian news that's being useful to find out what different populations are getting fed by the large media companies. And we have about 6 million books that we've digitized, one page at a time, that are available for free, for lending, and a lot of web pages. We're probably best known for the Wayback Machine, but we've got over 99 petabytes of data. I just love this number because it's just kind of ridiculously large. And so we're going to break through 100 petabytes and have a party. So we've also been pioneering this idea of the decentralized web by going and promoting a values-oriented next-generation web where it's a peer-to-peer backend. On the web, the Filecoin, the storage, are sort of the parts of this that we're trying to build a better internet. Best known for the Wayback Machine, we've got 700 billion web pages and a lot. But what happens when corporations license rather than selling digital things? And we've got troubles with the right to repair. We have, people that own tractors, they can't repair them because they're under a license agreement. What does it mean to own anything in this digital world? What happens when corporations license and sell things? Well, they get to hold on to them forever. So they get to basically be able to reach onto your device and pull it back. I guess the most dramatic of these is when Amazon came out with the Kindle. Why would you call a book reader something that has to do with fire? But anyway, their book reader, they bundled 1984 onto it and distributed it. Well, the family of George Orwell objected, and so Amazon went onto everybody's Kindles and took it off. I mean, 1984 happened to 1984. So is this happening? Yes, it is happening. So they get to hold on things forever. They can decide what can be done with it and these issues forever. They can say who can get access to what, when, and they can change anything about what it is that you can see. They can take it away, and this is happening. What if you can't buy one? and only lease digital books, then every reading event is permissioned. So anytime you turn a page, somebody is controlling what it is you see and whether you can see it. And it can be completely individualized. So the pages can be tracked. They can change the books at any time. They can deliver different books to different people, and you might not ever know it. And corporations and governments can change history. They can just make things go away. No amount of digital currency, magic, or changes to copyright law will stop this. It's the magic of licenses. It oversteps all of that. The publishers have manipulated copyright law to last way too long and cover all sorts of things. But at least it was under rule of law. But when you're under rule of contract, they can go and set whatever terms they want. And there will be fewer and fewer publishers, which is happening. They're consolidating and becoming platforms. So they're not interested in protocols, they're interested in platforms. So where we have a typically now sort of, we're trained to go and say, oh, bad Google, bad Twitter, bad Facebook. It's true, those organizations should reform. But there's these organizations that are behind the curtains, owned by some of the very richest people in the world that control not a lot of what it is we see, what gets published, and that structure. And they are getting stronger and bigger all the time. So, is it happening? I mean, you know, we hear a lot of scare things about, you know, this and that. And the answer is, well, yes. And will it continue to happen? I would suggest yes, unless we win our lawsuit. So our book's disappearing. So just 2 weeks ago, Wiley, which is a major educational publisher that had been selling these database products, remember you can't actually buy the ebooks, you can just rent them if you're a library, and then they were being assigned in classrooms, and then they took down 1,200 of them and just made them poof, go away, right? So yes, can they go and take books away on scale? Yes. Are they? Yes. Are they watching every page? Yes. In fact, they're proud of it. So Amazon is proud of being able to count all of the pages that you might read in some particular book and go and change how they compensate people upstream. The Authors Guild, which is a trade association very closely allied with the publishers as opposed to authors, has been pressured, and they were very proud that they pressured Amazon to spy even more on users, such that if you flipped too many pages in a book that you had bought, that you couldn't return it for money with Amazon. That they thought this was a huge victory to spy more on readers. So we've got some incentives not going right. But I'm just trying to demonstrate, yes, there are real problems going on. Is book banning going on? Yes, at scale. I mean, there seems to be a competition in the United States between the states to go and say how much banning can they do, and that's a pride in one of the parties in the United States to go and surface and constrict more of what people can see in the library system. So there's libraries can't buy things, they can't, and they're starting to get rules by governments to take them out. What libraries do is they buy, preserve, and lend. They buy books from publishers, and it compensates authors this way. They preserve them long-term, and they make them available, and then they also lend them one reader at a time. What the publishers are saying is you're not allowed to buy, you're not allowed to preserve, and you're not allowed to lend in the electronic world. This makes a shifting sands that's kind of supposed to be the antithetical to what we've been building in the decentralized world, where you actually know that you actually have those coins or whatever. But we're seeing some of these contracts be able to be used for exactly the flip opposite. Right? It's a little deja vu for me. I'm an old guy that did a lot in the early Internet Hall of Fame, the system of publishing before the web called Waze. So I've seen a lot of this go through. I've seen a lot of the promises go through. I've seen a lot of the dreams get twisted by extremely powerful players to play against exactly the things we set out to do in the first place. So think about it hard as we're building some of these systems, because it's going on now. So what should we do? What's sort of the, okay, that's a little doom and gloom, Brewster. Got any suggestions? Well, yeah, let's go and get the next generation publishers. Let's buy books from them, and let's publish your books with them. So when you're trying to go and get your next book out there, go with one of these presses. They sell to libraries. And Vitalik's book, the Proof of Stake book, it's on 7 Stories Press. And I visited them, and they gave me a preprint before it was published edition of it, which is just great. But these are some of the indie publishers. I would say indie publishers should be independent of the big behemoths, and they should, just like in the indie music world, go and do something differently of supporting the authors more and supporting libraries more. So these, at least, are ones that are selling. Support antitrust. The idea that these organizations can get so large, it can make it so that it doesn't even matter if there are anti-censorship rules. If only a few book publishers get to go and say who gets compensated to make books available at all, or who's on the major television news channels like Fox, then you can bend the discussion just from that. So let's keep the organization small. Cory Doctorow and Rachel have been very cogent on this point, and something to do. And support the Internet Archive and other libraries that own collections. That should be something that you're conscious of. Hopefully out of this, it's just digital ownership is something that really needs to be protected, not just for libraries, but the internet as a library. As we're going into the decentralized web, if we cannot make copies and put them in different places, we are sunk. The way that the world worked before the web is publishers, writ large, all sorts of publishers, would go and sell things. It would be bought by individuals and libraries, and they would go and hold on to it and make it available. And even if one library burned down, it would still be available. If the publisher went away, it would still be available. If it went out of print, which they do all the time, it would still be available. This is not the way the web works. It's on one server, and if it's changed on that one server by that one organization, they assert the right to go and change it forever and for always. This doesn't make any sense. So the decentralized web was to try to bring a peer-to-peer backend back to the information ecology, to make a healthier world. So that's the hope, and please engineer some of your systems into building a better web. Thank you very much. I think we have time for a few questions, if at all. Otherwise, you get some more time back. Why don't you just start by talking loud?
Yeah, there's a question over there with the gentleman in the white shirt.
Oh.
If you stand up, it might help the volunteers get you a mic quicker. Oh. Yeah.
So I read about an effort the Internet Archive was making to curate the Wayback Machine and curate snapshots of websites to include, some flags for fake news or misinformation. Can you talk more about that? Or,
yes. So the Internet Archive collects lots and lots of web pages and tries to get everything that's publicly available. But not all of it sort of belongs in a library in lots of different ways. For instance, we get people coming back to us from their blogs and going and saying, look, that was a blog when I was married to somebody else, and I kind of like to not have that be available. So a lot of those get removed from the Wayback Machine. unless they're a famous person. So for instance, there are some people that are now running for political office. We will put those back in play. There are other things that people have used the Internet Archive as a publishing platform, and we're not a very good thing for that. They might upload a movie to go and promote their recruiting of adherents and having close-up violence in recruiting of certain soldiers in their war. We want to have copies of these, but we don't want to be a publishing platform. So we put some speed bumps in the way of making it so that it's not just a Twitter click away. YouTube and those sorts of things are publishing platforms. We are a library. There's also some things that are not just calls for violence, but they're ongoing harassment. So these are, people will write to us and try to have things that are being used as harassment, and we will often put in a speed bump or put some context around it if it's been debunked, to try to give some context to people. I think that sort of something we've been trying out is the answer to bad speech is more context. To give it so that when people see something, they kind of know what's going on. They think of it as the card catalog function of a library. It's not just to have everything on the shelf. Blanket is to go and have things such that you know what it is you're looking at. And some things in the short term actually are used for harassing people to the point of death. And so we're trying to make the balances of these such that we don't take things completely away. We might just make it so that it's less visible or less visible for a time, to try to make it so that, I don't know, the bad behavior is not multiplied based on our efforts. We're here for the public good. We try to stay with that North Star. It doesn't mean that everybody agrees with what it is we do, but we try to be transparent, non-commercial about sort of what our decision-making process is in general, if not exactly in every specific case.
Awesome.
Yes.
So I hear you when you're talking about we need to decentralize more content distribution to have a more peer-to-peer web. But as you put it yourself, incentive works, and right now there is not a strong incentive for the distribution of content. Everyone has used a torrent before, I suppose, and there is the infamous...
I'm having a little hard time understanding.
Oh, sorry, too fast. So I suppose everyone in here has used torrents before, right? And torrents comes with a problem of seed versus leech ratio. And if you want to propose a more decentralized web for the distribution of content, there needs to be an incentive for the seeder to provide data to the leacher independently of the content of the data. And what blockchain does currently in cryptocurrencies is they incentivize block production, but not necessarily content distribution to the user. And how would you solve, in a decentralized fashion, the incentivization of content distribution? Right now, it's centralized by lawyers and these big corporations, like, oh, you're not allowed to distribute my content. But at the end of the day, they only have as much power as the law. And if you have someone that don't respect this law, like someone in Russia does not really respect Western law, let's say, and you could have content that is banned in the West being distributed by a Russian node. But right now, in torrents, there is no incentive for this Russian node to give you this data. So how would you go around incentivizing data distribution in a decentralized fashion, which means rewarding data distribution regardless of the content of the data?
I could only understand a small amount of that. Let me see if I'm going to say something back to see if it's basically right. How do you incentivize people to go and do content production in a world where things can be pirated endlessly?
No.
So I think the question was, how do you incentivize content distribution? Am I correct? Content distribution.
Correct. Anonymous content distribution, regardless of the data. Right now, there is no incentive to seed data to other people outside of goodwill. You're not getting paid to give someone data, regardless of the data. Like in peer-to-peer internet, you have no incentive as a seeder to give data to other people. How would you solve that?
So it's more of like how do you solve the incentivization like structure in order to have like more incentivization for people to give the data, like give the...
Right.
Yeah.
So there's been a long bed of work to try to get open access to work. Basically, writer pays, government created materials, which is great, but it doesn't solve everything. So how do we get people paid by going and making materials and then distributing on the internet?
Without getting lawyers involved, yes. So the consequence of the laws have been centralization by big platforms.
Yeah.
So this means you need a protocol solution to get around the law. Like Bitcoin did not wait for the US government to create digital money, and you need the same kind of thing to happen, to have your internet of peer-to-peer content.
So they're saying that the lawyers actually present like a point of centralization then? And so
Sure.
how do you incentivize it without the lawyers involved, setting up like a peer-to-peer structure?
Not everything is solved. Let's start with that. So there's open questions, especially in the digital arrangement. I like looking at history as sort of when did things work well? And there were periods of time when basically there was a royalty structure for large-scale production, distribution, sales of, say, books or music in a physical form. A lot of that has not translated forward. Some better or for worse, we've seen a lot more centralization. I think that we can have a many-to-many-to-many protocol system, as you point out, not a platform system. We're attempting to do such a thing with Book Server by going and making it so you can sell and lend books over the internet and be able to actually buy them. Could there be piracy? Absolutely. But let's make a system that actually works for people. And fortunately, there's enough money around. In the United States, there's $12 billion a year just spent on the library system. 3 or 4 billion of that goes to publishers' products. It's about 20% of all the trade books. Let's go and spend that money as well as we can to build a system that works for more than just a few big publishers. And so, do we have the solutions in the digital world? No, not yet, and hence this talk.
Awesome. Thank you so much, Brewster. We're at
Thank you very
time.
much.
So I'm sure there's other people who have questions. You can find Brewster over to the right if you do. Right now, it is time to eat, so feel free to go out to the lounge, grab yourself a bite to eat. I hope you have a great rest of your afternoon. Again, my name is Gloria. I'm with Biddlebox. If you have any questions or have any needs, come find me.
Space and distance, but if that's your decision, then I'll let you be. Oh, that's what you need. Meet you where you find your answer. If it changes after, then I'll let it be. Oh, that's what you need. If that's what you need. Wake me up, I'm ready now. Just one word and I'll follow now. 'Cause I want you. 'Cause I want you. Make you move, I'm ready now.
Good. Good afternoon, everybody. Hope you had a great lunch. My name is Kartik. I am from ETH Global, and I'll be your MC for the rest of the afternoon. We'll wait for everybody to settle in a few seconds. We have an amazing next 4 hours planned. We're going to talk about the nature of money, MEV, what comes after the merge, resource pricing, security, ZK rollups, and a bunch more in the middle. So we've got the next few hours really packed for you. And with that, we are ready to kick off with our very first talk for this afternoon. And I'd like to invite Justin Drake, who needs no introduction, to talk about Ultrasound Money. Please give Justin a big round of applause.
Thank you, Kartik. Okay, so I'm going to be talking about Ultrasound Money. And really, that's Ether, the asset. So I'll be focusing on the asset, not so much Ethereum, the protocol. And it turns out there's only one Devcon talk about Ether, the asset, and that's the one right now. And I'm hoping that this time next year, we'll have multiple talks about Ether, the asset, because in my opinion, Ether, the asset, is critical for Ethereum to be successful in its mission in becoming the settlement layer for the Internet of Value. We need to understand it, we need to nurture it. So, yeah, without Ether, there's no Ethereum. And if Ethereum becomes the settlement layer for the Internet of Value, then de facto, Ether will become something very special, namely money, money for the internet money. And there's this deep friendship between Ether and Ethereum that I'm going to try and tell you about today. But before we get there, I want to give you a mental model around the temperature of money, or some people call it the velocity of money. I'm going to invite you to think of money as water, which can be in multiple states. It can be liquid, it could be solid if it's cooled down and frozen, and it can be in this gas state if it has extremely high velocity. And this is interesting because at layer 1, we have mechanisms that explore these extreme temperatures. So you can take Ether, water, and at layer 1, you can freeze it, you can stake it. And in the process of staking, you're reducing the velocity of that Ether because it's kind of put in a black box and can't move. And something similar happens with the burn. The burn is all about destroying ETH, consuming it, vaporizing it, and turning it into gas, vapor. And something very similar happens at layer 2. So at layer 1, all of this is enshrined in the sense that Ether has a monopoly. And at layer 2, there's something similar happening, but it's more of an emergent ecosystem. It's more competitive. So what happens at layer 2 is that Ether or other forms of money get bonded and get used as collateral in the context of decentralized finance. And money could also be used as currency when you're transacting. For example, when it flows through the pipes of Uniswap. And the word currency comes from the word current. And it's basically money that is moving. And most of the time, when people hear the word money, they think currency. And they only think about the high velocity use cases. But it turns out that, especially for Ethereum, we shouldn't be discounting the low velocity use cases, as those are extremely important as well. Using Ether as collateral is a use of money. So just to recap, we have Ether, programmable money, which can be programmed to do various things that contribute towards Ethereum. A little bit like a stem cell, it can be fully programmed to be a brain cell or a heart cell or a liver cell. And Ether could be programmed to be stake, contribute towards security. It can be programmed to be base fees and contribute towards the sustainability of Ethereum as a project, economic sustainability, economic security. It can contribute as economic bandwidth in the context of DeFi, and it can contribute to economic activity that is that is on top of Ethereum within the decentralized ecosystem. And one thing that I want to highlight again is that there's these two different economies. There's the cold economy of money, mostly collateral money, and there's the hot economy, and both are extremely important. And in this talk, we're going to go through the various uses of Ether that kind of help Ethereum become a settlement layer for the Internet of Value, starting with security. So if Ethereum is going to settle the Internet of Value, it shouldn't get crushed by the economic weight of it, because the Internet of Value is going to be massive. It's going to be tens of trillions of dollars. And we can't have the Internet of Value be secured by like a tiny amount of Ethereum economic security. And so there's this important concept of the security ratio, which is simply the total value secured divided by the economic security that Ethereum has. And right now, we're at a point where the security ratio is very healthy. It's only 20. The lower, the better. And Ethereum is securing roughly $400 billion of value in the form of ETH, ERC20s, and NFTs. And because it has roughly $20 billion of economic security, that gives us the security ratio of 20. $20 billion of economic security. Is that a good thing? Is that a bad thing? Well, in a way, it is a good thing, especially for Ethereum that is such a nascent project. And it's especially good that it's become, Ethereum today is the most secure blockchain, even surpassing its older brother, Bitcoin, by a factor of 2x. So if you want to do a 51% attack on Ethereum, that's going to cost you $20 billion. If you want to do a 51% attack on Bitcoin, that's going to cost you roughly $10 billion. But $20 billion in the grand scheme of things, is that a lot? No, it's not. I would argue that we want trillions of dollars of economic security for Ethereum, partly because we want to keep that security ratio relatively low, but also because we don't want any attacker, even the most sophisticated ones, like nation states, to be able to attack Ethereum. And if we have so much economic activity, then we'll be protected. Now, the economic security comes from these ETH deposits. And in the last 2 years, we've had a very healthy, continuous stream of deposits. On the order of 20,000 ETH every single day for roughly 2 years. And so now we're at a point where we have 14.2 million ETH staked. And we can ask ourselves, how much ETH can we expect to be staked in the long term? And the way that I think about it is by looking at what incentivizes people to stake, which is issuance. So there's two parts to staking. There's the cold economy, where you're freezing money as stake, but there's also the hot component, which is when you're issuing Ether as incentives for validators. And it turns out you can have a look, you can look at the yield from issuance, and there's this relationship, which is that every time the amount of ETH stake grows by a factor of 4x, the yield from issuance decreases by a factor of 2. So with 4 million ETH staked, the yield from issuance would be 8%. With 16 million ETH staked, it would be 4%. And with 64 million ETH staked, it would be 2%. And now, it turns out that what we should expect is that the yield from issuance is going to have an equilibrium with the cost of money. And if the cost of money is, let's say, 3%, then we should expect something between 16 and 64, something like 30 million ETH staked. Now, this brings us to the importance of the ETH price, because we have, let's say, 2x increase in the amount of ETH staked. Like, how are we going to get trillions of dollars of economic security? So today we have $20 billion of economic security. We want to get, let's say, to $1 trillion. That's a 50x increase. We can get a 2x increase from ETH stake to $40 billion, but we're going to need more than that. And specifically, we're going to need the price of Ether to go up 25x in order to get this really robust amount of economic security. Now, one thing I want to mention at the end of this first section is this idea of minimizing the cost of security. So issuance has negative externalities because it dilutes all the holders. And at Genesis, we were issuing a lot of ETH, roughly 12.5 million ETH every single year. And now we're at a point at the merge where we've decreased that by roughly a factor of 20x. And we've reached a point where the issuance is extremely small and is essentially optimal. And that because we can't improve it, this is actually a forcing function for us to essentially ossify it, because we've reached the best possible design. Great. So now that we understand that ETH is like critical to the security of Ethereum, let's talk about sustainability. Now, what do I mean by sustainability? We can think of Ethereum as a company. And the product that it's selling is block space, specifically secure block space, extremely secure block space. And as a project, it has income and it has expenses, and that leads to profits. And we want profits to eventually be positive. We want the project to be successful, to be sustainable. So income is the block space sales, expenses is the security budget, and that's basically, for Ethereum, is the burn minus the issuance. And we can go further than that. We can actually look at PE ratios, for example, and analyze Ethereum almost as if it was a tech stock. Now, since the merge, despite the massive reduction in cost of security, we are still not sustainable, in the sense that Ethereum is still not able to pay for its security to compensate that with the income that it gets from selling block space. But the good news is that the amount of unsustainability is absolutely tiny. It's less than 0.1% per year. And if we were to zoom out a little bit, because right now we're at a moment in history where the depth of a bear market and the transaction fees are very low, but if we were to zoom out even just a little bit, then we'll see that actually Ethereum is in a position to burn much, much, much faster than it is issuing. So if we take all the data that we have since EIP 1559, we're burning roughly at a rate that's 3.5 times the amount that we're issuing today. And so the supply growth is expected to be negative. And so we have this shape of the supply which we should have, which is that during the first 7 years of Ether's existence, the supply has grown very, very fast from this extremely high issuance, and the peak is this inflection point around the merge, after which the supply will start decreasing and finding a new equilibrium. And this is what birthed the Ultrasound Money meme. If we call monies that strong monies that can't be debased artificially because they have a capped supply sound money, then surely something that has a decreasing supply, where the money becomes stronger and stronger every single day, should be called ultrasound money. And it turns out that bats produce ultrasounds. And David, who's with us here, kind of innovated here at the mimetic level and said, let's wear the bat signal to spread the ultrasound money meme. And this is what he started. We now have thousands of accounts on Twitter that are spreading the ultrasound money meme with the bat signal. And there's a community that is being built as we speak. Okay, so Ethereum needs security. It will almost certainly be sustainable thanks to all the fees that it's collecting and burning, compensating for the cost of security. What about the application layer? What about economic bandwidth? So ETH is used as economic bandwidth for decentralized applications. So two examples would be Maker, which uses 1.4 million ETH as collateral to power its decentralized stablecoin, and Aave, which is consuming roughly 500,000 ETH for its decentralized loans. And the reason why ETH is such a good choice as a collateral asset is because it's pristine. And what we mean by pristine is that it doesn't have a lot of these tail risks that other assets might have. It has no contract risk, no custodial risk, no oracle risk, no bridge risk, and no governance risk. But there is one downside to ETH, which is that it is pretty damn volatile. And so one of the things that we can try and do is stabilize ETH. And this is exactly what stablecoins are, specifically decentralized stablecoins that are backed by Ether. And here are 3 different projects that are using Ether to back their decentralized stablecoin. And right now, we're using about 2 million ETH specifically for collateralizing decentralized stablecoins. Now, I believe that we're at the very early days of Ether being used as a collateral. In my opinion, Ether is the perfect collateral money. And so today, we may only have, let's say, 16 million ETH that's used as collateral, but in 10 years' time, it could easily be 4 times more. It could be something like 60 million ETH that is used as collateral. Now, again, I want to emphasize the importance of the ETH price here in the context of economic bandwidth. Right now, we have about $1 billion of decentralized stablecoins that are collateralized by Ether, which is almost nothing. And really, we want to be in a position where we have trillions of dollars of decentralized stablecoins, right? We don't want to see a future where the economic activity is denominated in USDC or USDT, which are centralized stablecoins. Now, let's say we want to get to $1 trillion of decentralized stablecoins. We need to grow 1,000x from where we are today. We can grow the amount of collateral quite a bit by 15x, but that would only give us $15 billion. We need the price to go up, essentially. We need Ethereum to be successful so that we have a lot of economic bandwidth for decentralized stablecoins. Now, one of the concepts I want to talk about here is the notion of illiquidity multiplier. So you know how I kept on emphasizing that there's 2 economies within Ethereum. There's the liquid economy, which is hot, and the illiquid economy, which is cold. And really, all the cash flows happen within the liquid part. So if you think of the burn, it's liquid ETH that is burnt to pay for block space. And if you think of the issuance, there's like fresh ETH that is liquid that is added to the liquid portion. And so really one way to think about the Ethereum market cap is to focus on the liquid portion for which we have models. We have the discounted cash flow, we have PE ratios, etc. And then once we understand how much this liquid portion should be worth, the portion which is basically Ethereum as a business, as a tech company, then we can scale that out to the whole market cap. And the scaling factor is this illiquidity multiplier. And where we are today is that most of the ETH is liquid. And so the illiquidity multiplier is actually tiny. It's just noise. It's like 25%, which is roughly the monthly volatility of Ether. But things change quite a bit once most of the ETH is used as collateral money. Let's say that 80% of all ETH is used as collateral money, and only 20% is liquid. Here, then, the liquidity multiplier is pretty big. It's 5x. So if the Ethereum cash flows, if the business of selling block space is worth, let's say, $1 trillion, then the whole market cap of Ether, the assets, should be $5 trillion. Great. So we understand security, sustainability, bandwidth. All of these things are critical to the success of Ethereum, and they all are tied with Ether, the asset. What about the last point, activity? So by activity, I just mean the amount of flows that are happening on top of Ethereum. I'm thinking fluidity, liquidity, diversity, vitality, like all sorts of applications, millions of transactions per second, something very vibrant. And the only way that we can get there is with scalability. Now, the good news is that I believe we will be able to scale Ethereum roughly 1,000,000x. We have this massive wave of scalability coming. We have the surge is coming. And just to give you a little bit more detail, there's basically 3 technologies that compound on each other, each of which give us roughly 100x in scalability. So we have rollups that will bring us to 1,000 transactions a second. We have sharding, which was going to bring us to 100,000 transactions per second. And we have Nielsen's law, which is going to bring us to 10 million transactions per second. Nielsen's law is basically the equivalent law to Moore's law, but for bandwidth. And it turns out that bandwidth is the only fundamental resource that blockchains need to consume. Now, as we scale Ethereum by 1,000,000x, there's this concept of the ultrasound barrier, which is how much each single transaction needs to pay for Ethereum to remain sustainable, basically for Ethereum to have enough income to pay for its security expenses. And so the ultrasound barrier is going to decrease by roughly 1,000,000x. So right now, we need to burn in base fees roughly 3 million gwei for every single transaction. But once we scale things up 1,000,000x, we only need to pay per transaction 3 gwei to be able to be sustainable. And the good news is that 3 gwei is an absolutely tiny amount of money. It's 3 billionth of an ether. And even if this ether is widely successful, even if it's worth $1 million, let's say, 3 gwei would be still less than 1 cent. It would be $0.003, basically 1/3 of a cent. And so basically we're going to be in a position where Ethereum to remain sustainable requires transaction fees which are essentially noise, essentially just dust. Now, one of the exciting thing about Ethereum as a business is that the secure block space is big business, and it's been growing extremely fast. And this is basically the daily block space sales since the very beginning of Ethereum. And the y-axis is a logarithmic axis. So as time progresses, even though the per transaction fees might go down, in aggregate, the income should increase. And this is partly due to a concept called induced demand. As you improve things, as you reduce costs, then more and more users will come in, more and more decentralized applications will be built, and you're unlocking more and more activity. And I expect this to continue to happen. Of course, the block space is a very volatile resource, and so these peaks and troughs, they're highly correlated with bears and bull markets. And it could look like the aggregate fee volume has dramatically decreased by a factor of 100x, and it has, but 100x in the grand scheme of things is actually not much. Okay, so here's my last slide, and it's basically trying to give you a big picture summary, talking in terms of orders of magnitude, in terms of where I see a potential future for Ethereum. So I expect the supply to be roughly $100 million in the long term. So right now we're at $120 million, and the supply should decrease slowly and eventually in the equilibrium reach $100 million. Now, where will these 100 million Ether live? So they will live, partly as stake, securing Ethereum, partly as collateral, providing economic bandwidth for DeFi, and partly as currency. For example, Ether within exchanges like Uniswap or even centralized exchanges. If we have roughly 30 million ETH staking, that's going to lead to roughly 1 million ETH per year of issuance. And if Ethereum is going to be sustainable as a business, then the burn must match that at also 1 million ETH per year. Now, the income, what I expect is, remember the previous graph, I expect the income for Ethereum to be billions of dollars every single day in selling block space, even though the per transaction fee will be less than a cent. So this is the success for Ethereum, where we can get the best of both worlds. On the one hand, we get tiny transaction fees for one single transaction, but in aggregate, because we're doing 10 million transactions per second, actually Ethereum has a huge amount of income, and that allows it to have a huge amount of economic security. And then again, in the success scenario, I'm expecting tens of trillions of dollars of economic bandwidth for DeFi, and correspondingly tens of trillions of dollars of stable coins that are being traded on top of Ethereum. And I think if we do reach this potential future, then undoubtedly Ethereum will have succeeded in becoming the settlement layer for the Internet of Value. Thank you.
Amazing. Thank you, Justin. We do have some time for some Q&A, so if you have any questions for our speaker, please just raise your hand really quickly. We'll come in and give you a mic, so if you can raise your hand or stand up, we'll make it easy to find you. I have one question on this side. We'll have a volunteer just come to you right away. It's just behind you, sir. And other people will keep your hands raised, and there we go. Perfect. Let's make sure the questions are relevant to the talk.
Hey, Justin, thanks so much for making this talk highly approachable. Thank you for that. So I had a question with respect to, from your talk, what I would now call the illiquid premium. And I think it was actually in David's talk where he had a friendly ultrasound debate where he gave up essentially the point that liquid staking derivatives then I guess would reduce this illiquid premium. Could you potentially speak to that a little bit?
Yes, so I wouldn't have given up so easily for a couple of reasons. Like the first reason is that one of the main uses of the liquid staking token is to have leverage. And so what you end up doing is you end up locking this liquid staking token. And so that liquid staking token is itself not liquid. But there's maybe another reason which is more important, which has to do with the cost of money that I mentioned. So let's assume that the cost of money is fixed over time. Let's say it's 3%. The cost of money is going to dictate how much ETH is being staked. And what the liquid staking tokens do is they allow you to unstake immediately, as opposed to having to go through the exit queue. And you get this privilege of unstaking immediately by basically paying a very small fraction to market makers or arbitrageurs who will go through the pain of unstaking on your behalf. So you're going to sell, let's say, your one staked ETH for 0.9999 ETH, paying a little fee for the privilege of not having to go through the exit queue. Now, what will happen is that these arbitrageurs, they will go through the process of unstaking, but when they do that, someone else will come in and compensate for this removal of stake. And the reason is that in the equilibrium, the amount of staked ETH should correspond to the cost of money. And so even if there's like a large amount of ETH that unstakes, then in the equilibrium, more ETH will come in to bring things in. And so really, you can think of the total amount of ETH really as being this illiquid iceberg that is essentially impossible to melt, because if you melt a small portion, another amount of ice grows on the other side.
Awesome. We'll move on to our second question.
So in your future, why would there be tens of trillions of dollars of stable coins instead of Ether just having much less volatility and becoming like a stable coin?
Right, so you're really thinking ahead. So I'm thinking 10 years into the future, and I think it's going to take a long time to transition from fiat currencies that live in central banks to and commercial banks to basically stable coins that are settled on Ethereum. But I think you're right. If you want to think much further than 10 years, if you want to think 20 years, 30 years, 40 years, then maybe there is a case for Ether, the asset, to kind of be the stable money. I mean, one possible counter-argument here is gold, in the sense that gold never really managed to become this like perfectly stable asset, and it's possible that there will always be like too much volatility. relative to baskets of goods that people want to buy for Ether, the asset. So I think at the minimum, we have to go through a transition period where we have these decentralized stablecoins, and it's possible that even in the end game, Ether won't be stable enough.
And we have time for one last question, so I'll let David ask.
This is just to extrapolate on the last question. The debate was that Ether locked in the staking contract has always been a fundamentally bullish pillar of Ether. It's like the more Ether that's locked in the contract, the more scarce it is, more value it has. And then Jordy in the debate was like, well, all of these things are going to become staking derivatives so that you can easily sell. So there's no such thing as locking anymore. But the counter argument that I heard that I want to check with you, Justin, is that it doesn't matter whether you can easily sell it on the secondary market because the incentive to hold has always been through the yield. And
exactly.
you can always withdraw out of the staking contract. So
exactly.
is the 4%, 5%, 3% yield of Ether equivalent to just straight raw demand for holding this staking token regardless of whether you can unlock it or not? Are you saying that completely nullifies that
in my opinion,
argument?
it does, yeah.
Cool.
Yeah.
Awesome. Well, please give Justin a big round of applause. Thank you so much.
Thank you.
For our next talk, we're going to talk about how do we keep promoting the development of the Ethereum protocol. So for that, I'd like to bring up Trent Van Epps to talk about the Protocol Guild on how do we sustainably fund Ethereum development. Please give Trent a big round of applause.
Check, check. Hey, everyone. Oops, I think I left my water over there. Can somebody grab that? Thank you, everybody who's here to listen to this talk. Honored to be speaking at Devcon. I never really imagined I would be doing that a couple of years ago when I first got into Ethereum. So honored to be here and happy to educate or communicate what we've been working on here with the Protocol Guild. So the title of the talk is Funding Ethereum with the Protocol Guild. Like Kartik mentioned, my name is Trent Van Epps. I am a member of this guild. However, I do also work for the EF on the protocol support team, which is we work on network upgrades and generally coordinating the ecosystem around where the protocol is going and how we can improve this coordination process. So, brief intro. I'm assuming most of you are aware of this, but it never hurts to step back and think about what this topic is. So, Ethereum generally is a globally distributed computer that anyone can use, anyone can access. People can deploy contracts to it, they can send transactions and interact with it anywhere around the world. This means that Ethereum, the network, so mainnet is a screenshot from Etherscan there. This is a public good that users of the network can depend on and use throughout their lives. They can trust that it's going to be a resource for them. Nobody can stop them from using it. This is stretching the definition of public good a little bit because we have transaction fees, but generally we can understand it to be this. And if we take a step back, looking at the yellow paper, this is the Ethereum virtual machine. This is another public good that Ethereum developers, core contributors, they maintain, and many other chains besides Ethereum also use the EVM. So these are two fundamental public goods, infrastructure that people depend on, they build companies on, they store their finances on, and they're really important for people to actually have access to. And if we're thinking about the different categories, these can include, the research about where the protocol is going, the client developers who are implementing the protocol as it currently is, the coordination, like I mentioned, the work that I do along with many others to shape network coordination, and then there's tooling, so what developers actually use to interact with the chain. And then that brings us to the question of how are these areas of public goods funded? A big one is the Ethereum Foundation. You are probably aware of what the Ethereum Foundation is and what it does. It funds a huge number of initiatives in the space, sometimes through direct contributions, sometimes delegating funding to specific ecosystem groups, or things like the client incentive program where it gives ETH directly to client teams to run validators and it unlocks over a specific period of time. And then outside of the Ethereum Foundation, there's groups like Optimism, Giveth, Gitcoin, CLR Fund who run matching rounds, quadratic matching rounds, where the community can participate in actually funding these important public goods, things that people depend on. And then another smaller project, which you may not be aware of, is called Open Grants, which does vested ETH to specific groups. There's some projects that are using this to fund public goods. So yeah, there's quite a diversity, and I think this is one of the strengths of Ethereum is that it has a diversity of approaches. Kevin Owocki, formerly the founder of Gitcoin, had a talk earlier that I was on about practical pluralism and how important it is that we have these many overlapping approaches to how to fund these important initiatives, how to get funding to people who are working on infrastructure. And this is a great visualization of, I'm sure I'm leaving out some projects, so I apologize, but there are these projects on the slide and many more who do the important work of getting money to public goods, infrastructure, the developers who are actually building the things that we depend on. And I'll echo that by saying many community funding mechanisms are good. It decentralizes power and influence away from single entities. It celebrates pluralism, like I mentioned, prevents influence from being siloed with individual allocators, and it strengthens the intra-community relationships. However, especially the quadratic funding mechanisms, they often use similar curation techniques. For example, it weights the matching pool division according to how many people donate to a specific grant. And this is not to say this is a bad thing, it just, it can have a challenge when it comes to delegating funding or getting funding to areas of the protocol that may not be a fit for quadratic funding. Yeah. So the question is, how can we curate better, specifically related to the core protocol, and then even more broadly, how can we incentivize long-term core protocol contributions? So this is a big question that's been around as long as open source software has been worked on, and it's not a new problem for Ethereum. People have talked about it over the years. People join core development, they leave core development. It's something that will be with us as long as we're producing software and modifying the protocol. So these are the big questions that came to mind. Over the years, they've been a recurring set of concerns, and especially last year, in November, the discussion in the community began again about how can we properly incentivize contributors to stick around while also making sure that they're financially compensated. So when this discussion came up last year, there were my perspective of being around core development for a few years now and then working with core developers directly, some researchers. We started to think about what sort of challenges were most important to address when thinking about what sort of mechanism would be best to design. And I'll go through the first three here, just an overview, and then the next slides detail out what these challenges are. So the first challenge, curation is hard. The second, the incentives are imbalanced. And the third, contributor churn is bad. So the first challenge about curation, the ecosystem is very interested in sponsoring. This guy, the princess and the magician, the ecosystem broader, individuals, DAOs, protocols, L2s, they're interested in funding the core protocol, but they don't have a single mechanism to send funds to. There's sometimes projects will publicize their Ethereum address that you can send donations to, but it's not necessarily easy to find all of them in a single location. Similarly, protocol contributors are interested in receiving funding. Some of them may not be directly working for a team, but they're doing important infrastructure work. They're interested in receiving some form of financial compensation for the work that they're doing, but there's no single mechanism for them to plug into and be recognized for their work. And then on top of that, some of the existing solutions favor teams due to the difficulty of curation, like I mentioned. the solutions favor teams, and it's really hard for them to surface many individual contributors, for example, in a grants round. And we can't expect a single organization to that's outside of this core development or this core infrastructure to effectively curate the work that these people are doing. You know, it's very deep technically. It requires you to sort of be embedded within that work, and it's not reasonable to expect a single organization like Gitcoin to really effectively curate who's doing the work at the core protocol and how they should receive the funding. So the response to how to address this question is we should designate a contract on-chain that is regularly updated by the members themselves. So people who are doing core contributor work, they're updating this membership registry. The second problem is that the incentives are imbalanced. So this is maybe a little self-explanatory, but I'll go into it. L2s, DeFi projects, token projects, things that have equity, there's a stronger incentive for people to go work on them rather than the core protocol. And this is completely rational. You know, if you're weighing your options here, Ethereum just doesn't have token incentives or equity or anything that can similarly be offered by applications or L2s. However, it still needs to attract and retain talent to evolve the protocol. You know, Ethereum is an infrastructure in flux. There's a lot of changes that we'd like to make to better scale, to become more secure, and we need really smart people working on these problems. But we should be compensating them fairly. It's totally rational to pursue something with you know, greater financial upside, and I don't fault people for that, or for other protocols leveraging these incentives. However, as the broader ecosystem continues to grow, competition for these talented individuals is really going to only increase. Of course, financial motivations aren't the only or best motivator for people. We just want to recognize that it's just one tool in our tool set that's being under-leveraged. So the problem of imbalance, we can address this by tapping into the financial value that all of these amazing projects are building on top of Ethereum and getting them to contribute some of them back to the people who are working on the core protocol. The third challenge, excuse my rushed graphics here, but the contributor churn is a challenge when it comes to the core protocol. It can take 6 to 12 months for somebody joining a client team to really start to understand how they can contribute to the client effectively and start making meaningful impact on the work. So there's a steep learning curve for new contributors to deliver value. However, the contributor value does grow over time if you stick around. But there's less incentive to stick around if you're, once you're an expert, you sort of reach a certain level of expertise with a client code base, for example. So one of the things we thought about how to address this contributor churn is that membership eligibility to any sort of public goods funding mechanism. It should only be after 6 months of regular contributions, and that assets should vest over time in order to incentivize this this knowledge transfer between different cohorts, different generations of people working on the core protocol. You know, there are some amazing people doing work today that maintain clients and make Ethereum infrastructure and the protocol possible, but eventually they're going to move on or retire if we're still around in so many years. And we need to make sure that the next generation of people that are going to be maintaining this software are ready and incentivized to stick around similarly. So, as you may have guessed, I'm describing the Protocol Guild, which started as an idea last November, and we've been building it since then. We worked with a team called 0x Splits to design, well, they already had a split contract, but we worked with them to design a vesting contract. And it's a collective of today 119 Ethereum contributors, and we're working to rebalance the incentive, address all those challenges like I laid out in those previous slides. And here's a very simple diagram. The sponsors, these can be anybody in the ecosystem, individuals, projects, large scale, small, doesn't matter. Anybody who's interested in giving back to a really highly curated set of core protocol contributors, they send funds in whatever form they are to a vesting contract over a certain amount of time. Then it goes to this weighted registry, which is regularly updated by the membership itself. And that's the key, that it's self-curated, because you know you have a really high signal for the membership and the fact that you know that these are people who are doing really crucial work. I'll dive in a little bit into eligibility and self-curation. Like I mentioned, to be part of the protocol guild, it has to be, you know, something beyond a typo in a client code base or something. And beyond 6 months, we want to make sure there's a high threshold for people who are actually really committed to this infrastructure work. And touching on self-curation again, the reason this is super important is because it avoids intermediation between external curating entities, which may or may not be really close to the work that people are doing. So, like I said, you get a really high signal curation, and you can be assured that this is going to be consistently updated over time with membership that's really contributing to the core protocol. And it's incentive compatible because adding new members dilutes existing ones, so you don't have to worry about new members just adding anybody in the ecosystem. There's a cost to properly curating. However, if eligible contributors are not being added, then it removes any legitimacy that's built up over time, and external funders won't continue funding this mechanism. So we hope that these are sufficiently balanced against each other, but this next year is sort of a learning period. It's a learning period, so we've launched a one-year pilot to test out the assumptions about the challenges that we wanted to address, as well as the assumptions about what the best ways to approach them are, how long should vesting be, things like this. So we're working on that. We launched the protocol itself in May of this year, and it'll run until May of next year. And so far, we've raised 11 million in sponsoring assets, and like I said, these will vest for 1 year over time, again, to incentivize long-term contributions, knowledge transfer between different cohorts of core contributors. And it's been very awesome to plug into existing funding infrastructure to touch on this idea of pluralism in funding. There's a Gitcoin grant. We've tapped into some DAO treasuries who fund back in their native token. So shout out to the people that have funded, including Uniswap, Lido, ENS, Nouns DAO, to name a few, as well as this norm that we want to pursue of one way to scale the incentive, the treasury, to build the norm around allocating a % of the initial supply or annual revenue. So again, another shout out to TrueFreeze, Gnosis Safe, and TexturePunks, and NFT project. They've committed to contributing some of their revenue. And over time, we want to build this more and more. We're not saying that this is the only or best way to fund through initial token allocation, but we're very excited to explore this with the broader ecosystem. We're already starting some discussions with L2s about how they can directly fund this incentive mechanism. And one thing we really want to be intentional about is documenting the outcomes to see, does this really work? Does this increase the incentive to contribute to the core protocol? And we hope it will, but we want to make sure that the community hold us accountable and we really iterate and improve the mechanism over time. One of the cool things is, because this is all on chain, anybody can track it. So if you go to Dune Analytics and search Protocol Guild or something monkey, sorry, I can't remember the name of the contributor, but we've been working with someone to put together this dashboard, and anybody can track the finances of this on-chain protocol incentivization mechanism, which is pretty amazing. You can see the membership, the total weighting of their share of the proceeds, who has contributed, really great data source, and awesome for transparency if anybody's interested in tracking that. So I'm ending a little early. If there are any questions, I'd love to talk with anybody who wants to learn more about the mechanism. If you're part of a DeFi project or something that's planning to launch a token, please do come talk to me or any of the members. There's a ton of core developers here who are part of this project. That QR code, I think, takes you to the docs or somewhere else relevant. So yeah, and then there's some bit.ly links if anybody's curious to explore more. That's my handle, and then you can follow the organization itself at Protocol Guild on Twitter. Yeah, so thank you for the time. Again, to the Devcon organizers for giving me space to talk about this. Public goods funding is incredibly important, and it's important to have also a variety of approaches, different curators, different mechanisms, so that we can make sure that the incentives to contributing back to the Ethereum protocol in the context of amazing application layer projects is maintained over time. So thank you, and I'm happy to take questions if there are any.
We have a question here. We'll give the mic to the gentleman over there. If you have more questions, please just raise your hand or get to the end of the line so we can quickly give you the mic. And let's begin with the question.
Hey, Trent. Thanks. Amazing initiative. Thank you for giving the speech. I had a question about the recent acquisition of Prism. I'm curious if you could comment on that. Like, obviously, on one hand, that means that there's, I guess, less pressure on the Protocol Guild to fund those developers. On the other hand, is that the kind of outcome that we strive for? Now, obviously, Arbitrum, they're a good actor. I think they have a great reputation. But one could think of some potential downsides. So I'm just wondering, how does the Protocol Guild feel about those kind of outcomes?
What sort of downsides do you see?
Undue influence. I mean, obviously, we have like 9 teams in total who are contributing to this, if I'm not mistaken. And so, you know, we trust Arbitrum. If they start doing some weird stuff, you know, there's other options for people to choose different clients. And obviously, if we have many more clients, their influence, you know, they won't really have an influence. But nevertheless, you know, they have certain interests. They might, like, they're probably going to launch a token, tokenomics, how do they pump their token? You know, these kind of questions.
Yeah, you definitely picked the hardest question, given they announced yesterday. So yeah, this is really interesting and digs into, it touches a lot of different areas about protocol governance, incentivization, funding the core protocol work. And like you said, I know them all personally, so I do have a bias here, but I do expect that they will maintain their neutrality. I can't comment super deeply on it, again, because it just happened and I'm still digesting, still understanding the mechanics of it, but I don't expect that there would be any undue influence exerted by the L2. And like you said, if there were red flags starting to appear, I'm pretty sure the community would call it out pretty fast, and either Arbitrum or the Prismatic team would adjust course pretty quickly. But yeah, that's the short answer.
I saw another hand. Do we have more questions? There we go.
Let's say someone's leaving the Protocol Guild. What's like the process for the offboarding? Like, do they have an amount of time, or has that been thought through much?
Leaving or joining?
Leaving.
If they're leaving, so they can claim any assets from vesting at any point, but there are windows in the contract. So once they leave contributing core protocol work, they won't receive future vesting, but they can claim it at any time. It's permissionless like that. Does that answer yes? Yeah, cool. Anybody else?
I have one.
Sure.
How do you think about deciding what should be funded, and how do you sort of, in a way, prevent or get ahead of not having favoritism kind of come into play?
Yeah. This is something that we've been trying to iterate on through the pilot, and one of the reasons we wanted to start really small. I mean, 10 million is, it may seem like a large number, but split between 120 different core contributors, it's not that massive. But we were very intentional about the amount of money that we're raising, and that's one of the main reasons, is because the eligibility framework isn't going to be exactly right the first time, and we're going to need to iterate on it. And so that's part of this pilot, is figuring out what sort of scope we want to take on. And I think what we've learned over the past 6 months since May is that it's probably better for a more narrow scope and to be as explicit as possible. So if you're working on a research team, if you're contributing to a client code base or doing coordination, we want to make sure that it's very clear that these are people who are contributing value, because if you aren't explicit or don't maintain rigor in the eligibility process, again, the mechanism will lose its value. It'll become a lossy signal for people who are interested in contributing to something that's going to get their money to go to the right place. So make sure that we're iterating and starting small is how we've approached it.
That's great. And just out of curiosity, did you kind of compare this thing with the retroactive funding model, and sort of what was kind of the pros and cons list that you made you kind of pick this model?
Sure. So retroactive funding is great in that we can also plug into that. However, these individual teams, they don't have to apply on their own, or because Protocol Guild is biased towards the individual, you can imagine it's sort of like a collective or a union that represents them and makes it very, very straightforward for people interested in funding, like Optimism's retroactive funding program. They can just point it to a single address and scale it accordingly, however much they'd like to give back, rather than possibly missing somebody who did crucial work over the past 2 years. They can rest assured that this is a mechanism that's going to be very, very tightly curated. But yeah, I'm super excited to plug into retroactive funding, continue to have a Gitcoin grant, things like that is all possible, and I'm sure there will be even more mechanisms in the future that are a good fit for these types of things.
Awesome. Do you have any other last questions? Great. Well, please give Trent a big round of applause.
Thank you.
We'll take a 1 or 2 minute break before we get ready with the next talk, so you can stretch a little bit, and we'll be resuming in 2 minutes. All right, we are ready for our third talk for the afternoon. And for this talk, I'd like to invite Alex to stage to talk about building blocks after the merge. So without further ado, please give a big round of applause for Alex Stokes.
Okay, hello, great. Let me put some water down and let me just check that this works. It looks like it does. Great. Hey everyone, good afternoon. I'm Alex Stokes, a researcher at the Ethereum Foundation. And yeah, you know, the title here says block building after the merge. There's like a subtitle, which is MEV moving forward. You'll see in a bit, I gave another kind of variant of this talk that looks at more, I'd say, like the technical side of things. And I hope today to kind of communicate like a sense of the landscape around this topic, and like MEV is like the obvious, you know, buzz phrase here. But yeah, so let's dig into what that means, and hopefully by the end you'll have a sense of, again, yeah, like the landscape and what some of the concerns might be moving forward. So I've kind of always said that putting currency into crypto, like cryptocurrency, is like this double-edged sword, because, like, yes, you know, there's like this like speculative aspect that draws a lot of attention, a lot of talent, a lot of capital to the space, and that's great. But in the same, you know, sort of in the same breath, that also means that we're kind of directly programming with incentives here. We have this sandbox for you know, playing with these different crypto economic games, and I guess hopefully you'll see as we move forward that you know, this could perhaps backfire. It could be the case that short-term incentives that are supported by protocols like Ethereum are perhaps too great for us to sort of resist. And in the context here, this is an important point. I say secure block space will be a premier commodity of this century. So maybe that's like a bit of a forward-looking projection, and maybe you don't quite buy it. That seems to be, to me, the direction things are going. I called secure here out in italics because some people say, oh, you know, you could just make a new L1. There's like as much block space as you need. But I will claim that, you know, there's different qualities of block space. Some is much more secure than others. So we have this thing, and if there's this thing called block space, and it is actually so important, it's going to be very valuable. And because it's so valuable, we should expect battles for control over block space. So this is like, if anything, the takeaway points. I'll just get it out of the way. And when I say this, I want you to think about, like, you know, influences both inside the community and outside the community. There's going to be all sorts of people who are going to want to like try to attempt to co-opt Ethereum. And you know, that can happen in very overt ways. It can also happen in very sort of subtle ways. So just keep this in mind. I think when we think about any of this stuff around the protocol, what it looks like, how the protocol changes, things around the protocol like MEV, and like a whole separate talk in this vein is like staking pools. But when you think about this stuff, just have an adversarial mindset and just, yeah, be careful out there. Okay, so I use this word block space. Maybe some of you have never heard of it. So what I really mean is just the stuff that goes into the blockchain. So today that's like transactions. If you ever used Ethereum or like MetaMask, you've done this. You like have this transaction, and maybe you sign it. Maybe there's some error. Maybe there's not enough gas. Maybe you didn't pay enough for the gas. Like a lot of things that happen. But you're probably familiar with this notion of a transaction. And so, you know, in the very sort of naive model, we have a bunch of transactions that get packed into blocks, and these blocks go on chain, so to speak, which means they're like accepted as canonical or, you know, part of the consensus, and then somehow this like moves the state of things forward. I have this like sort of elusive comment to say tomorrow you'll see in a bit that this notion of builders I'm going to sort of present today unlocks a lot of sort of abstraction and flexibility around how we use the protocol and how we like access its resources. And yeah, so maybe in the future it looks a lot more general than just like the transaction you get through MetaMask. But so concretely, like transactions are, you know, like the takeaway here is that transactions are a way to interface with the protocol's resources. And like what we really mean when we say that is like the state. Like The fact that Ethereum is organized as a blockchain today is like kind of a detail, it's like an engineering detail almost. Like the important thing that we all care about is the fact that there's this like shared global state. For example, the account balances of everyone in the protocol, the state of smart contracts, of Uniswap, of Aave, of Maker, and everything else. There's a lot these days. And the state is like the thing that is sort of the actual valuable thing, and you need block space to access the state. And this is what everyone I claim will be battling for control over. And it turns out that because block space, at least on Ethereum, is so valuable, it supports this ability to specialize. So what I mean when I say specialize is that we're seeing the emergence of this role within the protocol called a builder. And yeah, it's just this entity that says, okay, like rather than just like run a very naive algorithm for like getting these transactions into the block, which then goes on chain, you can do like far more sophisticated things. And if you're familiar with any of this MEV stuff, this is like one example. And yeah, it's like, I really think kind of the sky's the limit in terms of like the ingenuity people will bring to doing this task. And the takeaway here is that builders specialize in refining block space. So a hopeful analogy that I've come across is like thinking of, we have like, actually I think this, yeah. So a helpful analogy here is like, analogously to like mining some resource, like say copper ore. You have copper ore, you can like dig it out of the ground, you just have this like thing, you have to like get the copper from the rock and this whole process of extraction to get to say like refined copper, this copper bar in the middle here. And then that can be further refined into, say copper coins or pick your thing. So this is just like a generic notion of like taking some raw asset, some raw commodity, and refining it through like a series of phases. And at each phase, it's sort of like is more valuable than the phase before. So like, for example, if I just like walked up to you and gave you like a hunk of copper ore, you'd be like, okay, cool, but I don't really care. Whereas like if I walked up and handed you a bunch of coins, you might care a lot more. So this is what I mean when I say that there's this sort of raw asset, or this raw commodity is probably the right term, of block space. And again, what we're seeing is this notion of a builder in the protocol, or at least around the protocol, that takes block space and sort of provides these like value-added services or almost goods, you can think of them as, to go from a less valuable thing to like a more valuable thing. And that's the job of the builder. So now the question is, well, okay, yeah, what are some examples of things they can do? And there's actually a lot. So here's like a list of things. There's a long list of things. Again, this is where I think all the ingenuity and creativity will come in that I think is really exciting around this space. And I'll just run through some of these examples here, right? So like one of them is like sponsored transactions. This is something people have wanted for like a very, very long time. And the idea is that basically you have this builder and they pay for the gas. So kind of concretely what that looks like is, I have my transaction. Rather than making like a direct Ethereum transaction, I make some intent, some message, something the builder knows how to like interpret in their own way that still has the same effect on chain, but then they can be responsible for paying the gas and like in protocol. Another thing they could do, instant confirmations. So this is again something, if you've like, going back to our MetaMask example, you might have seen where you send a transaction and you have to sit and wait, and it's like, is it on chain yet? Like, what's going on? Like, sometimes, especially when there's like volatility and like the gas market and things, like it can be very unclear what's happening. You can like end up waiting a very long time, and that's not fun. But there's this almost service or abstraction a builder can provide, which is just to say, okay, you want this transaction to be in this block, and I can basically, as a builder, say, I promise you this will happen. Trust me, and there's a whole design space around, changing what trust me means. But basically, I can give you those promises as a builder to get into that block. And in that sense, then I can turn around and immediately say, yes, you're in the block. Related thing, cancellations, retries. So the notion here is just saying like, yeah, let's say I make a transaction, and I'm like, oh wait, like the market just moved against my Uniswap trade. I'd rather just take it back. If you're just sort of sending raw Ethereum transactions today, that's really hard to do because you like gossip them through this global mempool, and you have to like, yeah, it's tricky. One way people kind of game this today is they will send a duplicate transaction or one that will overwrite the previous one that has different effects. But again, that's like inefficient. And you can imagine there's like this layer around the protocol that handles this for you. And like in the same bucket, there's like retries. So like, let's say I want to like, I don't know, do a token transfer. And for some reason it fails just because of like conditions on chain. So then I want to keep doing this, you know, until it goes through. And rather than me have to sit and do this, like a builder could do it for me. Next one, gas futures. So here, the way to think about it is that rather than selling you sort of like block space right now as a builder, I could sell you block space in the future, which is a pretty cool idea. And one reason you might want to do this is because, you know, as part of this like contract that we enter into, you're also selling me at a certain price. So even if like the gas market moves against me, I've still locked in a price that's nice to me. And builders could do this. I mean, there's other ways to do this on chain with like looking at the base fee and stuff. But yeah, so just to give you a flavor again of what builders could do, sell futures around block space. This was an idea I heard from Hasu. You could basically also sell block space in the past. And I won't go into too much detail here because basically what this means is like selling reorgs, which is probably something we shouldn't dig into too much. There's like some, I'd say, moral hazards around it. But the symmetry between selling block space in the future and the past is like, I think, too nice to pass up. Another one is just like this whole bucket of account abstraction. You might have heard of EIP 4337. And basically, again, it's just this way to like add more flexibility around the core protocol so that people have more, again, flexibility and how they use it. A simple thing would just be like a different signature scheme than ECDSA. And then this last bucket, MEV, I'm sure you guys have heard about this a ton this week. And you know, if you think about extraction as like the service a builder could add, or, well, there's a couple different things, but if you think of extraction, then there's like this whole bucket of, you know, we can kind of just shove MEV into this whole notion of like a builder providing the service to users, whether that's searchers or someone else. And so then I have a few examples within, you know, sort of that subspace. MEV extraction, which is what you usually think of when like a searcher's running some ARB. MEV smoothing, the notion here is basically, you know, MEV is very spiky, and so instead what we could imagine is somehow capturing it within the protocol and smoothing it out over time, and it's paid out to builders, to proposers, however that looks. That'd be pretty cool, and you know, you could imagine off-chain constructions that do this, that builders offer. The last one is like MEV protection or rebates, and the notion here is like builders kind of would have this direct pipeline to the protocol, and they could say, hey, I promise to keep your transaction private, so it can be, for example, front run. So there's a lot they can do, is the point. And again, there's a bunch more. Okay, and then like even looking a little further forward, I'll just touch on this. So these are like, you know, this list here I think is like pretty concrete things you could do today. And I do think this is painting a picture of this builder as this like generalization that we'll continue to see in the protocol. For example, you could have, rather than transaction level 1559, you could do it at the block level. So today, when you like send a transaction, you basically have to like have some amount of ETH that you burn. But if you think about it, the economics are the same if the builder of the block burns the same amount of ETH across all transactions at the end. And the reason you want this is because, again, there's like better UX for users. They don't necessarily need to have ETH. And yeah, again, this is a generalization of like the protocol providing resources and then the user consuming them. And then a similar thing is rollups consuming blobs in 4844. So you might not know about this EIP, but basically the idea is we're going to add a bunch of like data space to the protocol for users like rollups. And again, it's like we don't want rollups to have to necessarily like sit and like manage blobs and figure out when they get on chain and things like this. And so you can imagine there's a builder or some sort of abstraction, like a builder that manages getting blobs from rollups or from sequencers of these rollups onto the chain. Here's another talk. I'll just quickly point out where the one I mentioned previously, where I went into a lot more of these use cases in depth. You could welcome to check it out. So this sounds cool. You know, I am claiming there's this builder thing and it gives you all this functionality, and that's great. But what's the catch? I mean, there's probably a catch. And the catch is that the specialization actually implies validator centralization. And this is bad because it kind of harms like the whole health of Ethereum. Like the reason we care about Ethereum is because of this centralization of the consensus, right, of the protocol. And builder specialization harms us directly. So let's look at why. And why is that, this process has economies of scale. So right now, the builder protocol, or sorry, the builder role in the protocol is tied to the validator role. And because of that, you could have builders that do their things. You'll have entities that sort of have validators they partner with to do their thing as builders. And what happens then is better builders have better profits. And this makes this flywheel where they have better profits, they can get better at building, they can scale up their validation operation. And you just get this, again, flywheel that goes until suddenly, you have these, really huge actors in the protocol. So again, if you're, the best builder, that's great for you. But if this, goes unchecked, then it's actually really bad for the protocol in the long run, because now you have this, very fragilizing thing of this, one huge actor that's, easier to, say, attack and all sorts of things. So just a note, MEV kind of directly accelerates this problem, which is probably why you've been hearing so much about it this week. So, okay, what can we do? There's a couple things. One of them, proposer-builder separation. Barnaby gave a talk about this yesterday, I believe. And I mean, the idea, I think, is pretty straightforward, just from the name. I mentioned that this builder role and sort of the proposer or validator role, the thing that actually is minting the block on chain, these are tied together. So instead, we can just separate them. And this sounds great. The question, though, is how exactly you do it. And once you start looking into this in some depth, there's a bunch of subtleties and open questions that have a lot of nuance that still need to be worked through. So, for example, I think the leading design right now is from Vitalik, where basically we have two slots, alternating proposer and builder. And the point here is that you want to have the proposer do their thing, in a different context, have the builder do their thing, and it sort of firewalls these two entities from each other. And that's great, but then you have to make sure that it's incentive compatible. You don't want a proposer to release their block too late after they've accepted a builder's bid, and then because of that, the builder doesn't have time to reveal their block, and it quickly gets to a lot of tricky situations like that. Another one is actually deciding the mechanism of sort of selling the block space that a validator may wish to do. The default thing we do is just enshrine an auction. But then the question is okay, is that what we want? Do we want this thing where it's I'm going to auction off my block space to the highest bidder? There's a bunch of different ways to think about this. I will call out, again, Barnaby's very recent post on ETH Research, unbundling PBS, and he talks about kind of maybe pulling the auction bid out and just having sort of this notion of a commitment market, where the commitment then is quite general. Another point then is just the integrity of this thing, because kind of I alluded to, there's many actors now, and they all have different incentives, and you need to align them in the right way. If you don't do this properly, then, well, yeah, if you don't do this properly, then you could imagine people just not using it. So one way you could fix that is you have a testers go and also test the chain. If there's this two-slot process alternating, you can have the testers test what they see, and in that way they strengthen, again, the mechanism. But then it's okay, maybe they could be bribed, who knows. So point being, there's a lot of open research questions there. Oh no, my emoji didn't show up. Anyway, it turns out that that's not the only problem. So even if we had a great PBS solution, I think the way to think about it is you firewall off all of this MEV, all this builder stuff from the validator set, so they don't have these pressures to centralize. That's great, but then you kind of kick the can down the road, and there's another problem where, again, you really just kick the can down the road to the builders, because now the builders themselves could centralize. So we don't want to get to a world where there's a few actors, let's say very sophisticated actors from TradFi, who are here and sort of gatekeeping access to the protocol. Again, it'll be a way for them to again violate Ethereum's values, and that would be very bad. So I think it's even less clear how to handle this, just because the scope of the problem is so big. If you thought there's incentive issues with the previous sort of proposer builder siting, there's now it's, I would say, even less constrained. So that's fun. And okay, let's think about this for a second. How do we fix this? One option is just to say, okay, we will have very centralized builders, but we just want to make sure they can compete. And the idea is that if there's very healthy competition, then there won't be one entrenched player, and that avoids the situation where there's this very direct gatekeeping where I have to go through one or two entities to get on chain. So to do that, we'd want to keep the barriers to entry of building very low. And yeah, maybe that's enough. We'll find out. But still, you know, I think if you look around the world, you see there's like power laws everywhere. And so I think we'll still be, you know, even if we do have a healthy ecosystem, it could be the case that there's like not a great distribution. So we can ask, well, what next? Well, pretty much most of us here, we can call ourselves crypto economists. So we'll design a mechanism. And what does that mean? Well, we'll just read off this quote that I made up. What does it mean to design a mechanism here? Well, we want a peer-to-peer network with proper incentive alignment to ensure safety and liveness of the protocol. And now what does the protocol do? Well, it facilitates the refinement of block space in this way I was describing. So that's great, but there's some like huge caveats. The huge caveats are, we want to make sure that, well, I think there's many, but like 2 ones to call out, right, are that the people who are using this thing, like let's say users who want to like make some trade on Uniswap, we want to make sure that, you know, when I make a transaction and, for example, it has some MEV, then like I've actually generated value that wasn't there before. And it seems, you know, I think we'd all kind of agree it makes sense that the generator of that value should capture most of that value. So that's like a pretty big constraint on how something like this block space refinement decentralized protocol would look like. Another big one, censorship resistance. If you've been following any of the Mev stuff, which I'll touch on in just a second, you see that this is like a very critical question because, again, when you have just a few sort of, I mean, yeah, centralized pipelines in the protocol, it becomes much easier for censorship resistance to fall by the wayside. So I'm just going to keep going down. I kind of want to just like sketch this path for you, hopefully to jog some of your, maybe like capture some of your interest or, you know, jog your creative juices. But essentially, what would decentralized building look like? I mentioned this SBC conference. Vitalik gave a talk on this a bit, so I'd also recommend that one. So, but yeah, so for today, the ways I've kind of been thinking about it lately are you have a builder and you want them to basically, well, yeah, so there's different contexts. The first context would be in a single domain, and I'll kind of make that clear in a second, but essentially you have a builder, just imagine a builder on one chain. And rather than this builder being like one server somewhere, you can imagine it being split across many servers, sort of implementation-wise. But anyway, so that's actually not what we really care about. Like we care about higher level properties. Like we want this builder then to be able to, again, be like multiple, maybe competing entities. And so what that could look like is you have agents who are doing the building, and they're now competing for like order flow, for example. So if this is like an MEV context, you have people who are making trades, and I'm now like working or perhaps competing with other searchers, let's say, to build the best block. But we're doing it in a way that, again, we sort of enforce this competition. I think the more you think about this, there's like a trade-off between privacy and execution, because, you know, one thing we could say is, as a user, again, of my DEX trade, for example, you know nothing. And then it's just like grabbing random batches of transactions and like putting them into a block. Instead, you could like kind of be in the setting today where you see everything, and then you have sort of full information to even leverage against me. And when people are front run and they're upset about that, this is exactly what the tension they're getting towards. If you're familiar with CalSwap, so like one idea here is like the builder on a single domain context is you have, you know, imagine doing your DApp, your DeFi DApp, but inside some APC circuit. CalSwap has this thing for basically settling trades off chain before they land on chain by just doing just the diffs or just like the remainder. So it could be a cool research direction. Another one, there's this DApp, I guess, maybe application, maybe protocol, but either way, it's called Rook. Used to be called KeeperDAO, I think. And either way, at a very high level, how that works is that they have like a trusted set of searchers who have access to a private mempool, and because they're trusted, you know, we trust them to then search and extract MEV, but do it in a way that for the value extracted, most of it flows back to the users of Rook. So what this looks like is you have trades where you're paid to make the trade. You can do something like this, and then the question then is like, how can we tune this like trust spectrum so that we minimize trust while giving us all the nice properties we want? Another cool thing now is like, you know, there's not just Ethereum, there are other blockchains, and so now we can think about MEV in like a cross-domain context. And this one quickly gets pretty hairy because like, when you think about it, you kind of now, like if we're going to do this decentralized building thing across chains, then you now need to like I mean, yeah, it's not even really clear how you do it. Like you could imagine like some cryptoeconomic layer, whatever that looks like. Maybe like a network of state channels. Maybe it could look like, yeah, I don't know. Again, this is where it's an open question. But there's a lot of things you could do. And yeah, so I think we'll see a lot of exciting research come out of this area in the future. So yeah, I think I've just tried to like lay on a lot of problems, and maybe this seems like pretty hectic. That's not good. But yeah, like I do think these questions around like the builder and like how the protocol is used moving forward are like some of the biggest that we face as a community. So I do want to call them out, and yeah, just be aware that there's a lot of thorny issues here. So hopefully you are motivated to work on fixing them. And yeah, like I'd like to like end on a good note. Like we did the merge. You might have heard of that one. And you know, really, this is like an existence proof that like progress is possible. Like I'll steal a quote from Danny Ryan, quoting Albert Nee, who said that Ethereum is like an intellectual gravity well. And yeah, I mean, I think that's the case. Like Ethereum is like a really outstanding community, and I think that we're able to sort of adapt to whatever comes our way. So I think good things are possible. I'm running a little short on time, so let me see. I think I just had a few slides. So, yeah? Thank you. Okay, my problem. Right, so just a few more slides. And the first one is I just want to, again, call your attention to like, yeah, how can we actually start to work on these issues? With this problem of validator centralization, like, yeah, just supporting R&D towards PBS. I think there is some like nice PBS solution that we could get to. And we may realize that there isn't one, and that's also great, but the work needs to be done, and we'll see what happens. In the meantime, we have this thing called Mev Boost. So there's like an off-chain implementation of PBS stewarded by Flashbots and many others now. They've recently made a call for like open stewardship of the project. So that's a great way to get involved. I've called out the GitHub repo for Mev Boost. There's also some stuff around how this interface between the core Ethereum software and this builder network works, and those specs are under this builder specs repo. Some things that that community will be looking at very soon is like addressing censorship resistance. I'm also working on this notion of a relay monitor. There's this like very trusted actor in Mev Boost right now called a relay, and they can kind of do some bad things. And the idea of the relay monitor is to add some like automated monitoring to figure out when they're doing things we don't like, and that then will feed back into Mev Boost to hopefully make the situation a bit better than it is today. If you're interested to help, there's a repo there that I have, and please, I would love contributions. And then yeah, I mean, you probably get the sense that this like builder centralization problem is maybe even poorly defined. Like I think that's the first place to start there, is just like defining exactly what we mean, because I think it's like a big umbrella for many things. You can start pulling a bunch out of it. Maybe if we can like define the problem, we can start cutting into smaller pieces that are, easier to make progress on. For example, if we do some sort of like MPC or like some crazy state channel thing, then how far can we push the cryptography to like actually get the properties we want? How could we like now in this like very complex system address or analyze all the incentives to figure out like, okay, does this mechanism actually work? And I think so far Flashbots has done a lot of the thinking here, so I just wanted to call out them. They have a forum at collective.flashbots.net. And if you're interested in thinking about this, reading about this, research, and things like that, check that out. And that's it. Yeah, thanks. There might be just a few minutes for questions. And yeah, if you want to get involved, just here's my Twitter, and I'll answer any more questions you have, direct you to the next step, all that.
Awesome. We can ask 1 or 2 questions. If there's any questions, just raise your hand quickly. Make sure it's a short one. We'll pass that mic over there to you in a second. Just over there.
Hey, my name is Murat. I'm part of Block Native. We build a lot of blocks. Flashbots has a great searcher reputation system. I mean, we can talk about it, how great it is and whatnot, but I'm wondering if there's a reputation system that we can come up with within the protocol for block builders in the future as well.
Right, so I would push back immediately and ask how much we want actually in the protocol. because like once it's there, it's like very fixed. But yeah, I mean, again, like a lot of these, I think more like research or like even less formed ideas around distributed building need to take things like that into account. Like you're going to have some actors who are like helping the builder do their job, or you can even think like the searchers are the builders in this context. And yeah, like that's one way is like, ideally we could have some cryptographic mechanism where like everyone does like perfect searching and like users get all the value that is allotted to them, and that's great. I don't think the cryptography is there. And then perhaps it will be one day, but not today. So then yeah, we'll then rely on like trust, reputation, things like this in the short term. So yeah, I mean, it's definitely a very interesting place to look at.
Amazing. That's all the time we have for questions, and we're ready for our next talk. So please give Alex a big round of applause. All right, next up, we have a really interesting topic. We're going to talk about a theory of MEV, and to talk about all of that, I would like to welcome Tarun Chitra from Gauntlet to be on stage. So without further ado, please welcome Tarun on stage.
Hello. So, I probably don't need to talk about what MEV is as much, given that there were, if I remember right, 17 or 18 talks about MEV. But, I think in the spirit of trying to understand the incentives hidden in a lot of these systems, one question you might ask is, does there exist sort of some type of formal theory for MEV? Does there exist some type of mathematical structure to this thing that seems to be, captivate people's imaginations, yet no one can describe it? And so I'm going to talk a little bit about different ways of addressing this problem, including some work we've done. And I like to call any analysis of MEV sort of measuring the cost of feudalism. So that's sort of where the title comes from. Cool. So let's start with the operative definition of MEV. You know it when you see it, like of course, the famous Supreme Court ruling on porn. MEV comes in many shapes and sizes. Of course, we have everything from sandwich attacks, liquidations, arbitrage, NFT front running, and cross-chain. And as you can see, it's sort of quite a variable form of revenue for validators and searchers. And somehow, because we know there are many examples and we feel like we can't even enumerate all of them, it might feel like the space of all MEV is super big. So how do you analyze it? Well, I know there were 2 talks yesterday about what is and isn't MEV, but I think we're going to focus on kind of an operative definition that can be used. And we could sort of say MEV is any excess value that can be captured by validators by reordering transactions, strategically adding or removing transactions. And the idea is most of this is currently managed via off-chain auctions. So people bid on transaction priority, atomicity, within bundles. If we take a step back and look at the history of Ethereum as to why we got to the auction world, part of the reason is the blockchain was just getting spammed by people doing liquidations and backrunning oracles, and instead of normal users being able to get their transactions in, you'd have the entire blocks filled with people's spam backrun transactions. On the other hand, of course, as the previous talk was focused on, there's a lot of centralization risk with off-chain auctions. So let's try to maybe schematically look at how MEV works. We have users who submit transactions, which are the deltas. We have a mempool. The searcher has sort of their own view of the mempool, and maybe they have some transactions that are directly given to them, which people would call private order flow. And then the searcher sends their bundle, which they're willing to pay for, to the validator, and the validator adds it to the block. So the philosophical question here, though, is how do we know value captured by MEV is excessive, or in a notion of excess? In this sort of first definition, I said any excess value. Well, how excessive is excess? So describing value flows in MEV is actually quite difficult. So in algorithmic game theory, you usually have two main ways of thinking about the world. One is optimizing social welfare. Social welfare means if everyone has some notion of utility, some notion of how happy they are with the world, you want to maximize the sum of everyone's utilities. On the other hand, revenue is, you know, the person selling the good, you know, maximizing how much they earn. And in cryptocurrency, it's actually interesting that you have to optimize both jointly. So obviously, user welfare is important for the success of any network. I don't need to really convince anyone of that. But validator revenue being optimized is actually important for economic security. If validators are not making sufficient income from it, then they're unable to really secure the network. And in decentralized networks versus centralized networks, these are two competing goals. And I think the one reason there's a broad view of how theory, you know, algorithmic game theory, it's different for crypto, is that you have to sort of balance these two goals instead of trying to optimize one of them. So what pieces are sort of missing? So how would we kind of describe welfares? How would we describe revenue? You know, one thing is understanding the user's utilities. What is the user getting out? What is their individual notion of value? And that can vary over the entire network. The other thing is some notion of transaction fees and payments, that, you know, the distribution of payment sizes that users are willing to handle. And the last thing is an understanding of how an auctioneer, so in Flashbots or, you know, in PBS, how they allocate block spaces to users. And that last part is actually quite complicated, and these three things are quite entangled when you want to try to write a mathematical theory for MEV. And these sort of things actually depend a lot on the application, right? The user's utility for minting an NFT is extremely different for a user's utility for borrowing against some collateral. And inevitably, that means that the allocation mechanism should somehow be tied to that. Okay, so let's try to do kind of like the ELI 5 simple version of this, which is, you know, we have a notion of block space, which is sort of a notion of max number of transactions or slots or size or gas. You can choose a unit, but for simplicity, just assume there's sort of some fixed number of units. There's sort of a notion of a binary allocation to a user of whether a particular user gets a particular slot. The users have the utility functions. I'm unspecifying the domain and range because, of course, it's actually quite complicated in a world of cross-chain bridging. And we see here that social welfare is defined as sort of the expected total utility of all the users given an allocation. So these X variables are effectively whether that slot is given to a certain person, and this is sort of measuring their sort of net happiness, let's say. Revenue, however, is just the expected value of the payments. And notice these are quite different. In particular, the social welfare includes the utility of the auctioneer, which means that all of the payments that the users send are subtracted, or sorry, are negative terms for the bidders, and it's a positive term for the auctioneer. So the payments cancel out in social welfare. So you have no dependence on payments explicitly. Whereas in revenue, of course, you depend on payments. So, you know, if we wanted to try to formulate what is an economic equilibria for the system, you might say, okay, well, let's try to find joint maxima of the social welfare and revenue functions. However, given an allocation that optimizes social welfare, it implies a set of payments. And it can be true that the payments that you get from optimal social welfare are very far from the payments that you get from optimal revenue, right? That there's sort of some intuition to that, right? Like if Flashbots just basically gave every bundle for free, obviously there's a lot of user gains, but like, you know, the auctioneer is pretty pissed, aka the validators / miners. And this happens all the time in MEV. The idea that the optimal revenue equilibria and the optimal social welfare equilibria are sort of disjoint. So, you know, the name cost of feudalism is really a pun on the concept of the price of anarchy, which is sort of a common concept in algorithmic game theory. Roughly speaking, you can think of the price of anarchy as if I have a set of many equilibria, I want to look at the ratio of the worst case behavior of an equilibria to the best case behavior. It's an approximation ratio. And so what this, for instance, this formula says is, what's the worst case that the equilibria, the payments earned by the validator, deviate from the payments earned at optimal welfare? And what's the best case, and what's the ratio of those? And you could basically think of this as, if this is really large or depends on the number of transactions or users, that's really bad. And so, you know, tongue-in-cheek, you know, of course, nothing in real life is asymptotic, but, you know, I feel like these are good heuristics, which is constant price of anarchy is really good. It means that even if you get to a shitty equilibria, it's not that much worse. It's not that much worse than the best equilibria. If the price of anarchy is weakly growing, so little o of n, so like maybe it's logarithmic in the number of users or slots, maybe it's square root of the number of user slots, that's okay. You can deal with that. And if the price of anarchy is linear in the number of users, that's horrible. That basically means that the more users join the system, the worse the equilibria is for everyone, which is like the opposite of a network effect. It's like the anti-network effect, right? No one wants that. And the interesting thing is that this quantity, if you try to write it out, depends a lot on your choice of how you, what applications you're modeling, because to compute the prices, you need to sort of know these utilities of the user, and that, of course, depends on application. And not to keep belaboring that point, but I think that one of the reasons MEV has this, you know, both memeability and inability for anyone to write down equations for it is because it's so dependent on the application, which is something I think, you know, the early designers of cryptocurrency networks did not, you know, divine at that time. Okay. So let's go through an example, a stylized example of kind of what this looks like. How would you analyze this for AMMs? So there's a very famous paradox in algorithmic game theory called Brace's paradox. And Brace's paradox is really about how traffic flows on a network. So we have this network on the left, and we have a source city, S. We have a destination city, D. And imagine that there's a bunch of traffic that needs to go from source to destination. Each edge that it takes is a latency. And so when you see a latency of 1, that's sort of like a link that can take arbitrary capacity. It takes the same amount of time for everyone to cross that link. When you see a link of X, it's dependent on the amount of flow in that network. So you could basically imagine that, say we have 100 cars, if 100 cars all go down the route X, then it's proportional to the number of cars that are going on the route. And so what you can do is you can say, hey, what if everyone is selfish or greedy? They're not cooperating. They don't have Google Maps. So Google Maps effectively gets you around this because it sort of implicitly coordinates people, whether you're thinking about it or not. But assume everyone's selfish and they know this map. How would they choose which path to take? And the thing you can show is basically they would split themselves up 50-50. The traffic would go half on the upper path, half on the lower path. And so the time it would take is 3/2. You know, we choose some units such that X is from 0 to 1. On the other hand, you might think that adding more roads always, you know, decreases traffic, and this is not true. So there's this interesting thing of if everyone's selfishly optimizing, if you add a link between the two middle cities that lets you teleport, then everyone just takes the X middle link X path, and the total congestion that everyone realizes goes up. And so this sort of, you know, paradoxical behavior, I think philosophers would not call this a paradox, but economists call it a paradox, is that, you know, even though you added a road, you've actually worsened congestion because people aren't routing themselves across the network well because they're not coordinating. So you might say, okay, great, what does traffic have to do with crypto? Well, you know, first, before we even get to that, you may think MEV is always bad. You know, there's always these articles that people are writing that are like, front running is theft, it's bribery, it's, you know, whatever. You will pick your favorite negatively connotated weasel word. And you might just say, okay, like, yeah, we need to get rid of it at all costs, instead of thinking, hey, maybe it's just endemic to such systems. So, you know, we saw Brace's paradox, and what we're going to see is that for some examples of applications in crypto, you can get around Brace's paradox by having MEV, which sort of says MEV has some positive externality in some situations, which is, you know, the opposite of front running is theft as a service or whatever. And again, not all applications are the same, so that's where the conundrum in defining your sort of optimization problem shows up. Another thing that's actually really important to pay attention to is if we classify users into two types of users, strategic users who are MEV searchers or people who are trying to optimize routes on chain, and non-strategic user like the person who pays 80 bips for a MetaMask swap. If we kind of look at, you know, those two sides, routing is actually one of the hardest problems for non-strategic users. So non-strategic users actually, in fact, outsource that to third parties right now, right? So if I want to trade token A for token B, but there's no pool directly from A to B, or there's not enough liquidity, you know, I go to 1inch, Matcha, Gem. I'm including Gem from the, you know, you could argue NFTs have the same properties. And, you know, routing is actually quite complicated. So, you know, algorithmic game theory has studied routing. In fact, Brace's paradox is a great example of how to study routing. And one question you might ask is, hey, does this apply to AMMs? Does this apply to 1inch? Does this apply to Matcha? And the interesting thing that you'll see is now imagine in this prior example, instead of teleporting in the middle link, we actually add a small amount of congestion, epsilon times the traffic. Now you can show the equilibria basically approaches something, as epsilon gets really large, you go back to the condition where everyone routes themselves across the two paths. And when epsilon's really small, you get back to the purely selfish thing. And the idea is the MEV searchers are actually adding this extra epsilon so that people route themselves across the graph more efficiently. And that's something that's a weird positive externality that if you write out the math, you know, I tried to not add a lot of the equations to this talk, but if you write out the math, it's actually quite compelling that the social welfare somehow is improved by MEV in some scenarios, right? That's not the narrative you hear, right? The narrative you hear is like, oh, grannies are getting robbed in MetaMask, and that's just not true, always. So like I said, I'm not going to go through how you show such a thing, but I'll at least give you an idea of like what the theorem statement looks like for such a thing. And the idea is we showed that even when they're sandwichers, the price of anarchy is constant. Remember, price of anarchy constant, that's good. That's very surprising. You would think that, hey, as more users come to the network, sandwich attackers make more of a profit, they cause more of a loss. But in some liquidity conditions, they do not. And this sort of bottom chart shows you the expected profit on the y-axis, and it shows you sort of the amount of slippage inured by the user. And you'll see that it has a maxima. It's not like it keeps growing. And that's the thing that's actually quite interesting and nice about this example. OK. So you've listened to me try to convince you that MEV is not bad. It can have these positive externalities. Maybe there's something really interesting about it, and maybe you can direct it into being used for some particular applications that are just net beneficial to your network. So one question is, what do you do to harness it for good? So one thing I think that's interesting, and this goes a little bit to Alex's talk before, is suppose you did have a mechanism where it was just extremely expensive for people to bribe a validator off-chain. And in fact, people were willing to basically share their MEV revenue. Imagine like a mining pool for MEV revenue. Now, the reason that that's very hard to design is it's very hard to make it collusion-proof, where people pay one miner ahead of time who in the pool, and they don't share revenue with everyone. But suppose you have a way of doing that, and there's a lot of people working on really, really interesting stuff, both on the cryptography side as well as on the sort of distributed system side for trying to do such a thing. But suppose you have such a mechanism, then you can redistribute MEV to all the validators in the system. And one very interesting thing is you can show in some sort of different types of MEV, you actually can lower the overall inflation rate of the network if the MEV subsidy is large enough. So the x-axis on this plot is the percentage of MEV revenue shared, and the y-axis sort of is a measure of how much people are adjusting their stake. So let's say there's sort of opportunities outside of staking that people can earn yield on their assets with. One question you might ask is like, what are the incentives that keep people staking? And the interesting thing is that MEV actually adds this feedback loop such that you can lower your inflation but also ensure that people stay staked. And so, you know, the y-axis is sort of a notion of percentage of how much of the network is staked. And you can see that at around 25 to 50% in this stylus model of revenue sharing, you actually get people to continue staking, which is just, you know, it's just kind of surprising, right? Like everyone's always like, oh, we've always needed kind of hyperinflationary economics, and there's lots of reasons for that. But MEV distribution also allows you to avoid having to do that. So that's sort of like a kind of amazing blessing in disguise. And there's a lot more research that can be done in this space. I think we mainly looked at how liquidations impact staker incentives. Another interesting thing, and I think this is the type of thing that we're seeing in multiple ecosystems, whether it's in Ethereum, especially with roll-up auctions, whether it's in Cosmos, but everyone sort of is starting to realize the MEV auction of having a single MEV auction for everyone to kind of compete in may not be the best form of an auction. You may want to have an auction per roll-up, you may want to have an auction per application, so that you can tune the social welfare versus revenue trade-off. Right now, if you think about it, everyone who's making a Flashbots bundle for an NFT mint is competing with everyone who's sandwiching for the same sort of block space, but they may actually, if you segment to the block space and say only this amount goes for sandwiching and this amount goes for NFTs, you might have a very different equilibria. And I think, you know, a lot of the roll-up developers are basically kind of talking about this. But an interesting thing is, and some current work is, you can actually show that disaggregating a single auction into many auctions can actually have better social welfare for the end user. And that's sort of like an interesting kind of trade-off that I think as things like PBS get developed, you have to sort of analyze these types of incentives. So, you know, I think I want to just at least impress upon people that theoretical foundations for MEV are really important. And I think we've sort of started with this thing as this like emergent, unstudied phenomena. We sort of backed our way into some mechanisms for like, you know, doing an auction, coming up with sort of rough reputation scores, which, you know, it's not totally clear exactly how that whole system can be analyzed, to a point where we actually are really able to start thinking about, okay, how do we optimize for things like redistribution? How do we optimize for social welfare? How do we optimize for validator revenue in a sort of joint manner? And formalism, I think, provides us this way of finding these truths about MEV which show that, hey, it's not always robbing grannies in MetaMask. And the interesting thing is, I think, you know, this is sort of the beginning of this kind of new branch in my mind of algorithmic game theory, where you're really focused on the joint optimization of social welfare and revenue, because both of them are extremely important to network survival in cryptocurrencies. And so I want to leave you with some open problems in case anyone kind of is interested in this type of stuff. The first thing is, what's the notion of optimality for an auction, right? Right now, if you look at Flashbots, it's sort of a first price auction with some filtering because they use a scoring function that removes some public mempool transactions. Is that optimal? Does that work when you have multiple chains or this sort of hierarchical system? Also, does it sort of deal with some of the problems of, hey, how do I trust the auctioneer? Right now, we have a system where everyone basically trusts the auctioneer. And, you know, economists have copied cryptocurrency enthusiasts and made some trilemmas recently on proving things about when auctions, when you can't trust an auctioneer. And a lot of that work, you know, I think if the right people were focused on it, could really determine how PBS functions as an auction and what sort of like the expected properties of it are. On the other hand, there's sort of some notion of lower bounds. Like in an open permissionless system with some notion of value, there sort of has to be some lower bound to the amount that's extracted, because without any extraction, it's very hard to imagine validators being able to continue to sustain the network. And so one question is, how do you construct those lower bounds? You know, in information theory and in theoretical computer science, the lower bounds are extremely hard. Upper bounds are always easy. Lower bounds are really sort of some of the hardest kind of things to show. And I think the MEV space of lower bounds is still quite open. I think, you know, in spite of kind of there being a camp of some people who believe with sort of fair ordering that there exists no such lower bound, I would argue just proving that the lower bound's not zero is already a quite difficult problem that would, you know, be worth solving. And the last thing that's a very big open problem research-wise in MEV is this concept of aggregation versus disaggregation effects. And so I think a lot of people in the MEV parlance will focus on talking about things like private order flow aggregation, like what happens when a builder has all of a certain type of order flow. There are ways to talk about what the equilibria of the system are, what's the distribution of revenue to different participants based on these kind of aggregation versus disaggregation effects. But if I were to kind of give you the stylized version of what this question is asking, it's saying, what is the Coase theorem for MEV? So Coase theorem, for those who don't know, is sort of a very famous thing that I think basically says, imagine you have a company. Now suppose the company had everyone at the company as an individual contractor. Why is it more efficient to actually organize as a group versus individual contractors who are giving payments to each other? And the Coase theorem sort of says there's some equilibria in the middle where there's aggregation effects where it's cheaper for people to work together and share common infrastructure up to some point, and then after that point, the overhead of managing that many people starts causing you to lower your welfare. And this notion of aggregation versus disaggregation in MEV is completely unsolved, yet people are always talking about it. It's kind of implied in people's language, yet not formalized. Cool. And so with that, I'll leave you for questions and also, launch something today.
Audio check, there we go. Thank you. Do you have any questions for Tarun? If so, please raise your hand. We'll get you a mic. We got one question on this side. We'll get to you in a second. We got another question at the back. Just stay patient on this side. So the one in the middle. Awesome.
Hi. So my question is, you gave an example of, you gave first a theoretical example of how removing an edge from a network can make traffic more efficient. And then you gave an analogy for how this can also happen with AMMs. And you gave a practical example of how it could happen with AMMs, but I did not understand how this practical example works. So could you explain more, like how could MEV improve the efficiency of trading on this scenario with two pairs?
Yeah, so think of it this way. Imagine that there's people who want to trade from token A to token B, and there's an order flow of n orders from A to B. If I look at how to optimally route the orders from A to B, if everyone gets routed on the same route, the price that everyone pays on average could be a lot higher, right? If everyone gets routed on different routes throughout the network, you could have sort of your load balancing what the price impact is. And the point is that the MEV searchers are sort of acting in some weird capacity as almost like air traffic controllers. When there's a bunch of traffic going on the same route, it increases the MEV profit, but as the MEV profit goes up, then people start routing away from that. And you could effectively think of it as a way of sort of having a decentralized coordinator where it comes from the fact that the more traffic going on one route, the more the sandwich profit, but then once people start realizing the sandwich profit, they route elsewhere. And so this routing problem is actually, you know, the quintessential example of these cases where congestion sort of, you can add in some sort of like incentives to avoid congestion. And you know, a lot of internet routing, traffic routing on the internet, a lot of that kind of work is like where this initially started. And this is sort of making an analog of that here. But the key is that someone is getting a worse price by being sandwiched, there's no doubt. But everyone going across the graph is getting a better price on average. And that's the social welfare versus revenue trade-off, if that makes sense.
Awesome. We have another question at the back.
Hello. Good afternoon. Love the presentation as usual. My question is, have you made any studies around central bank digital currencies or even fiat currencies using the same theory?
Yeah, I mean, I think the hard part with any of these sort of like pseudo-centralized federated type of things is, well, I mean, the validator can just always do the MEV themselves, right? Like, the limit of the centralized thing is like, well, what are Facebook and Google doing? They're just doing MEV on their own auctions, right? They're constructing the bidding strategies for you. They're like, we're using the highest machine learning to give you optimal like targeting. It's like, it actually means, we're just gonna front run you in our auction, but it's too complicated to explain how. So in the centralized world, these types of things are not that interesting to analyze from that perspective, in the sense that the centralized coordinator will just like choose the most expensive route for you all the time, right? But in the decentralized world, it's actually quite interesting because the user has to choose their own way through the network. So yeah, that's sort of you.
Great. We have one last question on that side, and we'll move on to the next talk. So please go ahead.
Yeah, hi. I'm following up on the first question. In the RAS example, the conditions under which the routing would actually, or in which MEV would be beneficial is if you can teleport, right? These conditions are usually not met. What are you said under certain conditions this applies for AMMs. What are those conditions? Does it mean if I can trade, you know, if I can print free money or trade at unlimited or zero exchange rate, or what are the conditions in which?
No, yeah, actually, that's a good point. So the zero is in the traffic example. In the AMM example, you can never have zero, effectively, in that edge. There's always some amount of liquidity, price impact, unless it's like, you know, a linear AMM. I think the main thing we showed is that the liquidity difference on certain edges on that graph relative to the center edge has to be large. So it's not necessarily that it's saying that, hey, you're teleporting, or it's like you have some sort of like non-balanced budget condition. It's actually just that the relative liquidity differences on different edges has to be high. And those are the conditions. And you know, I'd say our proof is pretty pessimistic in our conditions, and there definitely were ways of like getting much better bounds on it. Yeah.
Awesome. Thank you so much. Please give a big round of applause for Tarun. Next up, we have our speaker, Ansgar, and he's going to be talking about how do we scale blockchains, especially from a roll-up-centric viewpoint. So without further ado, please welcome Ansgar on stage.
Hello, everyone. Yeah, my name is Ansgar. I'm going to talk a bit about scaling, but I want to start first just with a very quick apology. In case you were here to hear about multidimensional resource pricing, I had a bit of a hard time to make up my mind which of the two talks I wanted to give. So for a while on the website, both titles were on there. So if you're really into multidimensional resource pricing, which you should be, I can only recommend, I gave a talk earlier this year about it in the Ethereum context, which is quite interesting, I think. And then also with EIP 4844, we are about to introduce there's an open PR to update the fee market there. And hopefully, fingers crossed, this will be the very first time that we start moving to multidimensional resource pricing in practice on Ethereum, like in this case, two-dimensional. So do have a look. But today, here, I'll talk about scaling and specifically rollups. Why rollups? I first want to talk more on the theoretical side. Why really are rollups so fundamental to scaling? And then bring it back and talk about Ethereum's future place in that world, basically. So first, why rollups? And I want to start by with something that I call execution chains. It's basically just blockchains as you know them. So Bitcoin, of course, was the very first ever special purpose execution chain. Special purpose just because it's only for payments and money. Ethereum, the very first general purpose execution chain. And in general, all these chains, of course, they want to have maximum functionality, maximum throughput, but that's a tension with needing to guarantee security and decentralization. And to illustrate that kind of the tension, I created this little fun little graph. So basically, on the x-axis, you have the cost to run a full node, and on the y-axis, you have the throughput that your network can have. And with Bitcoin and Ethereum, basically, you are in this nice zone where down there, where basically everyone who wants to can run their own chain locally. I don't run my own Bitcoin chain, right? I occasionally use Bitcoin, but I could. It's just a trust trade-off that I choose to make. But that does mean that these chains are fundamentally limited in throughput, right? By basically the minimum consumer hardware capabilities. And kind of the key insight here really is that like everyone validating everyone's transaction doesn't scale. But of course, we don't want to give up, security by kind of moving beyond this. So like the very first thing you could do, and I picked Solana just as an example, and this is not meant as a slide at all. Actually, I think in a second you'll kind of see how, in a way, they're kind of moving in an interesting direction here. But basically, what they're doing, their version of scaling is just to basically go further up this diagonal, and that does give you higher throughput. But of course, it means that now running a full node becomes really expensive. So that's one way of just increasing throughput. The problem is, what if you don't run your own full node and there's some sort of disagreement, right? Some malicious attack, some chain fork. You only have two choices. Either you go with a majority, in which case 51% of the network can always rewrite all the rules, take away your money, everything, right? Or the other thing you can, of course, do is halt and recover via the social layer, but that's very slow, of course. So where do we want to end up on that graph? That's basically this, what I call the unicorn zone up there, where everyone could trustlessly validate the network, but we still have like really high throughput. So how can we basically find a way to get there? And that's basically where rollups come in. And why do rollups come in there? To explain that, as you might be aware, you probably are aware, there are like two different flavors of rollups, optimistic and ZK rollups. The easier to explain in this context is optimistic rollups. So basically to kind of get an intuition for how optimistic rollups solve this dilemma here, we can look again at the Solana case, and as I was talking about, right, if there's a disagreement, and even if you don't run your own full node, you always have the option to just halt and recover via the social layer. And the optimistic rollup kind of idea here is, what if we could just massively speed that up, right? Instead of running that kind of this fallback mechanism on human brains, where whenever something goes wrong, you have to actually go on Twitter and whatnot. What if we basically just automate that, right? Like we replace the human brain with software, and in particular with fraud proofs, and that's how you get optimistic rollups. So, kind of trying to keep with my little picture symbolism. So their optimistic rollups are also basically a form of an execution chain. They are their own blockchains, basically. The way they work is that they apply the changes optimistically. And anyone can submit a fraud proof. So the only guarantee you need is that there's someone in the system that notices if something goes wrong. But a one-of-n honesty assumption is a way less severe restriction than a majority honesty assumption. And then these fraud proofs, they are automatically resolved on some sort of settlement platform. That you need. And then the alternative, as I was saying, ZK rollups, they are just cryptographic magic, right? So in that case, you don't have to do this retroactive fixing of problems. Instead, you just have any state update come with a cryptographic proof that no one did anything wrong. And again, you need some sort of settlement platform where you can resolve this. One more little caveat here is that basically with rollups, we're moving away from this world where like everyone needs to run their own like full node to ensure integrity, right? Like I could basically only follow the settlement chain and still basically have all the guarantees about the rollup. But one additional thing to ensure is that we have to also pay attention to data. If you run your own full node for a chain, data is implied, right? Because you actually download all the data and execute it locally, but with rollups you don't do that anymore. So now we basically need explicit data availability mechanisms. And that's what I put this little kind of database symbol there. Yeah, and with that basically, once you have like an explicit settlement system and you have an explicit data availability system, now basically you can break out of this kind of graph of this full node versus throughput basically trade-off. And how can you actually use this now to kind of to build full blockchain systems? That's kind of what the second part is about. Like how do you actually turn this into something useful? And this is going to be very picture heavy because I don't know, for me it's mostly about giving good intuitions here for like, I don't know, my mental models around this basically. That was my motivation for the talk. So again, this is like an execution chain. I drew a little box around it. It's basically in its own box there. It has its own security. And that's the world as it used to be, the blockchain world. We had a lot of these boxes like a couple of years ago, right? And now we're adding these exciting new tools to the picture. We're adding settlement and we're adding data availability. And how do they basically change the picture? Well, first we kind of have to bundle them in some, or like we have to kind of put them into some useful form. The way we like to think about it is bundling them into what we call a settlement chain, which is its own blockchain there. You can see it has its own security. It's not the only way to do this. Like if you, for example, know Celestia, which is a really interesting other kind of project that basically works with similar kind of models. They keep data and settlement separate, but for us, the way Ethereum kind of likes to approach these things is by combining them into a settlement chain. So now we have these two separate chains. How do we basically now actually make use of them? Well, the way to do this is by, and that's what the arrows are for, by basically turning the execution chain into a rollup. It kind of functions as it did before, but now it uses the settlement chain for data availability and for settlement, so it needs some sort of fraud-proofing mechanism or it needs some validity proofs attached. But other than that, it still feels like a normal blockchain, basically. The simplest way to do this is what we call like an enshrined rollup. So in that case, you'd have like one settlement chain and one rollup on top, and it's basically like a one-to-one relationship. And a very simple way you could imagine basically this process playing out in the blockchain world is, and I guess that fits well into this kind of the multi-chain vision, would be where every blockchain that wants to basically go hyperscaling just adds their own little settlement chain underneath them. And that would basically bring you to this picture with multiple different blockchains. That would all now have their own settlement chain. The downside there is that for one, you have fractured security, right? Each settlement chain has its own validator set or its own miners or its own, however you get your security as your chain. And it basically, some of those will be higher security, some will be lower security. And that also affects bridges. Maybe some of you have seen kind of Vitalik's write-up a while ago about how basically if you bridge multiple chains, you always end up with the weakest security of all of them, right? If you want to use assets of like 10 different chains, if the security of one of those breaks, like that specific asset just basically is broken for you, right? And if you have some sort of DeFi system where all of this is interconnected, basically everything can crash and burn. You really don't want this minimum, worst of all security kind of situations. And also, I guess that's less of a severe thing, but also in this picture, you're kind of duplicating a lot of complexity for each chain. So what would be an alternative vision? How do we think the future might look like? That's what we call like a shared settlement chain. So in this case, you have one big settlement chain, and you can have multiple rollups on top. Of course, probably realistically, the future will look some sort of hybrid. You'll still have some blockchains that prefer to do their own settlement chain, but we predict that like this will be a big chunk of it, basically, like a shared settlement chain. And why is that advantageous? Well, two main points, really. One is the shared security. I like to think about it like shared pool security. It's not quite free security. Sometimes you hear people talk about how if you turn your chain into a rollup, you just get the security of the base chain for free. That's not quite right, I think, because actually, if say you have 10 rollups on top of a settlement chain, then they basically all put additional strain on top of that settlement chain, right? Like now the incentive to attack the settlement chain is 10x as high. So you don't just get, like security doesn't just, isn't just created for free, but it is pooled, right? So now basically you have to break the entire combined system instead of just being able to take the weakest link. And what that also gives you is then, because you have like one shared trust, one shared, trust zone basically, that all the bridges between those rollups, if implemented perfectly, important caveat, it can be fully secure. Okay, so with that, kind of bringing it back to Ethereum, of course, I guess the last slide there heavily hinted to where we want to end up with, but where were we in the past, where are we today, and how could we get to this shared settlement layer future? So kind of starting with Ethereum a few years ago, in the early days, basically, Ethereum also was a pure execution chain. We had proof of work security, rollups weren't yet a thing. That was kind of a happy place to be in for a couple of years. At some point, of course, like Ethereum always wanted to figure out like how do we actually scale to billions of users. It took quite a while, quite a few years of iterations and iterations, just because I like kind of research archaeology, and I would encourage you, if you ever have some free time and nothing else to do, go look at all research posts. It's always fun. So basically, just to illustrate that a little bit, I've like picked like 3 that kind of accompanied our way kind of towards this roll-up vision. The first one is, if you look, April 2019, it's really quite amazing. KCD trio, phase 1 and done, E2 as a data availability engine. Nowadays, I think this terminology, like everyone would just nod and be like, yeah, sure, dank sharding. But 3.5 years ago, I think that was quite visionary. Then a year and a half later, we had Vitalik for the first time kind of using this term roll-up-centric roadmap, where basically we finally realized that yes, there is no other way to scale. Like you really need this decoupling of the execution and the settlement. Otherwise, like you basically, as I was saying earlier, right? You can't break out of this dilemma. So we really like roll-ups are the way to go here. And then just third, just a fun little one. That my colleague Matt wrote a couple of weeks after Vitalik's post, looking back at our early ETH2 plans, and it actually turns out that basically this, if you remember the early sharding plans, if I just go back a couple slides, if this works, actually what we were planning back in the day with all these different shards was kind of this picture all along, right? It was just that we wanted to have all these shards be like super enshrined, and at some point enshrined rollups basically, and at some point we realized it's just much better if we open this up for general innovation, if we don't build, basically if we are the only parties building rollups. And so yeah, this basically just, as a little history kind of tidbit. So this is kind of how we got to where we wanted to move forward with Ethereum. So that kind of brings us to the kind of the pre-merge state, where we already started to use the Ethereum chain as a settlement chain as well, but of course it still has execution, so it's like kind of like a hybrid chain. Still proof of work security, of course, before the merge. And as I was saying, right, settlement chains need the settlement aspect, which you kind of get for free when you have a general purpose chain, but then you also need data availability, and data availability on the existing Ethereum chain is really quite expensive. It was never meant to provide data availability, so it's kind of basically right now kind of hacked in. You just basically just dump data into Ethereum transactions and then never actually use them, which works, but it's just very, very expensive as a source of data availability. Of course, we started having rollups on top. Really exciting, if you ask me. I think rollups have been making a lot of progress over the last 2 years. And then, pre-merge, we had this beacon chain, just an empty little box, nothing in it, but much stronger proof of stake security, right? And then, of course, as of today, we ended up, merging, and now we have this basically same situation as before, but much higher security. And just as a maybe quick aside, I think I have the time for that. Why does proof of stake actually give higher security? I mean, it's not really kind of part of my talk, but just because I always see a little bit of confusion about that debate on Twitter, I think it's really quite simple actually. Like the way I would think about like moving from proof of work to proof of stake in terms of security, one, it's just more efficient, right? And that is because you basically, with mining, you actually have to pay for the entire cost of the operation. You have to reimburse miners for both the mining hardware and the energy, right? Like they have to make all of that up with their income, whereas in proof of stake, you only have to make up the lost interest on your money. So basically, you can get away with paying way fewer rewards for the same security in proof of stake. And then the other one is also that proof of stake security is just fundamentally more effective. So that means that if ever there were to be a failure, which of course hopefully there will never be, but if there ever were to be like an attack or something, the attack is attributable, and so you can go in and selectively punish people. In proof of work, once someone like an attacker has 51% of the resources, you basically just, your chain is just lost. Nothing to be done. In proof of stake, it's really not a big deal actually, right? It's a little bit annoying for maybe a day, and then afterwards you're just done with it. So that's really neat, I think. And then also, like, I couldn't quite help myself. Maybe this one a bit more esoteric, maybe, but another quite interesting mechanism in terms of security that I really like is this Ultrasound Money one, where basically the idea is when you have no more mining rewards, that means that we have ETH as the asset has just much improved monetary properties, which in the long run might or might not turn into a higher expected monetary premium, higher total ETH market cap, and we can just buy more security in absolute terms. But again, this is more esoteric, totally fine if you don't buy into this. The first bullet point is the more important one here. Okay, so this is Ethereum today. Where do we want to go? How do we actually get to this full, shared settlement chain? How do we get full data availability? All of that kind of thing. So first thing is next year, hopefully, fingers crossed, looking good, I have to say. Proto-dunk sharding, ERP 4844, that we've been really actively working on. Just earlier today, there was a session on this, where basically I don't know if you saw that, but like the data symbol there just became way bigger because you just you add better data availability to the Ethereum chain. For the first time, data availability is an explicit service we provide. It's not just something tucked on, but it's an explicit service, and so it's just more effective. And then, of course, you've probably all heard about that, dunk sharding, soon, TM. Afterwards, that could be 2 years from now, hopefully, like maybe it'll be 3 years, but soon. And that's really where we get like ultra scalable data. And with that, we will be basically we'll be able to host multiple of these really high throughput rollups. So this is kind of, in terms of scalability, this is really the end game that we as Ethereum basically are aiming for. And basically kind of with those pictures in mind, I kind of wanted to then, for the last part, talk a little bit about where does this leave us? Like this, I hope that kind of gave like intuition-wise like a good idea of where we're moving and why, but what implications does that have? So the first thing I wanted to briefly talk about, what does it mean for the existing, well, ETH1, we used to call it ETH1 chain, like basically what now is just the execution chain within the beacon chain. What's the future of that? And there are basically multiple different potential future visions for it that you could see. The first one would be that it basically stays this hybrid execution settlement chain, or the rollup settle on top of it, but also still, it has some DeFi on it, whatever. For high value transaction, it can still be used as an execution chain. So that would be kind of the default case. Then we could have the scenario where it really turns over time more and more primarily into a pure settlement chain. So that means that really more and more of the user activity migrates to layer 2s, and layer 1 is really just becoming more and more just a rollup management layer. And then the third one, it's more like a fun thought experiment. It's not really kind of planned or anything, but just wanted to kind of illustrate how this modular architectures really lends itself to all these different ideas. What we could also do is that we could basically add an additional separate pure settlement chain to the beacon chain, and turn ETH1 basically into a, well, you could say a rollup, right? So in this case, if you look at that picture, you could just think of like one of those rollups being ETH1. So that's, again, I don't think that's likely that we'll go that way, but it would be almost, I don't want to say trivially, but it would be very feasible to go that route because we now live in this modular world. The other one I briefly want to talk about was the future of the EVM. So first, I do want to say it is by no means certain that kind of the future of high throughput execution chains will be EVM based, right? I think Ethereum as the settlement layer will always use the EVM. I think it's just good enough for that. But it's not yet decided. Like it could be that, you know, I don't know, Solana or something has the dominant winning highly scalable VM solution. It could be the EVM, it could be some of these other competing new ones. This is yet to be seen. I mean, we are very optimistic for the EVM in that scenario as well. And I think I do want to point out, because that's sometimes misunderstood, the reason why Ethereum only has the limited throughput it has is not the EVM. That's not the limiting factor. It's really that we want to keep the resource requirements for validators low. The moment you are a rollup and you adopt the EVM, you can still go far beyond the throughput constraints of the base layer. And there are many possible EVM improvements that we just never bothered to do on the base layer because they're just not relevant for us, but that layer 2s are very actively looking into. So I think there's a very good chance that the EVM will turn out to be like the winning or one of the winning high throughput VMs. Yeah, but of course, whether the outcome of all of this process will have like big implications. Like will clients basically say the existing EVM clients, will they be primarily settlement clients only, or will they also be used for rollups? At some point, maybe they'll want to focus on rollups even. How does it look like for programming languages for the EVM? What about tooling? All these kind of things, right? So I think this is going to be like one of the main interesting kind of technological debates of the next 5 years. And in particular, I wanted to very briefly talk about EVM equivalence, because that's just a topic that I personally am really interested in. So for these layer 2s, for these rollups that choose to go with the EVM, the question is, do they go with the exact EVM, or do they just go with something that looks kind of like the EVM, right? And if you remember, say Optimism, for example, they started out with what they called the Optimism virtual machine or something, OVM, which was basically an adapted version of the EVM, and now they're back at using basically the EVM as is. So the question is, in the long run, what is the way to go? Should you go with EVM equivalence or not? And so just briefly, basically the pros that I see would be, of course, standardization, right? Like if you use the EVM, just all the tooling works out of the box. You have multiple existing client implementations, which again, for security, having multiple clients is just really, really helpful, but also really hard to achieve. So this is like a big win you can get with EVM equivalence. The third one is a bit more speculative, but we could definitely imagine in the future that we have some sort of specialized settlement functionality around the EVM that we offer for rollups. Of course, that would not be mandatory, right? If you want to run your own like Fuel or Solana or something on top of Ethereum, you can do that as well, but we would have special support for these EVM-based ones. And one really interesting one, especially I think in the last few months, people have more and more noticed how governance can really be a liability. And if you actually follow the EVM as is, you can just defer to layer 1 governance and follow their changes, basically. And then what are the cons? Why might you not want that? Well, of course, one, it's just like if you're stuck with the layer 1 EVM, that does come at a cost of slightly slower iteration speed, right? We have to really vet every change that goes into the EVM quite severely to make sure nothing ever breaks. You might just need some layer 2 specific functionality. It's just harder to add that if you really don't want to, kind of mess with the EVM. And also, and I feel like that's the one that's the most relevant in the context of my talk here, if we expect layer 1 and layer 2 to really operate at quite different scales in terms of throughput, maybe having identical VMs is just not the ideal way to go. And just as like a potential compromise here, or having the best of both worlds idea that I want to leave you with here is one that I think might actually be quite exciting to explore in the future. What if we could maybe get the best of both worlds by having a dedicated version of the EVM specs for layer 2s that's still standardized across all the rollups that want, to opt in, but is able to over time depart from layer 1 and really focus on optimize for the layer 2 case. So I think there's a good chance that we might end up in that world, and I think that might actually, you know, be the best way to get us to high scalability. And yeah, and I hope, if I remember correctly, I do have a summary slide, so let me briefly go through that, but then we're done. So, you know, traditional blockchains, you always have the trade-off between security and scalability. Rollups solve this. Ethereum's vision, we want to become the primary settlement chain. We're still at the very beginning of this transformation. Ethereum will likely, this is the last point, I added the likely because who knows, right? But we do still, with the EVM, also have ambitions for execution chains. We do not just want to be a settlement chain. Yeah, and with that, thanks.
Amazing, thank you. We may have time for just one quick question. So if any has a quick question, please raise your hand. If not, we will move on to our next talk. Any quick ones? Going once, twice, 3, and we're done. Please give Ansgar a big round of applause. All right, next up, I'd like to invite Nick Johnson to talk about the state of ENS. You may all know Nick as Nick.eth. So without further ado, please welcome Nick to talk about everything that's happening in the world of the ENS ecosystem. Please.
Hello, how is everyone? I'm Nick Johnson, founder of ENS and lead developer, and I'm here to give you an update on what's happened with ENS in the last 3 years, which is give or take 300 years in crypto. Before I actually start, can anyone who's got an ENS card hold it up above their head? Wonderful, probably about half of you. I'm so delighted with how everyone's been doing with this. If the person next to you held a card up, have a word with them, say hi. Tap your phone to their card and you'll get a POAP that proves that you met them at Devcon. We still have a few of these cards left at our booth on level 3. So after the event, come down, we'll print one for you with your ENS name and your ENS avatar on it. We expect we'll run out sometime this evening, so I'm sorry if we don't get to everyone. But this is a great opportunity to meet the person next to you and have cryptographic proof of that afterwards. So first off the agenda, I'm going to recap everything we've done in the last 3 years and then go on to talk about what we're working on now and what we're working on next. First of all, in the next category, Thorin, which is ENS's new look and design system and new app. Second of all, talking about scaling ENS with off-chain reads and writes. Next, the name wrapper, which you may have heard about as a way to improve the functionality of ENS names and the ability to issue trustless subdomains. Finally, zero-gas DNS integration, how we can use these other components we've built to make ENS integration possible for DNS names without any gas fees. And then the conclusion. So first of all, the recap. It's been a long, long time since I've been at a conference, since I've talked on a stage in front of a lot of people, since I've given anyone an update on ENS. Last time I spoke was at last Devcon, in October 2019. We'd just transitioned from the interim auction registrar to the permanent registrar, featuring its current renewal model. And that was a mere 5 months ago. And while it was doing well at the time, we had very little idea of the phenomenon ENS was going to be coming in the next few years. We had about 50 integrations with various wallets, including MetaMask, applications such as Etherscan, and so forth. That's changed a bit in the last 3 years. Our set of integrations now looks more like this. So as you can see, we've come a long way from under 50 integrations to over 500. We had about 300,000 registrations back in the day. That's now over 2.5 million. We had about 96,000 Ethereum addresses that had interacted with ENS in some way. That's now over 1 million addresses. 66,700 years of registration had been purchased. That's now over 6.5 million, if you strung them all end to end figuratively. And the nascent ENS treasury had a stunning 382 ETH in it at the time. That's now 38,000 ETH, and I'll talk soon about the DAO and how it's able to put that to use. Of course, it's not all about the numbers. ENS has accomplished a lot on both technical and governance fronts in the past 3 years. Some of it will seem like old news, but it's been a long time. At Devcon 5, we had limited DNS integration with only the .xyz TLD supported. You could take an .xyz name, you could import it into ENS and use it just like you would any .eth name. Since then, this has been expanded to nearly every top-level domain that supports DNSSEC. So that's nearly 90% of all top-level domains. Nearly any name can now be imported into ENS and used as a native name. Just ask our developer advocate, Luke.computer. It's printed on his badge, I believe. There are transaction fees associated with importing any of these names, and at times when gas prices have been very high and the ether price has been very high, it's been quite pricey, but we've got a plan to improve that massively, which I'll talk about shortly. Another major improvement has been ENS's transition away from being just a way to name wallets and decentralized content to being a Web3 native identity platform with the introduction of avatar records and text fields that provide information about your profile, such as your Twitter handle, your email address. Your ENS name now represents you as your Web3 identity. It's a universal portable identity. And one project that's been bringing that to more users is Sign In with Ethereum. It started out as an RFP issued by ENS, and it was funded by a joint grant from ENS and the Ethereum Foundation. Spruce won the bid for that and has done an outstanding job of growing it into the primary way that people authenticate with Ethereum, replacing a plethora of incompatible and different standards for signing messages to assert your identity. With a symbol system that can be, thank you, that can be easily plugged into existing systems, including Web 2 legacy systems. But of course, when I talk about the last 3 years, and particularly the last year, top of most people's minds will be the launch of the ENS DAO, which is now one of the largest and most active DAOs in Web 3, which I am absolutely blown away about. ENS has always aimed for gradual decentralization, starting with the minimum set of permissions held by the widest number of people we could, which was the original 4 of 7 multi-sig. Unlike most multi-sigs, it included participants from around the ecosystem, not team members, and they had limited powers to upgrade ENS to replace components. Our goal was always to move from that to a system where ENS was governed by a decentralized organization. Since we launched all the way back in 2017, the only example we had to go on was the DAO, which, needless to say, was not a stunning success that inspired us to immediately decentralize. But things changed a lot, and the DAO space is now a lot more mature than it was in the past. And we decided that the time had come, that things were mature enough that we could let the ENS community govern ENS. And the DAO is the major milestone along that path of gradual decentralization. The DAO is now responsible for almost all governance levers and controls available to ENS, including approving contract upgrades, changes to core parameters such as pricing and how expired names are used. It's also responsible for treasury grants and projects using the funding gathered from the protocol. In the year since the DAO's launch, the ENS DAO has shown that it can maintain a high level of civilized discussion, made useful progress forward in improving the protocol. Besides budgeting and day-to-day bookkeeping, it's made meaningful changes to the protocol, including changing how expired names are handled in order to safeguard the stability and fairness of the system. The DAO has also started to build out public goods and grants programs of its own. One example of this is the small grants rounds that we now run. inspired by Noun's props room. This is a regular system where anyone can submit a proposal for work they want to do or work they have done. Anyone with ENS tokens from the DAO can vote on them, and the top 5 in each category, we have a public goods category and an ecosystem category, then receive 1 ETH each in funding to pursue it. The public goods is focused on anything in the wider ENS ecosystem, and the ecosystem category is focused more on things that relate directly to ENS. And we hope this can work to better incubate and start up new projects, both for ENS and for the wider public goods on Ethereum and Web3 ecosystem. Working groups have also funded initiatives on scales small to large, ranging from a 200K ENS token grant to the Protocol Guild, who are formed to help fund core developers throughout the platform, 169K Gitcoin matching pool, and we continue to fund and support Gitcoin, and smaller projects such as this plugin for discourse forums, which provides you with insight into the roles of delegates and their participation on the forum, which is something that any DAO that uses discourse can take and plug into their own system. This was built by Karma and integrates with all their stuff. You can also just use it to provide insight into how your delegates have voted, how active they are, how many tokens they have, and so forth. The DAO has also resulted in more community participation in the core protocol. One major success story is Rafi's work on improving ENS's normalization functions. Normalization is how we handle names like uppercase Nick being different from lowercase Nick, ambiguous emojis, hidden characters, and so forth. To start, we used a well-tested system called UTS-46, which is what the domain world uses. But it's become clear over time that ENS has some unique requirements, and we wanted to enable things such as emoji and other characters that are popular in the community but not supported directly by DNS. So Rafi has been working on harmonizing all of this. We're very close to rolling out the new standard for DAO approval, and it will enable a much wider array of characters while also providing more protections against deceptive names. The last 3 years has also seen an explosion in community-led ENS initiatives, independent projects that build on top of the ENS ecosystem. One popular example you may have seen is the ENS leaderboard, which shows people with Twitter handles that contain .eth and their ranking relative to followers. We've had some pretty popular ones, including Paris Hilton, for instance, right up the top of the leaderboard. I myself am now ranked, I don't know, number 400 or something. We've had the launch of ENS Vision, which is a third-party ENS trading market. Allows people to now register names from scratch and also trade existing names. And projects such as Nimi, which is a Web3 profile site. It lets you generate a customized profile, and in fact the eth.limo gateway folks have integrated with Nimi, so if you have an ENS name that doesn't have content set up, it will automatically show your profile with your POAPs and so forth, and you can customize it as you wish. Before we start talking about what's new, one small announcement. True Names Limited is the name of the development company that builds ENS. The company I founded that gets paid by the DAO employs about a dozen of us to build out ENS. When we formed it, we didn't really think of it as a name that would be visible to people. It was purely an internal thing. But in the intervening time, it's become more and more visible. And every time we have to say, we're from True Names Limited, the company that develops ENS, and it gets a bit tiresome. So we're renaming to ENS Labs Limited to better reflect what we do and who we are. So what's next? First, we're going to talk about Thorin. Thorin is ENS's new design system, and it's built from the ground up with usability and Web3 in mind. We've used it to completely rewrite the ENS app from the ground up, coupled with improvements to the smart contracts behind ENS. This enables a huge improvement in usability for ENS users. The ENS UI faces kind of a unique challenge from amongst Web3 apps, and in fact kind of apps in general, in that it needs to provide an interface that is both easy and user-friendly for new users, but has the advanced levers and sophisticated interaction required by advanced users. We don't want to create a situation where the app is sufficiently flexible to do anything with ENS, but deters existing users, which is a little bit the case of the current app, or is so straightforward and wizard-based that you need to go somewhere else if you do have more than basic needs. By surfacing the important details and flows while still making advanced functionality available under the covers, the front-end team have done an outstanding job of writing an app that is for all users. Aside from the functional improvements, we've hugely improved the loading times and made the new app 100% mobile friendly. The new app is at feature parity and live now on the Gurley testnet. Would be live on Ropsten, but that's already been deprecated. You can try it out now at alpha.ens domains. Just to emphasize, it's only on Gurley. It is a little bit, sharp edges still. The team really raced to get it out in time and did an amazing job. Please send us your bug reports, but we aim to have this launch on mainnet shortly after Devcon, once the name wrapper and other contracts are approved by the DAO, as I'll discuss shortly. So keep your eyes peeled. Thorin isn't just for ENS either. We've made it available as a standard React library that anyone can use for their Web3 apps. You can check it out on thorin.ens domains. And you may have noticed it powering a number of our other sites, such as the Swag microsite and so forth. One of our major ongoing projects is scaling ENS. For many projects, this is accomplished by going multi-chain, deploying to just multiple chains. If you're Uniswap, for instance, you fragment your liquidity a bit, but you can work in parallel across multiple chains. ENS is in kind of a unique position here. We need to maintain a single cohesive registry of names, and it's far too early in the L2 and the roll-up ecosystem to pick a single service as the winner that we're going to migrate to. Instead, we've been pursuing options that make it possible for people to host their ENS names anywhere without the resolving having to know or care where that is. Earlier this year, we launched CCIP Read as a collaboration between ENS and Chainlink. While previous systems, such as bridging, often introduce new trust assumptions and require L1 transactions to execute, CCIP Read uses a lower-level primitive, proofs, which means that in many cases, such as with L2s, this can be done with no additional trust assumptions over those the L2 itself requires, meaning you could host your ENS name on Optimism, have users resolve it from any client that doesn't know what Optimism is, without introducing any additional trust that relies on the gateway operator, for instance. Further, the solution's far more flexible than bridging, allowing data to be stored not just on L2s or sidechains, but on arbitrary systems, including centralized databases. At its core, ENS is a way for any contracts to fetch data from off-chain resources. Because contracts can't directly talk HTTP requests, this ends up being a little bit like having one of those conversations with a couple who have had a fight and are refusing to talk to each other. Well, you tell the gateway that I think that they should give you this data I need. So the conversation tends to go like that. Unfortunately, just ask them yourself isn't an option, so the client has no choice but to play middleman. The end result is good. With the resolver and the gateway agreeing on a protocol, it's possible for the client to facilitate a lookup of off-chain data without any knowledge of what their shared language is or what the off-chain system in use is. The necessary proofs to make this trustless are encapsulated in the response sent by the gateway and verified by the resolver before returning the result from the name resolution. This means that implementing the base protocol is enough to enable all current and future L2s and off-chain storage systems to be used in the ENS name resolution. For instance, Ethers already supports this, which means that you can resolve any ENS name that uses it, even if it uses an L2 that didn't exist when the Ethers implementation was written. CCIP Read is already in use in production. Both Ethers and Web3.js support it. And so if you use either of those libraries, or in fact, as of, I believe today, web3.py, upgrading to the latest version will mean you automatically support ENS off-chain resolution. Some of the largest apps and wallets have already upgraded to support it too, including MetaMask, Coinbase wallet, as well as Ethereum, Etherscan. There's a long way to go in terms of making this latest change universal, So please reach out to your favorite wallets and apps if you see that they don't support these new names, and ask them to let them know how important it is. Like our Thorin, CCIP read also isn't just for ENS. It can be used to add off-chain resolution support to any project. Coinbase has gone a step further than just integrating CCIP read for name resolution. They're using CCIP read, ENS wildcard support, and ENS's DNS integration together to allow their wallet users to create ENS names under the .cb.id domain for free. These names will instantly work in any wallet or dApp that supports ENS's new resolution improvements, and they have no transaction fees to set up for either users or Coinbase. Likewise, Lens is using CCIP read to integrate their own .lens naming system with ENS. Any .lens name, you can add .xyz to the end, and it will resolve in MetaMask or any other wallet that supports this. So off-chain read support is great, but how do we enable writes? The default option for every platform is to provide its own interface for users to update their records, meaning if you use Coinbase Wallet, you have to use Coinbase to update your records. If you use MetaMask, you'd have to update with MetaMask. But this leads to fragmentation and makes general purpose apps like our own manager much less useful. Fixing this is still a work in progress, but EEP 5559 lays out a way forward by enabling a discovery mechanism that allows clients, such as our manager, to discover how they can send a transaction or an HTTP request to update data that's stored off-chain. It currently supports writing to EVM-based L2s or sidechains, or sending signed messages to an HTTP API, but this is extensible with new methods as they crop up. Adding support for this to the ENS manager and further standardizing the best practices and making it as flexible and extensible as possible is an active area of research and development for the team. So next up, the name wrapper, which you've probably heard about griping about on Twitter because it's been underway for a while. ENS predates all of the NFT standards, and while the .eth registrar was written after EEP 721 came out, that functionality only applies to .eth second-level domains. So nick.eth, but not wallet.nick.eth or nick.xyz or whatnot. As a result, not all ENS names can be transferred, exchanged, etc. using standard NFT interfaces. Further, one of the main advantages of tradability is trustless ownership. If somebody sells you a name or a subdomain or gives it to you, you want to make sure that they can't take it back next week and set it to a different address. You're kind of reliant on their goodwill. There are solutions to work around this. You can give ownership of the name to a contract, and we've had a system for that called now.ens.domains for some time. But it has significant shortcomings in that you're committing your name to a specific contract where it has to live for the rest of time, which limits what you can do with it. The name wrapper solves both these problems. It allows any ENS name at any level, whether it's a .eth or a subdomain or a DNS name, to be wrapped as an ERC 1155 NFT. It also allows owners of wrapped names to revoke permissions, such as the ability to replace or delete subdomains, by a mechanism we call fuses. Fuses allow the owner of a name to revoke their own control and that of any subsequent owners over certain functionality on a name, such as the ability to unwrap it again, to create or to replace subdomains, to transfer it to another user, and so forth. Once a fuse is burned, that fuse can't be reset until the name expires, giving a user a guarantee as to what can be done to or with their names until the name expiration is reached. The name wrapper tracks these permissions and provides a very easy API for fetching the set of restrictions currently applied to a name and when they'll expire. Alongside the name wrapper, we've also implemented a suite of other contract improvements, including to the .eth registrar controller, the reverse registrar, and the public resolver. Altogether, these will permit a much smoother registration process for end users and cut down on the number of transactions and gas required, as well as other quality of life improvements, like allowing contract owners to set primary names for their contracts. The long and the short of this is that with the new .eth registrar, you will be able to register a name, wrap it in order to set permissions, burn fuses, and set your primary name all in a single transaction, and using less gas than doing those operations would cost today. All of these updates are live now on the Gurley testnet, and we're planning to submit them to the DAO for approval on mainnet very shortly after Devcon. Thank you. Finally, I'm going to talk about something else I'm excited we'll be able to release soon, gasless DNS integration. Presently, claiming a DNS name in ENS costs a substantial amount of gas. It's about 100K to 1 million gas per signature it has to verify. Depending on the ether and gas price, that can range anywhere from $20 to, at the extremes of the bull market, $1,000. Obviously, this isn't a particularly scalable solution. And so this can be a substantial barrier to DNS integration. Fortunately, we have a plan for reducing this all the way to zero. So first, a quick overview of how DNS works. It uses a chain of trust, just like SSL. The root zone is signed by a well-known certificate authority, and they sign keys for each of the subdomains, such as .com, .link, etc. Each of those zones uses its keys to sign its subdomains, and so on and so forth. Our current DNS integration uses this to allow users to claim DNS names inside ENS. Our front end collects up all the complete set of proofs necessary and submits them to a smart contract, which verifies the signatures, and if they match, it lets them claim the name. If you've been paying attention to the talk so far, this may sound quite familiar to you, similar to something else we've discussed, CCIP read. If we treat the whole of ENS as a massive off-chain distributed database, we can have a gateway that fetches DNS data, collects all the proofs necessary, and submits it to the chain, just like when you're resolving a name. So then we can write a resolver for DNS names that uses that gateway to resolve names in ENS, entirely using data stored in DNS. Users can set DNS records to configure their name, and they will resolve everywhere ENS is supported with 0 on-chain transactions necessary. Claiming on-chain may still be useful in some cases, for example, if you need granular control over the subdomains, but for most users, it'll be possible to claim your DNS name just by setting some text records. We're working on this right now. The DNSSEC Oracle changes are done, and we're working on implementing fixes from an audit before we roll it out. We hope to have it ready to go before the end of the year. There's been a lot more going on with ENS, but compressing 4 years down into 25 minutes naturally means I have to leave some things out. Just one more thing. The DAO is nearly a year old, but still in its infancy. We have a lot to learn and a lot to do, and we need your expertise. Please take a look at our governance page, reach out to ENS Domains on Twitter, see how you can get involved and help us build a truly decentralized public good naming for Web3. And that's all I have for you. Thank you very much.
Awesome. Do we have any questions for Nick? Please raise your hand. We'll get you a mic. There's a lot of things that we talked about.
There.
We see a hand over there. Keep your hands raised so we can find you and get the mic to you. All the way at the end. We're coming from this side. Almost there.
Sorry, that's all the time I have for questions. No, I'm kidding.
Hi, Nick.
Hi.
Thanks a lot for the talk. One thing I was thinking about, you should probably be able to use ENS to, the problem is when you use UI to communicate with a page, the MetaMask will generate you, it will provide a transaction for you, and basically you have no idea like if actually the UI is the right UI and you are calling the contract you want to be calling. And I guess you could UNS, you could UNS for this, for linking both the domain and the smart contracts with the same ENS and have MetaMask check it, basically to provide a lot of attacks connected with the UI
yes.
spoofing.
Yeah, definitely. Better user insight into transactions is, I think, probably the major adoption barrier and phishing and so forth issue in Web3 today. Naming contracts with ENS names is one big step towards making that a bit better. And in fact, the latest contract updates we're pushing out make it easier for contracts to get ENS primary names. I am also the author of a proposal with Richard Moore on how to better provide insight into transactions, which is also very relevant there.
Yeah, and could you make basically the calls from the other side? Meaning MetaMask could somehow check with DNS, like what this contract is, what ENS is this contract associated with?
Yes, and further you could put authorized front ends in your ENS records so that it will warn you if you're making a transaction to say Uniswap from a scammy site, which is an excellent idea.
Yeah, perfect, thanks.
Cool, thank you very much.
Awesome. We have one last question here, just at the front row, and then we'll be at time.
Hi, I was wondering if you could kind of give us a state of the union on efforts to resolve pages via browsers and at the OS level.
Sure. So at the OS level is, depending on how you look at it, tricky or easy. You can run your own DNS resolver, in which case you personally get to resolve all ENS names. Getting it rolled out to everybody is a very steep hill to climb. I think we're going to have more success getting this integrated into browsers such as Brave and Opera, which already support it, rather than integrated directly with OSs. On the other hand, there are efforts around .eth, talking to Ethiopia about whether they would be willing to relinquish that. This is all very nascent, however, so there's nothing concrete for that right now. The shorter term solution is, as I said, browsers, I think.
Awesome. That's all the time we have. Please give Nick a big round of applause.
Thank you.
Up next, we're going to talk about how do we make the best possible experience as we use and scale more blockchains. And to talk about that, I'd like to bring on Taylor Monahan on stage to talk about the original sin. So please give a big round of applause to having Taylor on stage.
All right. Woo! All right, let's do this. For those that don't know, I'm Taylor Monahan. I'm going to be talking about the original sin, basically some of our early choices and how they've shaped this ecosystem. And more importantly, how can we make better choices so that the world is better tomorrow? A little bit about me. Again, my name is Taylor Monahan. I've been in the space since 2013. I got in right before the Mt. Gox crash. I've been building wallets since 2015. I started my Ether wallet. We then did like a brand fork into my crypto, and we were acquired by MetaMask earlier this year. It's been a ride, that's for sure. But I'm basically like an expert in how to like build wallets, also how not to build wallets. So maybe I can like share some expertise today. So I have a 4-year-old now, and this is one of our favorite books, and it's like quite ironic because it's basically the story of my life. When I first started out, I was just building. I was building something amazing, and I think a lot of you here are probably in the same boat. Right? You're in the early days, you're in the early stages, you're building something inspirational, right? That's going to change the world, it's going to make people's lives better, it's going to make society better. And I hope that you're really proud of what you're building, right? Like you create something, you brought something new into this world. And this space specifically is like truly remarkable. It is next level in terms of like what we are actually doing and the impact that our products can have. These are all of the best Web3 words, all of the most amazing things that we can do with the technology and our products. And most importantly, like, I think, you know, at the end there we have the inclusive community and we have the genius people and the good vibes. Like, that's what I'm here for. And that's kind of what I like to focus on most, right? Like, when I get on stage, I like to talk about people. Because if we only think about the technology and the products that we're building, well, you're going to end up in this situation quite a bit. Because the second that you sort of, I don't know, the second your dreams start to come to fruition, the second that everything starts to line up and you feel like you might have a grasp on it, it really does seem that then out of nowhere, everything keeps crashing down. Because building shit is really, really hard. And especially when you're a wallet and you know, you're the product that people are using to access and manage all of their digital assets, it's really hard. Things come crashing down a lot. And the worst part of failing at like building a good product is actually like the failing people, right? We're failing the newcomers that enter the space. They're getting phished. They're getting scammed. They're optimistic one day, and then they have their hopes and dream crushed the next day. And that's what basically the last, I don't know, like 7 years of my life have been, right? Like trying to be better every single day, trying to help people understand the technology, trying to get people to understand how they can use this technology to actually improve people's lives. Because this shit is fucked up sometimes. As hopeful and as optimistic and lovely and as much as we want to believe that we are building a better world, it also means that sometimes you have to face the reality that our world is one where, like, this is money, this is people's livelihoods, this is their financial well-beings, this is their families, their mortgages, their children's colleges. And this ecosystem specifically, the entire ecosystem from the get-go, has really been built on top of these public-private key pairs. Like every single thing that we do traces back to the private key. And that private key is just like a single string of characters. And it's so important that I've spent countless hours trying to educate people about the importance of this private key. I worked with MetaMask years ago to rename it. Now we call it a secret recovery phrase so that we can like hopefully have people understand the importance of it and the secretness of it earlier. But the reality is, like, the products that I've built are responsible for a lot of money getting lost. And if we don't get significantly better and make Web3 significantly easier to access in the coming years, it means that the products I build and we build are going to be responsible for billions more dollars lost. And that's like a hard thing to wrap your brain around. It's not super pleasant. I would say it's pretty fucked up. And it's been pretty fucked for a while, actually. This is a comment I made in 2018. One of the earliest mistakes I ever made was when we created my Ether wallet, we didn't really understand why you shouldn't let people enter their private keys in the browser on a website. And so we did exactly that. You would generate your private key, you would enter it on the website, and that's how you access all of your money. That was a terrible idea. Don't do that. Seriously, don't do that. This is Dan. Dan is one of the founders of MetaMask, and he has a bit more optimistic take, right? The way he kind of looks at the world around us and the things that we're building is, he phrases it as, we're basically at the eating poisonous mushrooms phase of product development, and we're all just leaping. We're taking the leap of faith. Hopefully, we're coming back and you know, letting our product creators know like what hurt and what didn't, what worked and what didn't. And hopefully the people that are building those products are listening to the people who are adventuring out there into the abyss and updating and improving and iterating on all of their products so that ultimately it hurts less in the future. Because what we are doing is truly like a new paradigm. Like Web3, we are really starting at the ground floor. We are creating entire new systems. We're creating new tech systems, we're creating new social systems, financial systems. Everything is brand new. Unfortunately, sometimes these new paradigms just, you know, they come with some struggles. And I think one thing that it took me years to really comprehend and really grok was the fact that there is such a huge incentive for bad actors to get your private key, to get your secret recovery phrase. Like, it is so huge that, I don't know, hundreds of thousands of like random scammers around the world, North Korean hackers, like literally like nation state actors are trying to get your private keys. And we're building the product that houses that thing, that has all the people's money. That's cool. Over the years, we've seen like an increasing number of scams and SIM swaps and social engineering, phishing, spear phishing, account takeovers, Web 2 account takeovers, Web 3 account takeovers, supply chain attacks, DNS hijacks, BGP hijacks, injection attacks. And even at the root, the cryptography itself, we've even screwed that up a couple of times, resulting in keys either being stolen or inaccessible. And this incentive is so large. Like, I cannot emphasize, the traditional world just does not operate like this. There's almost nothing in the traditional world where if you lose it, like, that's game over, and there's no like path to recourse. Like, that doesn't exist. We have so many layers to protect people. And in crypto, we just don't have those yet. And the hardest thing about this is the reality that truly people don't understand that this string of characters, these like random numbers and letters or these words, like if they lose that or if it's stolen, it's game over. And increasingly, especially with this last bull run, it's not just their ETH, right? It's their tokens, it's their NFTs, it's their collectibles, it's their soul-bound tokens. It's access to communities and games. It's everything, right? It's like basically turning into their identity. Like, we're getting dangerously close to turning that key, that string of characters that nobody really understands, into people's identity. And I think that we think a lot about education. We think a lot about UX. We think a lot about the UI. We think a lot about the things that we can do to fix it. I've given probably like 15 talks covering how you should educate people more and fix your UIs. And it's had some impact, but not enough. And the thing is that the people in this ecosystem are creating real value, and they're creating it so quickly that I'm not sure that just like, you know, updating some copy is gonna cut it. Because again, at the end of the day, the whole entire ecosystem is relying on these freaking characters, right? This string. This string, that's a private key. Don't lose it. That's you, that's your identity and all your money and everything you have and your children's future. Don't lose it. It might look like this. That's the secret recovery phrase. It's the same, right? Don't lose that either. That's everything. It's kind of absurd. Like, when you really just like cut down to the core of it, it's absurd. And we have such big brains in the space, like truly remarkable innovation happening every day. We talk about game theory, we talk about incentives, we talk about the economics, we talk about so many different things. And yet somehow we haven't really been able to come to the conclusion that like, maybe we should focus for a second on how do we actually improve users' lives on the whole at the core protocol layer. Right? We're like solving scalability. We have thousands of VIPs that are solving every single thing. Can we do something for like the end user though? That's going to directly impact their lives and save them hundreds of millions, billions of dollars over the coming years? Because right now, migrating all of your assets from one account to the next is basically the best thing you've got. Earlier this year, MetaMask had 30 million monthly active users. That's a lot of people. There's a lot of private keys out there with ETH in them, with some asset on any of the other 23 EVM-compatible chains, tokens, NFTs, non-standard tokens, standard tokens. There's open positions. There's open positions across chains. There's synthetic assets. And right now, if you get into the space and start doing stuff, and then something happens, right? Your computer is hacked. You're physically attacked. Your entire infrastructure is taken over by North Korea. Your only path of recourse is to try to front run the people who have stolen that phrase and like move all your stuff really fast. And that like not only is absurd, it also like it has a real cost. Like it's hard, it's stressful, it's time consuming. It punishes the people that are most engaged, right? So like the people that we want in this ecosystem the most, the ones that are like total degens, right? It's punishing those people because when something happens, which it will, they are the ones who have to spend the most amount of time and the most amount of real money to move their assets. And frankly, it should not be like this because we can do better. Because this entire ecosystem builds magical shit all day, every day. We literally create billions of dollars out of thin air like nothing. We can do this. It's like it's quite remarkable how limitless our imaginations are in some ways and how limited we seem to be in the other ways. So this is the original sin. We need to understand collectively, whether you're building wallets, whether you're building smart wallets, dumb wallets, whether you're building dApps, whatever you're doing, whatever layer of stack you're in, we are responsible for what we create. We are responsible for how that impacts people's lives. Technology is incredibly, incredibly powerful, but it is not like the end-all be-all solution. We can't just like put technology or code like in a bubble and say like, oh, that's just that thing over there. It's immoral, it's apolitical, it's like just this thing. What we're building is not about, I don't know, whatever's on your landing page, right? Like what we're building is trying to make people's lives better, make society's lives better. What we're trying to do is solve really messy problems, social problems. We're trying to improve how people can coordinate with one another. We're trying to allow people to take control over their lives and their futures and not be restricted by some government, some state, some corporation. And in order to do that, like, we really need to value people, and we should be putting people and the problems that people are encountering every single day sort of front and center. Like, what are we doing to fix that? And our products are a mechanism that we use. The technology is the tool, but the choices, those are ours. And those have to be about people, and they cannot shy away from the hard things. This book is really real, guys. I highly recommend it. All right, so new paradigms. This is a new world. We are actually successfully creating a new world. We have successfully onboarded a remarkable millions and millions and millions and millions of people into this new world. We have successfully disintermediated a ton of things. We've given people control, full control, where nothing can stop them. What we need to be heading towards is saying that this stuff, this key, this whatever you want to call it, right? Whatever it turns into tangibly, this is mine, right? When we talk about identity, when we talk about our things, it's mine. What we should be striving for is it cannot be hacked or stolen because it's mine. I have full control over it. I can use it, I can access it. I can revoke it, right? If I think it might be compromised, I can be like, oh, let's just pause for a second and reevaluate the situation. Let's not let those hackers take that thing. And then once I've secured the perimeter, I can recover it. The things that I do, they don't just happen on my behalf, but I'm giving my full consent. That consent has to be informed. Like, I have to know what I'm consenting to. I have to have a choice in that, right? I can choose to consent or to not consent. Because ultimately, we all need to choose how we interact with the world and also how we impact the world. Because it's our choices that shape this world. Every single choice that we make. So there are a couple EIPs out there that are trying to tackle this problem. I am not going to say which one is best. I think that the solution is probably not one of these. It's probably a few more conversations, some online debates, and whatever evolves from that. I trust the big brains to figure it out. But these are the ones that'll get you started. They're the most recent ones. If you want to go down the rabbit hole, there's like 10 other ones that really did some deep research, but these are the ones that are kind of out there right now. ERC 4337. This is sort of operating, it doesn't require a protocol change. It'll be implemented probably by flashbots. It gives some, quote unquote, account abstraction stuff. Then you have 3074. This is the one that, if you have an account, right, you have a private key right now, you can delegate control. That's like sort of one half of it, right? Like when we talk about key rotation or key revocation or key recovery, it's, you have to like assign that authority somewhere else. And then the original thing, you want to like revoke the authority. 3074 is the one where you can like, it's the rules for how to delegate. And then EIP 5003 is a new one. I think we're calling it auth usurp. This is basically you're going to deploy some like code. We imagine that in the beginning it'll be some simple code, but it'll basically take your current account, your current private key, and it'll give it some like smart contract abilities. 5003 really makes sense with 3074. It doesn't really. There's better ways to do it without 3074. But most importantly, there's a lot of mechanisms and a lot of things we can learn from all the history and all the research that's been done, the conversations that have happened around these, and we can talk and discuss and put our big brains together to hopefully come up with a really strong, powerful solution that will actually serve real people. Because that's the goal. We can do anything we want. And the most important thing that we do is continue to dream. Don't be limited by some, I don't know, stupid tweetable phrase like code is law. Don't have your imaginations limited by this ecosystem's obsession with immutability, or like trying to put technology and code over here and pretending that it's separate from the people over here. Everything has to work together, right? The whole system is where the magic comes from. And so we all have to work together. We have to use the tools available to us. We have to use each other. We have to collaborate, right? We have to get really, really creative. And we can't be limited by anything. All right, so I encourage every single one of you to keep on dreaming, because that's the only way that we're ever going to build a better world. And we're well on our way. The amount of people that are actually using this technology that we're building, it's truly impressive. I never thought that we would get here. But I do hope that we're going to be able to make some real improvements before the next wave. Because as of right now, we're simply not ready for 100 million or 1 billion people to have their identities tied to that single string of characters. All right. I also have to show some stuff. Okay, so for those that don't know, I'm at MetaMask. MetaMask is part of Consensus. Consensus has a ton of amazing things going on. One of them is Village DAO. So remember how I was talking about, like, you know, incentives and getting people working together and collaborating so that, like, everyone can be better and more empowered? Village DAO is one of our various attempts to do this. It's really, really exciting. Is Village DAO in the house? Make some noise. Find them. They're freaking cool. They'll explain everything to you. It's such a cool initiative, and yeah, I'm so excited. Okay, next, Infura. You know that evil centralized thing that the whole ecosystem is relying on, and it's going to be our death? Yeah, no, it's well on its way to being decentralized. We could not be more excited. EG and the team have been working on this for, God, as long as I've known him, and I've known him since like 2016. It's been crazy. But we are actually making moves there. That's a QR code. I don't know where that QR code goes to, but I assume it'll give you more information. Or maybe a party favor? I don't know. Find out. Is Infura in the house? Is Patrick here? Oh, okay. Okay. They'll explain to you. But all I want to say is that we are committed to building a decentralized world, right? We really are. And last but not least, where's Snaps? Okay, we got a lot of Snaps people here. MetaMask Snaps, this is the future of MetaMask. I know every single person in this room has some problem with MetaMask. I have problems with MetaMask. I sit there and I go, like, why do you do this to me, MetaMask? And I'm building MetaMask. And then I tell people to fix it, and then, like, I yell at MetaMask more. I know that you've all been in this boat with me. MetaMask Snaps is actually the solution, though, because we can't keep making MetaMask bigger. We can't keep running around, like, doing whatever Taylor says to do. That's not scalable. We are building for billions of people. What Snaps does is it enables every single person to extend the MetaMask functionality. So instead of MetaMask having to, like, build and maintain something for your custom thing and try to keep up with this ecosystem that moves so freaking fast, what we're going to do is we're going to put the power in the builder's hands to actually extend MetaMask to better serve you as the builder and also better serve your users, because you actually know best, right? We can grow our team bigger and bigger and bigger, and we still won't be able to keep up, because the innovation that is happening in this ecosystem is so, so remarkable. And that's what Snaps aims to do. It aims to give everyone, the builders, the smart, big brains in the room, the power to make MetaMask work better for you. Like you heard earlier, there's a bunch of Snaps people here. If you're a builder and you're frustrated with MetaMask, talk to them. They will explain it all to you. And that's all I've got. Just want to say thank you.
Amazing. That was an excellent talk. We have time for just one question, if anybody has a quick question. If so, please raise your hand, and we'll get a mic to you ASAP. Do I see a hand? I saw one, and then it went down. There we go. I'm just blind.
These lights are crazy.
Yeah, hello. Just a quick question. What will be your perfect world for perfect users, a perfect user system for you?
In terms of like the accounts and the private keys and stuff?
Yes.
Yeah.
For example, on what thing can we back the user information? So right now we, in the physical world, we back up with the people's body. I know that person because I see that person physically beside me. So I will need something based on the physicality of the person, or something like a second factor authentication. But then give you the clicker.
Yeah. So the reason why I kind of shy away from saying like this one technology, this one thing, or this one thing that these one groups of people or this standards body is working on is like the solution, is that I think, frankly, I think it's ignorant to think that like any one party or any one group of people can serve like the entire world perfectly, and especially at the pace of innovation that we're seeing. I think that there's like a couple important factors, and I think the conversation is often marred in this like account abstraction is the word, if you want to Google it, like Ethereum account abstraction, you can get the whole history. It's such a big thing, and it has so many goals at this point. But the thing that I'm most focused on is like, I think we need to provide a migration path for users that is as cheap as possible. So not migrating all their assets, but going from whatever this old way of doing things to the new way of doing things has of a low cost. Secondly, I think that people should be able to like revoke, whether that's like permissions or their entire key or whatever it may be. They should be able to say like, no, that's not valid anymore, that's not me anymore. And then I think that obviously in order to make those two happen, there has to be some delegation, some permissioning system, something where, because like if you revoke all the permissions, then you don't have any, you can't do anything. So you have to like give them somewhere else. And there's a ton of people that have been doing a ton of work on this over the years. The Ethereum account abstraction research is in conversations like those. That's one thing. But if you look at decentralized identity, which has been a decades-long effort by some remarkable organizations around the world that are really focused on this, that's like a whole another rabbit hole that you can go down. And I will not pretend to think that like I deeply understand this design space as much as them. So if this is something that like really interests you and you want to start working on it, I would definitely recommend like starting there and looking for the experts and the people who are talking about it, because they are way smarter than me.
Awesome. That's all the time we have. Please give Taylor
Thank
a big round of applause.
Love you.
And with that, we are ready for our last talk of the evening. Without further ado, I'd like to welcome Yin Tong and Nalin Bardwaj to talk about recursive ZK applications and affordances. Please give both of them a big round of applause.
Hello everyone, I'm Nalin.
I'm Ing Tong.
And today we're going to talk about recursive ZK snarks, the kinds of applications they unlock, and how we can implement them. So first we should talk about what recursive proofs even are. So in the context of snark, recursion is usually the ability to verify a snark proof inside of another snark proof. So this is the ability to say something like, I know a snark proof that when I run the snark verification algorithm on, it returns true inside of another snark proof. And the sort of key part here is that verification of recursive ZK snarks is usually not significantly slower than ordinary regular ZK snark verification. So now that we have this primitive in mind, we should think about the sort of natural question is, why would you want to make recursive snark proofs? So typically, regular ZK snarks, we think of them as having two sort of properties, succinctness and zero knowledge. So recursion, in fact, unlocks powerful versions of both of these properties in the form of compression, which is a stronger version of succinctness, and multi-party composability from zero knowledge. So first, let's talk about compression. We think of compression as supercharging succinctness. And in particular, usually the applications of compression tend to share a sort of common pattern. And this common pattern looks like, let's say we have a prover who wants to show a verifier some n pieces of knowledge. How do they do this? They make a proof showing two sort of things. First, they show one piece of knowledge, and then they also show, additionally the n-1 other pieces of knowledge. But for these n-1 pieces, instead of showing each piece individually, they will show that they know another snark proof of these n-1 pieces. So the next question is, how do you make the snark proof for the n-1 pieces of knowledge? And in fact, we use the same kind of strategy again. The n-1 pieces of knowledge, we show one piece of knowledge, and additionally we show that we know another proof of n-2 pieces of knowledge. And so then you just cascade down this sort of strategy, and you end up with this situation where you're verifying one snark proof, and in that it's automatically verifying these n items of knowledge. Another instance of compression that's particularly helpful to point out is the setting where you want to compose between different proof systems or arithmetizations, and at the time also pick the good features of each of them. So for instance, you can have some setting where you have two different proving schemes, one where you have a fast prover, but unfortunately the verifier is slow, and another where the prover is slower, but you get the trade-off that the verifier is fast. So using recursion, you can compose between the proving system from the wider setting to the narrower setting and get a tiny proof output, as well as fast prover getting sort of the best of the both worlds. A concrete sort of instantiation of this interoperability is the setting with Starks and Grot16. In particular, Grot16 is very cheap to verify, whereas Starks are very easy to prove. So if you verify a Stark proof inside of a Grot16 snark, you end up with a proof of the original statement with a fast prover as well as a fast verifier. So generally, compression has this sort of property that is very mechanical, and usually you're rolling up some giant list of computation or items of knowledge incrementally into a single proof. So just to give a flavor for sort of what applications this unlocks, let's look at things that are interesting to roll up. So first is signatures. Over the summer, we built applications using sort of this primitive of recursive compression of signatures called isocratia, where we end up with a low trust, low cost sort of roll up of off-chain votes and end up securing governance. And then more related to sort of blockchain land, you can do the same kind of trick with light client proofs. And in fact, Plumo, which is Solo's light client, is based on this sort of idea. And there's also another group named Axiom, which is exploring sort of more cooler use cases for this with aggregating and providing historical data through the use of recursive snarks. And then finally, the sort of hot topic in blockchain land these days is making roll-ups of transactions. Two particular ones that are sort of interesting to point out are Mina, who sort of used this recursion primitive as a consensus layer primitive, and Polygon Hermes, who used the exact strategy of like using Starks for fast prover settings and Grot16 or Snarks for fast verification settings. Next, let's talk about composability, my personal favorite property unlocked by recursive snarks. So to give some context for this, let's take a step back. Let's think about what a normal ZK proof, what's the context of a normal ZK proof? We usually think of ZK proofs in this context where a prover is showing knowledge to a verifier without revealing the underlying fact of the knowledge. With recursion, in fact, you can unlock something more powerful. A prover can show knowledge to a verifier without fully knowing the underlying facts themselves. So this is a bit hard to model, so I'll just lead with an example. Over the summer, we built this application called ETH-DOS, which is Erdos numbers on social graphs. So these social graphs are sort of graphs of relationships of people saying, I am your friend kinds of things. And for instance, here we have this graph, and Vitalik sent someone, who sent someone, who sent someone, and finally I ended up with a 4-degree path to Vitalik. Now I can prove that I have a 4-degree path to Vitalik without revealing any, or without knowing any of the intermediate parties in this path. So how do I do this? I say, I am a friend of Adhyan, and Adhyan has a ZK proof that he is 3 degrees from Vitalik. So in this process, I do not know the 3 degrees that precede Adyan, and I have still convinced any external, as well as myself, that there is a valid path of 4 degree between me and Vitalik. So, of course, this is not the only application you can build. In general, we think composability is particularly cool to think of in sort of incomplete information game kinds of settings. Of course, the sort of very typical example, the very starting point we thought of was games like Telephone or Chinese Whispers, where you pass a word around or something and you want to make edits to it incrementally. And then you can make more complex applications, like party games like Mafia, those kinds of things. And then more relevant to blockchain land, you can build private state channels and roll-ups of that sort.
So now that we have some intuition for the high-level properties of recursive proofs, and now that we've seen some classes of applications that are enabled by them, you might be feeling that recursive proofs are kind of unreasonable. We get unlimited compression and composability. So I guess the natural question now is, how do we implement and construct these systems? So right now, there's broadly 3 classes of recursive proofs in production. And as we descend the hierarchy, we are relaxing the requirements on the proof systems which are eligible for recursive schemes. So at the very top of the hierarchy, we have really the most stringent requirements. So we need proof systems with verifiers that are sublinear, that are succinct in the size of the statement being proven. And this enables us to do full recursion at every recursive step. So this has been implemented for the Groth 16 and Fry proof systems. So if we relax our requirements a little bit, and we say, even if we don't have a succinct verifier, maybe we're happy enough just with a succinct accumulator. So intuitively, what this means is that we want a verifier with this shape, that they have a succinct check, a cheap check, and then separately they have an expensive check. And so here we can instantiate an atomic accumulator, and at each recursive step, we only perform the succinct checks. And we accumulate the expensive check and delay checking it until the end of a long batch of proofs. And doing this gives us amortization of the expensive check. And finally, if we relax even more, we don't even require a succinct accumulator. Now we're just happy with a succinct public accumulator. And the idea behind this split accumulation is simply that you split your accumulator into a public and private part. And the public part is short, and this is what we accumulate at each recursive step, whereas we delay the verification of the private part of the accumulator until the very end. So let's go through these constructions at a high level, one by one, just so you can see the shape of it. So probably the cleanest shape is, the cleanest shape would be full recursion. So over here we start with our application circuit, and it's F of Wi gives you Zi plus 1, right? It's a normal relation. Now, we bundle that together with a recursive verifier, and basically this recursive verifier takes in a proof instance that was produced by the previous instance of the recursive circuit. And so if we look forward, we need to generate a proof of the whole recursive circuit in order to input to the next recursive instance. So in this way, we're chaining recursive circuits. And at each step, we are fully verifying the previous instance. And when we get to the final verifier, we no longer need to bundle it with the application circuit, and here we can just perform a final verification of the proof outside the circuit. So this is full recursion. It's the cleanest API. Now we're gonna get slightly more messy, and we're gonna relax our requirements to get an atomic accumulation scheme. So now if you recall here, in an atomic accumulation scheme, our verifier is not sublinear. So in fact, the verifier inside the recursive circuit is just the accumulation verifier, and it only concerns itself with the succinct checks of the verifier. And the expensive check is accumulated and deferred at each step. So here we are chaining basically instances of proofs and accumulators. And at each step, we're just procrastinating on performing the expensive check. Well, until we're finally satisfied at the end of a long chain of proofs, we perform the final decider subprotocol that finally bites the bullet and does the linear time check. But at this point, we can do it outside the circuit, and at this point, the cost of the linear time check is amortized across a big batch of proofs. Now, from here to atomic accumulation is just a small step. So it's just splitting up your accumulator and your proof instance into a public and private part. And now the verifier, the recursive verifier, gets even smaller, and it concerns itself only with accumulating the instances, the public parts, and it does not have access to the private parts of the accumulator, and rather it relies on the prover to provide some commitments to the private parts, which it then performs accumulator checks on. So a lot of these constructions I've described are really cutting edge, and they come from a feature of our modern proof systems that are very modular in design. And as we get a better understanding of the building blocks and the components of our proof systems, this lets us customize our proving stacks with a lot finer granularity. Oh. And recursion, as we saw, also allows us to compose proof systems and to get the best of both worlds in many cases. So here's an example of a modular conception of a proof system. So I work on the proof system Halo 2. And I think of Halo 2 in terms of these 4 components. So at the very front end is where you're interfacing with your business logic. So you take a relation and you arithmetize it into, so in Halo 2's case, we encode our values in the Lagrange basis, and we encode constraints on these values as polynomial identities. We then input these polynomials into this information theoretic polynomial IOP that basically checks the correctness and the consistency of the polynomials encoding our circuit. And then we realize this polynomial IOP using a cryptographic compiler. So in this case, it's the inner product argument and the Fiat-Shamir transform that allows the prover to define their interaction with the verifier. And at the very end of it, Halo 2 is a recursive proof system, and we can in fact instantiate an atomic accumulator over the inner product argument. So these are the 4 sort of modular pieces of modern proof systems that I think of. Now, we can do pretty funny things composing these pieces. So I've thought of 3 cases. So the first one is information theoretic compilers. And an example of this is MPC in the head. What this does is it converts one information theoretic protocol to another one. And in this case, it's the prover sort of pretending to run a multi-party computation in her head. So she's really simulating the multiple views in an MPC and committing to those views. And now the verifier is only checking the outer protocol, being the MPC, instead of checking the inner protocol, which is the ZK proof. So this is one very interesting way to compose proof systems. Another way that we've seen before in this presentation is more or less just implementing verifier X in prover Y. And you would do this also for efficiency gains. And sort of the last class of composition that I came up with was really just thinking up better cryptographic compilers. So there's this recent paper by a group at Consensus, and they took this protocol, GKR, that's highly optimized for repetitive computations like hash functions. Now, but the problem with GKR is that it has a slow verifier, and and it also uses the fiat Shamir hash as a cryptographic compiler, and this makes it very inefficient in the context of recursion. So what the team at Consensus did was they came up with their own cryptographic compiler that was custom made for their target proof system. The target proof system here is like a Groth 16 R1CS proof system. And so really, like, that's going in the middle and making changes, like customizing proof systems at a very low level for efficiency. And yeah, I think this leads me to ask whether or not we can systematize this process, and whether or not we can, I don't know, explore this optimization space in a well-defined way. So you can think of this as kind of a call to action. So I think there's certain nice to have, certain to-dos that all proof system implementers would really like. The first being good benchmarks, fair benchmarks of heavily used primitives like hash functions, like big int arithmetic. So benchmarks of these primitives across different proving stacks. And the second would be, it's a kind of a meta requirement, is to think of like what metrics we're interested in. For example, efficiency, for example, proof size, and basically how to optimize towards these metrics. So on what basis are we comparing different compositions and configurations? And the last sort of call to action would be to think carefully about how security properties also compose. Like, excuse me. Like, is it the least secure proof system, the fewest bits of security, or like some weird composition when we mix and match proof systems? So all these are questions that it would be great to have everyone's input on. Like, even this taxonomy that I came up with, I'm not sure that it captures all features of proof systems in the best way. So Nalin and I actually help out at a group called Xerox Park. Oh, we didn't put the name on the slide. It's 0x Park. And we're setting up this task force to look into this area of recursion, aggregation, and composition. Yeah, and I think like I might as well take this opportunity to shout out Xerox Park. They supported a lot of our work, a lot of those fun apps, and a lot of these community efforts. Yeah. I think that is all I have, so thank you.
Awesome. Well, thank you so much. We have time for 1 or 2 questions. If you have any questions, please raise your hand. We got a question here on this side.
Hi. I didn't think this would work for years and years and years. And I'm not even sure that it does work. It does seem way too good to be true. So can you prove, and how do you prove that it's secure to do recursive proofs like this? Like, where is the security proof? You know, I don't know how to convince myself that this works actually.
Yeah, I mean, that is a good question. It seems very unreasonable that you can prove like an arbitrarily long history of computation with a constant size proof. It does seem unreasonable, so I will say that security proofs exist. They're in papers. But Nalan, do you have like some intuition as to why the security should hold?
Yeah, for sure. I think one sort of physics-based view that we've seen before is like, it's like, oh, you have 3D space and you're collapsing it to like a 2D surface. I forget the exact name of this, but...
The holographic principle.
There you go. So I think there is like some sort of meta justification you can come up with to convince yourself if that's like the sort of thing, but there is proofs of all kind that are actually substantial.
It's a good question.
Any of the last minute questions? We have one at the back all the way over there. To your left.
So recursive proofs are real fun, but if you do it at scale, then it's like you have Scylla and Charybdis napping at your heels because of the proof carrying data, right? If you want to build on recursive proofs and it doesn't happen at the same time, so let's say you do a proof and you do a recursive proof, and then you have to wait for a state change for something else that might happen much later, you need to keep the proof carrying data around. And as you know, but most here, that is typically a very large amount of data. So it's like if you're doing it at scale, you're really running into the issues of data provisioning, and all the fun part can get really expensive really, really quickly, not even talking about like the computational overhead that you have.
Yeah, for sure. I don't think recursive proofs are a silver bullet, and I think they're better suited for some shapes of applications. So recursive proofs are very commonly used to reduce prover space complexity. So breaking up a large circuit into many smaller parallelizable circuits. So yeah, but I agree, like in context of applications with more complicated and like timely data flows, we have to put some care into how and where we are inserting this proof carrying data. Yeah.
Right, and also just to add, I think there's also some interesting like sort of clean separation here of like rules versus data availability sort of problems. And if you just look at data availability as a sort of black box problem, you have lots of blockchain kinds of solutions for it. And for instance, Isocratia explores one sort of solution that maybe you can check out the blog on.
Yeah, also to add on to that, like I really like Nalan's thing about composability, the fact that you can play incomplete information games. So I think sort of fun applications like that are unique to PCD are also very interesting to explore.
Amazing. That's all the time we have for today. Please give Ian and Elaine a big round of applause. And with that, we are done for today. Thank you so much for staying here with us. We'll see you all tomorrow for the rest of the talks. Have a great evening, everybody. Take care.
seem stuck now. This pain still weighs me down now that you're gone. Oh Lord, I seem stuck now. My patience wearing out and you've moved on. Oh Lord, am I hurt? Am I alright? My spirits don't seem high. Am I lost? All these cold nights and these tears don't seem to dry. It seem dark. Am I blind? Is my heart lost all its sight? This poison's taking over. Feel like I've lost life. Still you're not here. Still you're not here. Got me questioning, would I love again? Still I wonder when. This don't make no sense. I seem stuck now. Pain still weighs me down now that you're gone. Oh Lord, I seem stuck now. Patience wearing out and you've moved on. Oh Lord. I've tried to let you go and give you up in my mind. I've tried to let it go and say hello, man.